just go out and have people come in, tell them we are starting. All right, welcome everybody to the second day of the Theory Festival. We're very pleased to be here, and let's get the talks of the day started. I have just one very quick announcement. The meals today will not be in the main dining hall that it was yesterday. We have a smaller group also today. We have two dining halls. You will see it's in this foyer area itself, the annex dining hall and the so-called exhibition hall, also known as hall 2 or something, not sure, but basically just here. Okay, so there's another event happening in the main dining hall, but our food is better, so come to ours. All right, so I'll hand it over to Krishna to do the introduction.
Thanks, Shweta. Good morning, everyone. Thank you for joining us early on a beautiful Saturday morning. We are delighted to welcome Professor Amit Kumar from IIT Delhi. He's a professor in computer science and engineering there. He's received his PhD from Cornell and BTech from IIT Kanpur. He's a recipient of the prestigious Bhatnagar Award, Fellow of the Indian Academy of Sciences and Indian National Academy of Engineering. We are delighted to have you here. The floor is yours.
Okay, thanks Shweta, and thanks Krishna for the introduction. Thanks organizers for organizing this wonderful event. Pleasure being here. So today this is more like a survey talk. This will be I think it's, now it is. Okay. So this is more of a survey talk. We'll talking about online algorithms. So online algorithms, of course, is a well-established area. It has been around for 50, 60 years. But this is a new model and still an area which is evolving. So what I'll do is I'll just give you some examples, show you some sort of sample settings. But the main takeaway should be that this is an area which is evolving, and you can formulate interesting problems here, and there are also interesting techniques. So let me just begin by just explaining the first phrase, online algorithms, in case you have not seen this. And what I'll just do is show you a few examples and just tell you what predictions essentially mean here. So okay, so let's just broadly, the area of online algorithm essentially refers to the fact that the input to the algorithm is not available in one go, so it arrives over time. So this is an algorithm, and the input is going to arrive one by one, and so at any point of time you've only seen part of the input, and depending on what portion you have seen, you have to sort of maintain a solution corresponding to that portion. So some input has been there, so you maintain a solution corresponding to whatever that input is, and the input will grow over time, and then the solution will evolve as the input arrives. So I'll show you some examples, it will become clearer. So but that's the generic sort of setting. So unlike settings where you have the entire input and you just want to run something in polynomial time, note that here the input is sort of not clear at the very beginning, and so that's where the hardness of the problem comes from. Okay, so so I'll take this as a starting example and show you some sort of sample results here, and then we'll move on to some more examples. So paging is a very classic setting. So the problem is as follows. So you're given n pages. So think of each page as a color. So there are n distinct colors, and but you have a bag and you have a cache which can only hold k of these colors. So k pages. So k is a number which is, think of it as a number which is much smaller than n. Okay, and what happens is that at each time t, a request for a color or a request for a page arrives. and you have to make sure that that color is in your bag there. Okay. So of course, if bag size k was equal to n, you'll just put all the colors there, and then this problem is done. But the issue is that k is less than n, and you have no idea what is going to come in the future. Okay. So for example, if this comes, then that color is already there in the bag. Great, no changes. Now if this color comes, then that is not in your bag, and you have to bring that color in your bag. But because that bag has capacity 2 only, you have to throw out one of the 2 colors. Okay, so let's say you throw out that color, and so now you bring in that color. And so this keeps on happening over a period of time. So this color again is not there, so you have to bring it. Now this is again not there, and so on. Okay, so far so good. And the objective here is that each time you have to throw away a color and bring a new color. That's called an eviction. So you have to minimize the number of such evictions. Okay. So that's the classical paging problem. Okay. Now how do we? Okay, so we'll talk about what you do in such settings, but how do you evaluate the performance of some online algorithm? Right. And the standard way of doing this is what is called competitive ratio. It says that look at any sort of input. Okay, so look at any input, and so P1, this is an input, and look at numerator. I have look at how many evictions your algorithm is incurring, and in the denominator, I have the number of evictions of an optimal algorithm, which knew the entire sequence in advance. So I'm going to call it an offline algorithm. So offline essentially means that you know the entire input, so you know what's the best strategy, and that's the best you could have done. Okay, and so the numerator is the online algorithm, which does not know the future. So this ratio will always be bigger than 1, and so you're looking at this ratio, the ratio, and typically you would like this sequence to be very long. Yeah.
So here are you assuming any distribution on your input? So in this particular example, you can't do anything except throw things randomly out, right?
Okay, so we'll discuss that. Good question. So just hold on for 2-3 slides, and yeah, that's a great question. Yeah. Sorry.
Looking at the fixed capital.
Fixed.
T, so
T is think of soup over all sequences, right?
but it's not the other. It's not for every time step. It's the same.
Well, it kind of says so. It's the same thing. So, and the reason why I don't want T to be very small is that I don't want to get stuck in examples with 1 or 2 pages. You want to ignore those things. Okay. So, so what's the what would you do if you knew the entire future? Okay, and this is something you study in algorithms class, right? That there's a greedy algorithm. The greedy algorithm says that if I have certain number of pages or colors in my cache and I have to throw away something, I look in the future and see the page which will be requested furthest in the future, and that's the one I want to throw away. And that's a natural strategy, and you can again prove that this is optimal also. So if you knew the entire future, you will look at your cache and see which one is the furthest in the future and throw that away. But of course, you don't know much. And what can an online algorithm do? Well, it's very easy to show you, as Shweta also pointed out, that it's quite pessimistic, but still, what's the best it can do. So it's very easy to show that any online algorithm, its competitive ratio, remember this ratio means that how good this algorithm does versus the best possible. This ratio will be at least k. K is the number of slots in your cache. And why is that? So imagine that this is your cache, and I am an adversary. I am trying to sort of fool this algorithm that you have. So each time you maintain a cache, I'll request a page which is not there in that cache. Okay, so I'll keep on doing this, right? So those two, I'll request a color which is not there. Again, I'll request a color which is not there, and so on. So your online algorithm, if I know what your algorithm is, I can make you pay 1 unit of eviction at every time step. Okay. Whereas if I knew the future, because I can hold k pages, the offline algorithm would incur such an eviction only after every k steps, because for the next k steps, I know what to hold on to my cache, right? So this ratio can be made at least k. And again, you can also ask, are there algorithms for which this is at most k? Yes, there are algorithms like that. I'll just show you one. Okay. All right, questions? Okay. So for example, this is a standard algorithm. It's called 1-bit LRU, and this is known to be k competitive. And again, you can think k is a very pessimistic number, but in some sense, this is the best you can do. And this is again an algorithm which is widely used. So let me show you what 1-bit LRU is. So LRU means least recently used, and it's a very standard algorithm in architecture and other settings. So what is the algorithm? The algorithm is that suppose this is your current cache, and with each page you maintain a bit, a 1 or a 0. 1 means that it has been recently accessed. 0 means that it has not been accessed. Okay. So whatever the page is, if it gets accessed, right? If its bit is 0, you make it 1. Basically saying that it has been accessed in the recent past. And again, so this is already there, nothing happens. Now this page is there, but it's not in the cache. Okay. So what you do is you evict one of the pages which is marked 0. And that's again is natural because 0 means this guy was not recently accessed, so hope is that it won't be accessed in the future also. So let's evict one of those guys. So you basically throw away such a guy and make it 1. Okay. And again, this makes 1. Now what happens when everybody is 1? And now if you access a page which is not there in the cache, now which one do you throw away? Because all of them are 1. So the rule is that if everybody is 1, then you reset everybody to 0. And the game starts all over again. Okay. Yeah. Just arbitrary. Yeah. But we will come back to that issue of ties. Okay. So
Why should you lose all the state you have? I mean, yes, you ran into a bad situation and you have to do something, but why do you want to throw away all the information that you have?
Yeah, this is a good question. So and the reason is I'm maintaining only 1 bit. If I were maintaining 2 bits or 3 bits, you could have said that I would maintain more information.
No, like you could throw away one of the ones and put this and also have it 1.
But then everybody is 1, right? So now I have no way of doing anything, right?
Okay, so randomly pick 1 and make it 0 or something.
Right, but essentially, if I just maintain everybody to be 1 from now on, not much is happening. And if I just randomly throw away somebody, suppose I don't reset to 0, then it becomes you randomly throw away one page. That may not be a good strategy because, imagine a setting where cache is large and I'm only sort of playing between a small set of pages. I want those guys to stay in my page, right? And even an online algorithm should be able to detect that. So I want some distinction between those pages. Yeah, so if everybody becomes 1, I make everybody 0, okay? And let me quickly argue why this is K competitive, right? And the reason is this, right? So think of these reset events. Between these 2 reset events, how many cache evictions did I incur? K, right? And I'm seeing sort of K plus 1 colors between 2 such reset events. So any offline algorithm also will have to incur at least 1 eviction. So essentially that's the reason why this is K. Okay. Now we can ask, that strategy that I was doing, right? Where somebody is observing how the algorithm is behaving and giving you the worst possible input. That's very tailored to an algorithm. What if my algorithm was allowed to use randomness? Okay. So if I allow my algorithm to use randomness, right, then an adversary cannot really predict what I will do. And so it cannot really design a tailored input which will make me fail every time. And but if my algorithm uses randomness, what does it mean, right? What does competitive ratio mean? Well, all I do is I just look at a define expected competitive ratio. This is the definition. It is just in the numerator, I just replace it by the expected cost of my algorithm. Offline, of course, will not be randomized. It will be some specific solution, but in the numerator, it is my expected cost. Okay. And if you do that, then I can have a randomized version of that algorithm which said that look at all the guys which are 0, throw away a random page among all those zeros. Just make that adjustment in that algorithm, and then you can show that this is log K competitive. Okay, so K goes down to log K. Again, these are very classical results, and it's not hard to show this. You can try to prove this, but let me not go there. So the theme of this talk was something else. That and this is where the second part of the title comes in. That how about I involve another sort of player in the game, which is prediction about future input. So suppose somebody is giving me some sort of predictions, and this is very natural in practical settings. If you study architecture, there would be some sort of algorithm which will be giving some sort of prediction about the future sequence or something like that. But what do I mean by prediction? These days it could just be some ML model which is giving you some sort of prediction about something. Right? We'll see what that something could be. And of course, the question would be, what is it that you're predicting, right? So at a very high level, the idea is that there is some ML algorithm or some learning algorithm which is observing your data, which is observing your algorithm, observing the optimal solution, and giving you some hint about what's going to come in the future. And again, this is very open-ended, right? What do I mean by what are we predicting? Yes, sorry. Log case type, sorry, I should have said that, yeah, log case type. So this is, again, the same input where I play with just k plus 1 pages, and you can show that, using Yau's lemma if it's a random sequence. Okay, all right. So, so let me show you one specific paper which sort of initiated this area and the model that they chose. Okay, this is not the only model which has been considered in the literature, but this is one of the initial models. They said that, okay, so when a page is requested, I'm going to predict when is the next time it will be predicted again. Okay, that's what my ML algorithm is going to tell me. Okay, so let's say this page is at time t, this yellow page is predicted. Some ML algorithm is going to tell me when is the next time it will be accessed again. Okay, that's all. And notice that the offline algorithm, remember, furthest in future, this is exactly what it needs. Right? So among all the k pages that I'm holding in my cache, it needs to know, who is the last guy here. I'm going to throw that away. Okay? So if these predictions were perfectly accurate, okay, then you can actually implement your offline algorithm. You're done, right? Now the issue, of course, is that no prediction will be accurate, right? So if we are adding such a thing in our model, we should also account for the fact that there could be errors in these predictions. Okay, so maybe this guy said that prediction was there, but the actual thing happened much later. Okay, can happen. So I need to have some way of measuring. If I'm using predictions, I need to have some way of measuring errors in my prediction. Okay, and again, there can be various ways of measuring errors. Here I take the L1 norm. So what I do is I look at every time t. Look at, so these are discrete times, right, integer times. At every time one page is being accessed. So I look at the difference between the actual prediction, and the actual sort of event when this page was next accessed. So look at the difference, absolute value, sum over all time t. And the hope is that, if E is very small, if the error is very small, then my algorithm will be near optimal. Okay, can I show something like that? Okay. So, so let's say, right, so why not just, great, so let's take the predictions and just use my, now that I know that furthest in future is the optimal algorithm, let's pretend that these predictions are correct and just run furthest in future with these predicted times. It will keep missing. So as Siddharth is pointing out that even if you make very small errors, maybe this will incur a huge cost. But let me show you what is known. So yeah, so let me just run by what you're saying. So maybe show you one extreme example. So let's say that this is the input. Okay, input is that initially yellow, then these two colors keep on alternating, right, forever. And cache size is 2. So somebody who knew the future would say that, okay, yellow, let's throw away yellow and just keep these two colors in my cache. And then I will be done forever, right, till the yellow thing which is accessed way further in the future. Okay. Now, however, the prediction is saying that, look, the yellow page is going to occur right next here. So the error is, maybe the length of this entire time scale. But it's only for one guy. For everybody else, the error, it's, let's say, accurate. But just because you made such large error in the beginning, right, you will keep thinking that the yellow is the next page to being accessed. And if you just use this prediction, you will always keep yellow in your cache. Yeah? Are
you assuming that in every step you're predicting yellow to be...
No, it's good. So the question is, when I'm here, this guy had said that yellow would be accessed here, right? That has not happened. So what do I do? So right now my algorithm is that you just use, even if it is something in the past, use that as your current estimate. Now you can say that maybe, if past has already happened, throw away that information. It doesn't help. So that's why I'm not showing you a more extreme example. But even if you said that, oh, here this guy said it would happen earlier, it's wrong, let's ignore it. If you have those kind of strategies, even those won't work. I don't want to show you all those examples, but essentially the point is that, so let me just show you. So if the total error is alpha times opt, okay, so opt is the optimum number of evictions. So in this example, for example, optimal number of evictions is 1, just at the beginning, and so alpha opt is the entire length. Then this algorithm can incur alpha times opt. Okay, so basically saying that whatever your total error is, your algorithm can incur that many evictions, extra evictions. Okay, so if error is very large, then, and this is tight, so you can also show big O of alpha. Right? And one annoying thing is that, remember 1 bit LRU was k times optimum. Yeah.
Sir, you said that we are assuming it to be random, that it's not following any kind of a distribution.
What do you mean? It's a worst case. Yeah.
You are not assuming any kind of distribution of that.
Right.
So, what good does a loss function do in that case?
So the loss function meaning the number of evictions. I'm counting number of evictions, right?
Right, so the error that you mentioned, that next.
Oh, that error is essentially fix an input. So it's error input specific, right? So for this input, my prediction is giving a number to each time, and there's an actual number associated with each time, right? The next time, you're looking at this difference. So loss function is this difference.
Yes, so what good does that loss function do if there is no particular distribution getting followed? That is.
So I'm not understanding. So imagine that there is an input, right? And this prediction gives you a prediction at every time t, and there's an actual next t at every time t. You look at the difference and you just add this up. This is my error function. Okay. One other thing is that if alpha is right, this error is very, very bad, more than k opt. This is saying that you're even now going beyond what is possible with worst case. Should not have taken this help at all, right? So this is called, in literature, it's called robustness. It basically says that if your prediction is so bad, right, that you should not have used it, you should catch that, right? I mean, that robustness guarantee should be there. And again, it's not hard to build this into all these algorithms. I'll show you just for this one, but most of the time it's very easy to do this. So I will not sort of assume such things. So for example, how will you do it in caching? You'll say that, look, suppose somebody told you the optimal value, optimal number of evictions. And this is something I can guess, doubling tricks and all that. So suppose you know the optimal value. Then if your number of evictions exceeds k times opt, then you realize, oh my god, if I had just followed 1 bit LRU, then I could have just stayed within k times opt. So then you're just going to throw away the advice, right? Just fall back on the 1 bit LRU algorithm. So such kind of tricks I can always do. So I can always say that my eviction cost is minimum of whatever the advice is, comma k times opt. So if the advice is very bad, I will at least fall back on my robust algorithm. So those kind of things you can always do. Okay. So let me just sort of summarize. So every prediction has some errors. Sorry, let me just show you what else is known here. So this was the first paper I mentioned. Now if you use randomization, you can show square root alpha. Okay, so that alpha becomes square root alpha. Subsequently, this has been improved, and currently the best is alpha over k. So if the error is alpha times opt, then you can get alpha over k times opt. The idea of the algorithms here, so you can ask, what are the algorithms here? Essentially, the algorithms are like this. You initially follow the predictions. Now, suppose a page fault occurs. You have to evict a page. You try to follow, why did this page fault happen? This happened because, earlier at some point, I should have kept this page in my cache, but I had to evict it because of some reason. And that reason was because of some other reason. So basically it leads to some sort of chain of events. And if such chain of events gets very long, it means that there is a long chain of, or there is a long cascade through which this error was happening. Okay, so whenever you sort of follow these predictions, you realize that if you're falling into a long chain of bad decisions, then you fall back on your randomized algorithm. So some algorithm like this. Okay, so I don't want to get into too much detail, but essentially some algorithm which combines predictions, following predictions, but falling back on your randomized LRU after some sort of setback, okay. And it gives you these kind of results. Okay, there's a lower bound which says that you cannot beat log of alpha over k essentially. So there is a slight gap there, but essentially this is what is known about this problem. Okay. Now there are other models, which I will not discuss, which are like, somebody gives you a hint about what's going to come in the next 10 steps or things like that. But let me sort of summarize the high-level theme. So the high-level theme is that online algorithms, typically come with very high competitive ratios, and this is because the future sequence is unknown. And the hope is that some prediction or advice can be useful in improving these guarantees. And again, this is an evolving area, so you can always ask, what are we going to predict? And it could be some feature of the input, as you saw. It's going to tell you when the next page is arriving, but it could be something else. Sometimes, people predict the entire input, or it could be some advice on what to do, right? When you see this input, what to do then. For example, if you're doing set cover and an element is arriving, it can tell you, which set to pick. So there could be some other kind of advice, or it could be just giving you some feature of an optimal algorithm. Right? It will be telling you that this is how the optimal algorithm behaves, so try to follow this pattern. Okay? So it could be any of these, or it could be something completely different. And whatever kind of prediction you're using, there has to be a notion of loss or an error of a prediction. And your algorithm's performance should degrade smoothly with whatever this loss function is. And standard hedging strategies always will ensure, most of the time they'll ensure that there is robustness in your system, that if these advice or predictions are going very bad, then you can fall back on your old algorithm. And the one thing which I'm not going to talk about, but is also again a very key thing, is that can I show that whatever you're predicting, this can be learned from data? What's your sample complexity? So again, people talk about these things, but today's talk I'm not going to talk. Yeah.
So, in the example you showed, you had this cache restriction. What other models are interesting in this online streaming sort of setting?
So actually, so the next 3 examples, I'm just going to run through 3 examples and just show you. But again, that's a great question. I don't have a clear answer. I don't have an answer which says that these are the big problems. I can show you some settings where people have attempted a few things, but this again rapidly growing area where people are discovering new ideas or new models. Also, it is partly driven by applications. What are you really doing here, right? So. Okay, so I want to pick 3 sample settings because they illustrate different issues, and I'll just run by what is known and what are some sample results here. Okay. I have 20 minutes. Okay, good. Okay, so let's look at scheduling first, and so again, all these 3 settings. You probably would have seen these kind of algorithms in your undergraduate class. So single machine, one machine, and jobs are arriving over time. Okay, so what do I mean by job? Job is like a job like that which has a few parameters. One is it comes at a certain time. So it has a release date. It comes at this time, and it tells you how much processing I need. Pj is its processing size, and so the entire input is going to look like this. Okay, so every job will have it will arrive at a certain time, and will say that I want this much amount of processing. Now you can schedule these jobs. You have to schedule these jobs on one single machine. You're allowed to be preemptive. So preemptive means that if that's your input, you can build a schedule like this. Okay, so jobs can be broken down, but there are only 2 restrictions. You cannot start a job before it has arrived. So all processing has to happen after its release date. And for each job, the total amount of processing that you do has to match its size, right? So you have to complete this job. So this is called, okay. So let me add one more notation. A flow time of a job, or what you can also call the waiting time of a job, is the gap between when it arrives and when it finishes. So there's a total amount of time it spends in the system. And your objective is to minimize the average or the total flow time or total waiting time of the jobs. Okay, so again, it's a classical problem which we teach in undergraduate courses. Another way of, one way of interpreting this objective function is that so flow time is, remember, measuring how much each job is waiting, but I can also break this sum in a different way. I can say that look at every time and see how many jobs are alive at that time, how many jobs are waiting at that time, and just sum over all time t. So both are same. So instead of counting like this, you're counting like this. Okay, so that's my objective function, right? And it is well known. We teach it that the standard offline algorithm, well, here it's an online algorithm, is shortest remaining processing time. So what is shortest remaining processing time? It says that look at all the jobs you have in your queue. Now what do you do next? So look at every job and see how much time it has remaining and prefer the job which has the least remaining time. So for example, at time 0, this is the only job, so you do this. At time 1, this job arrives. Now you realize that the yellow job has only 1 unit of demand left, whereas the green one has 2 units of demand left, so you prefer the yellow one. So, and then if a red one comes, then you realize that the green one is better, and so on. Okay, so this gives you optimal schedule, right? So it's even an online algorithm, right? Now, the question is, what if the sizes are not known? So in practice, again, you don't know these sizes, right? So what would you do now? Okay. So this is called non-clairvoyant scheduling. Again, it's a well-studied notion. And basically, the idea is that you get to know that a job has completed or its size only when it completes. So at some point, the job will say that, okay, I'm done now. So that's the time you will realize that, oh, this was the size of the job. Okay. And again, you cannot do much here, right? So basically, there are a bunch of results which show that the best approximation or comparative ratio that you can get here is log of n. N is the number of jobs. So that's fairly pessimistic. And this is including the setting if you allow randomization and all that. So, so the question now is, can we do better with some advice, right? So what are we going to predict here? Okay. So again, I want to show you a recent model which generated fair bit of subsequent work, which they called it a robust scheduling model. This was introduced by Yossi Azar, Stefano Leonardi, and Noam Toito in 21. And it says that when a job arrives, you get a prediction about its size. You don't get to see the actual size, you get a prediction about its size. Okay. And let me sort of have one parameter. So again, this prediction will not be accurate. If it is accurate, you're done. You'll just run the same algorithm with those predicted sizes. So let's say there is some error in these sizes. And I'm just going to measure mu as this sort of ratio. Okay, so think of mu as the distortion in the sizes. So the actual size divided by the predicted size. Okay, so this could be both above and less, so that's why I have those two parameters. But really think of mu as what's the error between the ratio between the actual size and the predicted size. Okay, so mu is some number which is bigger than 1. Okay, and the algorithm may not know mu or may know mu. So typically would assume that the algorithm doesn't even know what mu is. Okay, so what is known here? Known here is that they gave a mu square comparative algorithm, which was aware of mu. Subsequently, sort of we improved it to sort of big O of mu, and it's also known that you cannot do better than mu. Right? So without even knowledge of mu, you can give an algorithm which uses these predictions, and provided these predictions are correct. So note that what is the error here? Error is look at every job j. Look at the ratio, and it's a supremum, right? It's a max over all. So mu is a very strong guarantee, right? You could have argued about some other error metric, right, which is like average distortion or something like that. Average distortion would not do well, but perhaps some other metric would be better, right? This is a very strong metric. It says that even if you do error on one job, right, then this mu becomes very large. So again, this is not perhaps the best model here, but this is all we know, right? Okay, and it's also known that. So let me give you just maybe one slide about what's the intuition behind this algorithm, and then I'll go over. I want to go over all the other problems also. So again, SRPT is known, right? Remember, the shortest remaining processing time is known to be optimal, and then you can ask, just run this algorithm on the estimated sizes, right? Whatever those are. But the problem is SRPT is very sensitive to remaining size. Imagine that there are two jobs. For both, the predicted size is same, but it could happen that very tiny amount is left for a job, but the prediction says that only half the job is done. And so it's not difficult to construct examples where you can show that if you just follow SRPT, then this is very bad. Okay. So you can construct example as an exercise. It's not difficult. But let me suggest a different algorithm. More straightforward algorithm. Why do we even care about shortest remaining processing time? why not look at the initial size? Shortest job first, right? So forget about how much is remaining, just do shortest job first. Why is that a bad algorithm? Okay. And here is the reason why it is a bad algorithm. Imagine that you have a job of certain size, size 1, it arrives. When it is about to finish, another job of roughly the same size or maybe slightly smaller arrives. So if you're just going to look at the original sizes, shortest job first, you're going to say, oh, let's switch to the yellow job. Although very tiny amount of this was left. Okay? And the same event keeps on happening. Okay, so when your yellow job is about to finish, you say, oh, another job which is only slightly smaller arrives. Right? Let's think of each of them as having size 1. But the moment the yellow job arrives, you say, oh, let's forget about the yellow one. Sorry, the blue one arrives, you say, let's forget about the yellow one, let's do the blue one because it's smaller, right? So what's going to happen is that you're going to accumulate tiny amount of fractions of each of these jobs, and they'll just blow up your objective function. Remember, the total flow time was summing over all time of how many jobs you're waiting. You don't want to have too many jobs waiting at any time. But what's happening is that because you're following the shortest job first rule, you're not looking at how much is remaining, you keep on accumulating a lot of small jobs. And that's the reason why we don't follow shortest job first. Okay, so yes, some calculation here, but essentially this is what is happening. Okay, so the algorithm which sort of works, right, is the following. It's called, we call it balance, but essentially what it does is it balances these two sort of objectives. It says that you still want to prefer small jobs because now that I'm getting predictions, I have no idea how much is remaining. So I'm still going to use predictions, but I am going to avoid creating so many tiny jobs. That's something I want to avoid doing that. Okay, so it's some sort of algorithm which tries to balance these two aspects. Okay, so so let me sort of skip over the algorithm, but essentially says that these are jobs which I have not touched, these are jobs which I have touched, and I don't want to create too many of this. So I want to follow the shortest job, but I don't want to create too many jobs which are partially processed. So something like that. Okay, so let me just skip over this. Sorry. Let me go to the second one, which illustrates some, because the plan is to show you some of the various models that people are using about predictions. So let me show you the next one, which is load balancing. Okay. All right. So in load balancing, here's the setting. Each time a job arrives, okay, so you have multiple machines now. Okay, earlier I had single machine, now I have multiple machines. Each time a job arrives, it has a certain size, just like before. And now it also tells you that which are the machines I can go to. So for example, here it says that I can go on machine A or machine B. And you have to send it to one of the two machines. Okay. Then again, another job arrives, it says that I can go on any of the three machines, so you have to send it to one of the three machines. Okay, and this keeps on happening. So it just says A only, so then you have no choice, you have to send it to A only. Okay, so once you assign a job to a machine, that assignment is done, you cannot sort of change that assignment. And what is my objective? Your objective is to minimize the maximum load on a machine. So what does load mean? Load means that the total amount of processing that you have assigned to any machine. So you want to minimize the total load. Now again, if you knew the entire sequence, this is some sort of matching problem. You can imagine that this is a matching thing, right? Each jobs are on one side, machines on the other side, and you have to do this assignment, right? So it's some sort of matching problem. And so you can do well here. But the issue is that you don't know the future. So again, this online setting where knowledge of future would help. Now the natural algorithm again would be a greedy algorithm. It says that when a job arrives, right, look at how much each machine is loaded and just go to the least loaded one. Okay, so when this job arrives, it has two choices, A or C, and it goes to A. Now it is known that this algorithm is log m competitive, and you cannot do better. Okay, even if you use a randomization. So m is the number of machines. So again, it's fairly pessimistic, right? You cannot do much here. And so the question is, what would can predictions help here, and what would you predict here? And imagine that predicting for each job. Unlike earlier you were predicting the size of a job, right? I mean, what kind of prediction would help here? I already tell you the size, I already tell you the subset of machines on which it can go. What other predictions would help? Sorry? Yeah, so how many, so in all of these settings, you typically don't assume a bound on the sequence. You assume that the sequence is infinite. And the guarantee you want is that at every time, whatever is optimum. Yeah. So, okay, so I'll show you what is known here. Perhaps this is the only known result. Let me make a simplification which only sort of simplifies my algorithm. Let me assume that jobs can be broken, okay, and assigned fractionally. Okay. So suppose that was a job of certain size. I can break into two pieces which could be unequal and assign them to the, in some fraction to the two machines. Okay. So let's assume that they can be fractionally allocated. Of course, that was not the initial intention, but let's for the sake of argument assume that. Okay, so there's a class of algorithms which are called proportional allocation algorithms. They say the following. I'm going to maintain, in fact, I'm going to statically have some weights with each machine. So every machine has certain weight. Okay, and when a job arrives, you assign this job fractionally to those machines according to their weights. Okay, so suppose a job J arrives, it says that, well, how much fraction of this job goes to machine I? Well, look at the weight of that machine I divided by the total weight of all the machines on which I can go and multiply that by my size. Okay, so this is the amount of fraction, or this is the amount of job that goes to that machine. Okay, so these are called proportional allocation algorithms. Now, one very nice result in 2018, this was that for every input, there exist weights of these machines such that this allocation algorithm that I'm giving you is a 2 comparative algorithm. Or you can make that 2 as small as you want, but it has to be bigger than 1. It won't be 1 comparative, but essentially it says that this very simple proportional allocation algorithm, if you knew the entire input, you can design these weights very carefully. And once you use those weights, then this algorithm does just fine. Okay. So these are coming from duality sum of certain linear convex programs, but essentially it says that once you have these weights, you can just run your very simple algorithm. And so, sorry? These are fixed. They are not evolving over time. Right? The way the proof goes is, they start with some weights and then they say how you can modify them, but these are offline settings because you have to run several iterations. But the result is that there are these weights. And so those are what I predict. Okay, so the predictions are essentially those. So this is more abstract now, right? This is not something about the input. It's saying something about the solution, optimal solution. So you predict these weights, and again, let me say that eta is the worst possible ratio among these weights. Okay, and it's not hard to show that if you so eta is like the distortion. Look at the ratio of these weights. Worst possible ratio. If you just run your proportional allocation algorithm with these predicted weights, right, instead of the actual weights, you just incur that eta factor in your ratio. It's not hard to show. So this idea was actually introduced by Latanzi and others in 2020 paper, and they showed that eta can be improved to log eta actually. So the algorithm was as follows. I can show you the algorithm in one slide. The algorithm idea is that, again, in all of these settings, even though we don't know the optimal solution, you can assume that you know the value of the optimal solution, because you can typically within a power of 2. So these are standard techniques. So assume that we know what the optimal solution is, and assume that all the weights are powers of 2. So run your proportional allocation algorithm with some, with the actual predicted weights. Now suppose if these are correct, you will never get high load on any machine. Every machine you will be within twice of the optimal value. But suppose something goes wrong and some machine, the load becomes suddenly very high, 4 opt. It means that your weights were not correct. So in particular, it means that maybe the weight of this machine was not correct. So you just half that weight and keep running this. Okay, so that's the complete algorithm. All right. And again, the analysis is not difficult. Basically, what you show is that whenever you reduce the weight of a machine, it must be the case that whenever load becomes very high on a machine, it must be the case that your predicted weight was strictly larger than the weight of that machine. And since everything is a power of 2, dividing by 2 is okay, you still maintain this invariant, and this can only happen log beta. Okay, so some simple argument. So now if you were going to do integral assignment instead of fractional, you incur an extra log m cube factor. They also show that this log m is necessary. You can ask what happens to more general machine scheduling settings, what is called unrelated. So again, there are papers which discuss that. But the question is, there are many metrics known for load balancing. This I just showed you one. What happens in other settings? So again, this is a problem where we don't. 5. Okay, I'll show you the last one. Maybe not go over the algorithm. You can stop. So again, minimum spanning tree. We all study this in algorithms class, right? Greedy algorithm. So let me show you the online version of this problem. Okay. So so points, minimum spanning tree is what you give in a graph, and you want to build as minimum spanning tree. Here the problem is the online version is the following, that points are arriving over time. So imagine there is a metric space, and points arrive one by one. Each time a point arrives, it reveals the distance to all other points. Okay, and you want to maintain a spanning tree on the points that have arrived. Okay, so for example, initially V0 is there, you don't have to do anything. V1 arrives, you connect it to V0. V2 arrives, then you have to maintain a spanning tree containing all 3. So maybe you do that. V3 arrives and so on. Okay. So you want to maintain a spanning tree, and your question is you minimize the cost of your tree. Okay. And the greedy algorithm says that, well, it's a very natural algorithm. It says that when a point arrives, look at all the existing points and connect it to the closest one. Right? And essentially, for example, when V3 has arrived, V3 sees that look at all 3. Let me look at the closest one. Maybe it is V0. Let me connect to V0. V4 arrives. Maybe V4 says that let me connect to V1. That's the closest one. And this algorithm is known to be log n competitive. That is, its cost is at most log n times the cost if you had known the entire future. And it's known that you cannot do better, even if I allow you randomization. Okay. So again, the question is, what would prediction do here, right? How could it help? Okay. Okay, I don't want to show you this example. So this example essentially shows that, why is it log n, but it's not important. So this is a paper which appeared recently in 2021 SODA, which talks about, the prediction model. And I'm just going to show you for minimum spanning tree, but it also works for other network design problems. So the prediction here would be the input. Okay, the entire input which is going to come in the future. Okay, so it's a graph on n vertices. Not everybody will arrive, but it shows you what these are the points that it's going to show up. Okay, this is the prediction. Okay, the tricky part here is how do you define the error of this prediction? Okay, so this is the actual input which is going to appear. What do I mean by the error here? Right. So distance between these 2 point sets, and remember they are not of equal size. They may not be of equal size. So the way they define it is they say that look. Let's say I designate some points as outlier points. Okay, so these are outliers. Okay, these are way far off. Among the remaining green and the red points, I'm going to just build a min cost matching. Okay, so min cost matching is a natural thing, right? That this is the predicted point, this is the actual point. They're close to each other, but not quite there. So I would account for the cost as some matching cost. So it's a min cost matching provided you take out some outliers. But now, this outliers business is very tricky, right? I mean, I could designate everybody as an outlier, right? So, so the actual sort of notion of error is not a single number here now. So it's a pair of numbers. R comma delta says that suppose you're allowed to take away small r points as outliers. Small r could be green or red. Then what's the minimum matching cost? Okay. So if you're allowed to take away very few points as outlier, this is your matching cost. It's very high. If you're allowed to take away everybody's outlier, then maybe matching cost is much lower. So error now is not a single number, but it's an entire profile here. It's not really earth mover, right? Yeah, we can discuss more here. So, and what they showed is that there is an all-in algorithm whose cost is within delta is the actual matching cost plus log of number of outliers times opt. Okay, where you can plug in any r comma delta you want here. The algorithm doesn't need to know that r comma delta, right? So one algorithm which will work for all of these. Okay, and so for example, if you plug in R as n, you want everybody as an outlier, then of course delta is 0. And in that case, you get the log n times op, which is the offline, which is the known result. Okay. Okay. So I don't want to go over the so the algorithm essentially, maybe 1 minute on the algorithm. What's the algorithm? The algorithm is the following. I give myself some budget. Okay, this is the prediction. I give myself some budget, and this budget keeps on doubling in every iteration. So let me give you one iteration. What happens here? I give myself a budget, and I say that look, within this budget, build a tree which can cover as many of these predicted points as you can. Okay, so I give myself budget and build some sort of tree which lies within this budget B. Okay, so this is a tree which covers as many of the predicted points. Now, whenever somebody comes, when some point arrives, it may not be one of these green points. You just connect it to this tree, the closest point in this tree. Okay, so any point arrives, it gets connected to this tree. Till the cost of these connections, they themselves exceed this budget B. In which case, you double your budget and do the whole thing again. Okay, so that's the algorithm. Okay, and I don't want to go into the analysis, but again, it's not very difficult to do. But then they extend to other things. Now, of course, as you can see, this is a very weak sort of prediction model. Question would be, what are other prediction models? And these things only work for sort of single connectivity settings. What about when you have higher connectivity requirements? Suppose I want 2 connectivity or 3 connectivity. Not much is known here. We don't have great algorithmic results. We don't have great prediction models here. There's another line of work which looks at why are we just saying one prediction? What if I have a host of ML models, each of them is giving me one prediction, so multiple predictions. So again, not much is understood. There's one paper we have on set cover, but I don't want to go over it. But then, as such, not much is known here. Okay, so typically most of these results incur an extra factor log m, where m is the number of predictions. So if you're getting multiple predictions, you incur a corresponding loss, which is not so nice, right? You would think that using more predictions should be somehow more useful. And the reason why log m is appearing is that all these examples, what they're doing is they're saying that there's one guy who's giving the correct answer, rest of them are trying to confuse you, right? But that's not how it's supposed to work, right? I mean, so somewhere there is something wrong with the model itself. So what's the right sort of cost-benefit analysis here, where using more prediction should be somehow more useful, right? So as I said, this is an actively evolving area. This is a page which Alexander and Nicole maintain. And this kind of tracks, the publications in this area, and you can see it started very slowly around 1819, and it's growing steadily. And the page is very nice because you can filter by kind of problems you want to look at, and it will show you all the problems which are there in this area of algorithmic predictions. Most of these papers appear in NeurIPS, ICML, but you can see SODA, ITCS, there are iCalc papers also. So, but that's the current status. Okay, so let me conclude. Online algorithms can have pessimistic ratio, but predictions hopefully can lead to significant improvement. And there are many research directions here, new problems, new settings. Again, the model is not set in stone, so you can think about interesting prediction models and how to model error. Multiple predictions, of course, we don't understand very well. And the thing that I didn't touch about, but is also very important, is how do you learn these predictions? What is your sample complexity? You need to show that these predictions can be learned over time also. Sorry?
The upcoming tax site aesthetic, like what if the tax is dynamic?
Oh, so no. So okay, so good. So we of course don't know the incoming input, right? But when we want to analyze this algorithm, we say that suppose this is the input. How will my algorithm perform then? So of course I have to try over all possible inputs, but because I'm fixing that input, right? So that already is somehow sort of, so suppose I show you an algorithm, right? You will try to see okay, so if I give it an input like this and build the input like this will be the worst possible input for this algorithm, right? So in that sense, you are dynamically designing that input, but the input as such is static, right? Because I can always assume that, because I have looked at the algorithm and I am designing the worst possible input for the algorithm. So because I'm looking at all possible scenarios, right? There's no need for me to tweak the input as the algorithm sort of.
But in real workload, like uh, dynamic instruction counts,
Dynamic.
instruction count. So in this case, like we can't predict.
Right. So no, that's a valid. I mean, yeah. So the question really is, whatever parameters that I'm trying to predict, they should be learnable over time. Right? Yeah, that's definitely an assumption.
Quick question. So, my initiation into online learning is through regret minimization algorithms. What's the connection of this competitive ratio to regret? Do these algorithms minimize regret?
Connection of the competitive ratios to
Like you have algorithms which give reasonable competitive ratio, but if I take these algorithms, do they
oh, so the
still
idea would be
minimize
that
regret?
you get better competitive ratio, right? So, so if I have something which has a bad competitive ratio, the hope would be that with combining predictions, I can improve on the competitive ratio.
No. If my optimality notion is regret, it's like the predictions done by the best. It's like if you have experts, some expert gives the best predictions, and you take your algorithms and take a difference like regret. We call it regret, right?
Yeah.
So how do these algorithms relate?
Compare
to regret?
with those.
Yeah, like will these algorithms which work
So
with
you're talking about online learning kind of settings.
Yes, online learning.
So online learning, typically the assumption is that there's a distribution from which the input is coming.
Yeah, but you can
But
do,
here I'm not really tying myself to a distribution as such, right?
but you have the non-stochastic versions also.
Yeah. So I'm not assuming. Yeah, that's the only.
Yeah.
So yeah. That's
Any-
Okay, let's, in the interest of time, take other questions offline. We have a coffee break after this talk, so let's thank. Sir. We have a small comment as well.
Yes, please come here, Krishna. So we have a small token of appreciation.
Thank you so much.
So everyone, as we prepare for our next talk, it seems we actually have an overflow. So we have an overflow room where some people are sitting. I'd like to bring them in this room. We were not really expecting that this overflow room will be used, but there are about 10 people there. There are a few empty seats here. I will just bring them in, and also we've arranged a few extra chairs. So we can just put the chairs on the aisle or something. It will be nice if they can be part of the main room. So if your bag or something is on a chair, I request you to bring it down and just allow me 5 minutes. Let's just bring them in. Okay?
Okay.
Thanks.
Sure. जनता है ये तो, अरे ये अपने मन से क्यों इधर जा रहा है? क्या कर रहा है? हो अपने मन से जा रहा था ना? This is not my. मैंने अपडेट कर दिया था. मेरा 10 मिनट तो ऐसे ही खा गया स्पीकर. मैं क्लॉक करूँगा 60 मिनट्स. मैं घर ही ले आऊँ. वो तू ये है क्या? तू क्या ये है? चेयर है. Oh, I see. Okay. मैंने ना जो लास्ट स्लाइड है तो स्टॉक हटा दिया था जानबूझ के.
though we arranged this overflow room, I didn't expect that we'd use it. I'm a bit sad that people are sitting there, but I'm also happy that there's so many students who come. Moving this may be hard. Krishna, feel on the screwdriver. ठीक है, otherwise I guess the overflow will also right. And maybe after the coffee break we can share after. Okay, let's. Is it better? Okay, cool. All right, everyone. So let's begin the next session. So I invite Akanksha to introduce our next speaker. Use the mic.
So it is my absolute pleasure to introduce Saket Swaram, who is a professor at Institute of Mathematical Sciences here in Chennai and also at University of Bergen, Norway. So he is a leading expert in the field of theoretical computer science, and his research mainly focuses on graph algorithms, parameterized algorithms, kernelization, and a lot other things like computational geometry. He is a recipient of Shanti Swarup Bhatnagar Prize from 2021 and ACM India Early Career Research Award. His work has been supported by both ERC Starting Grant and Consolidator Grant. He is an elected fellow of EATCS, Academia Europea, and the Indian Academy of Sciences. And I have known Saket for more than a decade now. So I think he is the reason I got into parameterized algorithm, he and Neil Dhara. And over to you, Saket. He is also my PhD advisor. Boss.
So he's the guy we should blame for you.
Yes.
Thanks a lot, Akansha, for your introduction. So, so today I'll tell you something about random walks and how to do FPT approximation. But I'll just give you a very simple example, keep it very simple till the last slide, which might be slightly this. So let me first start by congratulating Sweta for putting up this wonderful Center for Theoretical Computer Science. Hopefully we all can make use of and prove more theorems in local Chennai. So thank you, Sweta, for this. And with this, so let me tell you what problem I'm going to talk about. So throughout the talk, I'm just going to talk about this problem and design some 10 algorithms for this problem, giving you different set of things throughout. So the best way to explain anything, at least in parameterized algorithms, or for that matter, even in approximation algorithm, is you give this vertex cover example, right? So what is this vertex cover? So you are given an undirected graph G, your natural number K, and you are basically asking, can I delete K vertices so that what is left is independent set or does not have any edge? Or in other words, I want to find small set of vertices such that every edge at least intersects my selected vertices. So for example, here's my graph and you want to find vertex cover of size at most 3. So for example, if you look at this V1, V5, V3, then every edge has at least one endpoint in the selected set. So this is what will be my vertex cover. Okay? Any problem with the problem? So we all are there. Okay, good. So now let me give you the first FPT algorithm for vertex cover. I'm not going to define what it means by FPT and this. Yes? I will tell you. Don't worry. Right? I mean, I will define everything for you. It's just patience. Okay? I'm not going to use any big hammer, so, okay? So here's my algorithm, whatever that means. So what my algorithm does? Now, if you have an edge, you have to pick one of the endpoints. So I recursively try to find a solution which either picks u and try to find a solution of size k minus 1, drops the budget k minus 1, or from the other endpoint of my edge v and tries to recursively try to solve the problem on the budget k minus 1. So that's my algorithm. Okay, so this is a simple algorithm to solve my vertex cover. And of course, I have some base case which says if k is less than 0, then return no, or if some edge is empty, some such base cases. But basically, if you have an edge and you're looking to find a solution that contains at least one of the endpoint, so you try to find solution containing one and see if that leads to a solution. You try to find a solution leading to other and try to find a solution. If either of them succeeds, you succeed, else you fail. Okay? This is what is called FPT algorithm. Okay? Now, what's the running time of this algorithm? So let's notice what happened to this algorithm. So I started with G and the budget K. In this search tree, I deleted U because I decided to put this vertex into my solution, and I'm looking to find a solution of size k minus 1, right, with budget k minus 1, similarly in the other side. Okay? So what is the depth of this tree? Depth of this tree is like k minus 1, and how many children each branch has? 2 children. So how many nodes this search tree has? Huh? That's it. So that's all that it is, and each node I'm going to spend some polynomial amount of time. So the total amount of time that I spend on finding this algorithm is like 2 power k some polynomial in n. Okay? So analysis is very simple. Every vertex cover S must contain at least one of endpoint, hence one of the 2 branches is always correct. Okay? So this gives a depth k search tree. You could have also written a recurrence, right? Why I showed you this, you could have written a recurrence that, look, I'm trying to solve a problem with budget k, and to solve that I'm trying to solve 2 problems with budget k minus 1. So that's this, and this polynomial, you know how to solve this recurrence. So from now onwards, I'm just going to forget this polynomial factor in this, just for the clarity. Okay? So this is what is called vertex coverage FPT. So if you can get an algorithm with this k running like this, it's called FPT. Nothing more to know, nothing less to know. Anything else? Any question? No. Now, here's a simple principle for vertex cover that people have explored for last 3 decades is that, well, what is the meaning? There's another way of thinking of this. Look at any vertex and its neighbors. If you decide not to pick this vertex into the solution, what it means? Who will take care of these edges? This edge, this edge, or this edge. You better have to pick all these 3 vertices, right? And that is what is shown here. In the first one, I try to take this vertex into my solution. In the other one, I try to discard this vertex and take its neighbors, and we're done with it. Okay? So, but now let's look at what algorithm does this. Yes? No, that's a question we have to check, decide. You might be able to say there is no vertex cover of size at most k. For example, the example that I draw, if you try to find a vertex cover of size 2, you can say no. Or for example, if you're looking for a vertex cover of size 2 and you find a matching of size 3, what can you say? No, right? Because if you have matching of size 3, you have to pick one from each of them. So there are ways, it may not be always a yes instance. So it's like a decision question where your answer is either yes or no. Right. Yes. And that's what we're going to do the next. Okay? So here's my algorithm. Right? Imagine that if a graph has maximum degree 1, do you need to branch or do anything? What is this? It's like a matching edges and some isolated vertex. Solve it in polytime. Even if the degree would have been at most 2, you could have solved this problem in polytime because it is like cycles or paths. But what about if degree would have been 3? It's NP hard. So then you already have reached the hard case. But even like I do not want to go to 2 like this. So even if the degree is 2, I branch as he suggested. So I pick up a vertex with degree at least 2. And you are right, the best heuristic would have been to find a vertex with highest degree. For example, we know how to solve this problem with minimum degree 2 in polynomial time. Then ideal would have been to put degree v at least 3 and then I branch. But the reason I did not put it because I do not know how to analyze it yet in the settings that I need further. So I will leave it for now. Okay? So this is my algorithm. So now my algorithm is g comma k. My budget drops by k minus 1. In the other, budget drops by as much as degree, but at least 2, because the vertex that I'm branching on has degree at least 2. Now, if you write the recurrence, does it remind you of some recurrence? Fibonacci recurrence, right? So this solves to 1.618, right? So from 2 power k, we immediately went to 1.618 to the power k. So these are the 2 algorithms that you need to remember throughout this talk, and that's it, okay? Now, what is known for vertex cover? So let's know what is known for vertex cover. So people have designed an algorithm. I think if Nari is not in the room, then he's one of the co-author who has designed an algorithm for vertex cover who runs in time 1.25284 to the power k, okay, whatever. And vertex cover admits a 2-factor approximation algorithm in polynomial time. I will tell you in a minute. And we also know there's a hardness barrier that if you assume unique game conjecture, then you cannot do 2 minus epsilon. And if you believe p not equal to np, then I think root 2 or some such lower bound we still know. So the point what I'm trying to make you is that this is what we have known for vertex cover in FPT time in 3 decades, and doesn't look like now with people are pushing very hard and you like breaking this 5 itself looks very difficult, hoping that someday we will achieve 1.19 algorithm looks even very difficult to do with the current set of methods. And we have such barrier in polynomial time. So what is the next question to ask? So in polynomial time, we have actually know what factor 2 approximation is best possible. So we just ask, is it possible that we can get 1 plus epsilon approximate solution? And I'm happy to run FPT algorithm, but you should beat this 1.25. So if I'm allowing you to get 1.1 approximation, maybe you should be 1.2. But if I'm allowing you 1.75, the running time should be different from 1 or 1.1 or 1.5 or 1.7. How do we do this? Okay. So can approximation bias speed? Okay. Okay. So now I'll give you an FPT approximation for vertex cover. But when I say via, I want to introduce the definition. So what I mean by, so if you do classical polynomial time, the notion of approximation is very clear, right? There's a notion of minimum, and you are fighting against that minimum. So 2 times op, 3 times op, log n op, it's very clear. But in the world where we are going to measure the running time with respect to some number, I need to define what I mean by FPT approximation or this. And this is what it means. So I gave you this number k, okay? If you give me a solution of size alpha times k, I don't ask you any question. But when you say no, you are correctly concluding that the reason I failed is because there is no vertex cover of size at most k. The minimum vertex cover has size at least k. But when it says it returns you alpha times k, it doesn't mean that it has a vertex cover of size at most k. It could be that it has a vertex cover of size 2k and I returned you a vertex cover of size 2k. Or it has a vertex cover of size 3k by 2 and I returned you a vertex cover of size 2k. But when it returns no, you are correctly able to conclude that it is a no instance for vertex cover. But when it returns an answer, you are happy, you take this approximate solution and you don't ask question, as we do in the classical polynomial time outcome. Okay? So this is what I mean by FPT approximation for vertex cover. And you can do this for any minimization problem. There's nothing about vertex cover. You either returns a solution of size at most alpha k, or you just say that optimum is more than the number you are trying to. And now why it is important, let me give you one very good example. Imagine a maximization problem. I want to maximize number of vertex disjoint cycles. It's an NP-hard problem. Now, at least k, and I put k equal to 2 or k equal to 3, but the number of vertex disjoint cycle could be as much as n by 3. So now, in polynomial time, we are trying to find too many vertex disjoint cycles, right? So this is why this k play a role. I don't care that you give me this or give me that. I'm okay. Number of vertex disjoint cycle could be too many, but with respect to this k, if you are happily giving me something, I'm happy because that is how much computational running time I'm giving you or I'm providing you. Okay? So that is why we have to make this distinction. Maximization problems becomes slightly more harder to phrase, so we'll leave that discussion for later. But for minimization problem, it is fairly clean. I give you a number k and factor alpha, which is an approximation. Either return me a solution of this, or you correctly conclude that the minimum size or optimum is more than the threshold you have provided. Okay? Any question on the definition? Yes?
So not allowing
Meaning? No, yeah, just larger than k, not alpha k. Okay, so what is a simple polynomial time 2 approximation algorithm for vertex cover? You find a maximal matching and you return both endpoints of this maximal matching. And you know that this is 2 times cardinality of M is 2 times the minimum vertex cover. You are happy because every matching you must contain at least one vertex in the vertex cover. Correct? So this is a factor 2 approximation. I'm going to modify this algorithm to give you an FPT approximation. How? It's very simple. Let M be a maximal matching. I'm going to give you 3 by 2 approximation. So what I do is that I find this maximal matching. I pick up any k by 2 edge of this, right, and take both endpoints of this. Okay. If the graph had a vertex cover of size k, whatever may be that vertex cover, which we do not see, must have picked one vertex from each of these k by 2 matching edges. So what is the remaining budget on G2? It should be k minus k by 2, right? Here, for this k by 2, to get this in polynomial time, to drop my optimum by k by 2, I have paid k by 2 times 2, so that's k. And on the remaining, I can run the best known FPT algorithm and give you a 3k by 2 approximation, right? So that's all this algorithm does, right? So it picks up this any k by 2 matching edges. And why it is important? Because this allows me to argue that opt has it reduced in the reduced graph. Okay? Okay, so this is what happens, right? So 2 into k by 2, those matching edges, factor 2 approximation. And on this, I'm going to run my exact FPT algorithm. So approximation factor is guaranteed to be 3 by 2 times k. But what is the running time of this algorithm? Well, running time is you are running your expensive part, but on the budget k by 2. So if the best known algorithm is this, now it is k by 2, so this is the running time. So I'm getting a 1.5 approximation, but my running time is much, much faster than this. Okay? Now, there is no magic about 3k by 2. I could have done this for any 1 plus epsilon approximation because all I need to do is I choose epsilon k by 2 matching edges, right? Then I pay epsilon k here and my parameter drops here by 1 minus epsilon by k, right? So my running time will be how much? 1 minus epsilon by 2 times k, right? So this is my running time. So I can get any, so if you want to get closer to k, you are paying more and more running time. You want to get closer to 2, you are paying less and less running time, right? So just by playing on this, I have got this nice curve of running time. Okay? Any question? It could give you a good advantage. So people have designed very convoluted algorithm in last 15 years, but yeah. So for example, oh, let's find a triangle, 2 will be go into the solution. So let's take all the 3. You could do that. At least for D heating set, for 3 heating set, people have done this kind of recursive. For vertex cover, I have more seen that people are analyzing local, and whenever they have opportunity to say that, oh, at least X will go and I have X plus 1 or X plus 2, pick all of them and paint this. So this is something which I have seen quite much more people doing it than recursive. But for 3 heating set, people have done recursive. But what I will tell you is that we can do way more faster than these things by interpreting these algorithms slightly differently. Okay. So what is the takeaway? So this is a curve that you are starting to get. Okay. So people up until now we used to design this algorithm, but now with this approximation, we are able to get plethora of these algorithms with different ratios. Okay. So now I will tell you. So now this was the starting of the kind of results people have studied, what is known in the literature, and what we are trying to provide in the current article. Okay? So it has witnessed a lot of growth in last decades, and people have proved, especially in the lower bound size, people have proved some amazing set of results by relating it to hardness of approximation in polynomial time, proving some variants of PCP kind of theorems for parameterized complexity, and proving, but this is still, people have not got the kind of results they still want, and this is a very active area, and people are working. So that is beyond that I can tell you. So what I'm going to tell you is what was known if you had C power k poly n algorithm, which in parameterized complexity we have plenty of them, can we get such kind of curve for those kind of problems, right? So we know how to solve them exactly. Can I get a curve for these problems by, say, now I allow approximation, give me slightly better running time. So this kind of time ratio trade-offs, okay? And this is what was known in the literature before us, is that everything was like more like a vertex cover or cousin of a vertex cover, except for feedback vertex set, which, so what I'm going to tell you is the ideas which we flushed out from this paper, this idea to complete totality in this article, okay? So except this, everything was about cousins and brothers of the heating set, okay? So the milestone in this area was by paper by Kluik and Shashanani in Fox 2020, who introduced randomized branching into this area of parameterized approximation, and they developed machinery to how to analyze these two variable probabilistic recurrences, and they applied it to this vertex cover 3 heating set, but still very simple kind of probabilistic recurrences. Okay, so more than the algorithm there, I would say their main contribution was that you can bring this machinery from convex optimization or information theory, type theory, and use this to solve some of these beautiful recurrences. Okay. So the natural question was that, I mean, how far we can push beyond this D approximation, like which problems truly admit this kind of ratio, can we systemize them, can we automatize them, that look, if you have a branching algorithm which satisfies property A, B, C, D, then you have such a ratio algorithm. So that was the goal to design, is that if I have a problem for which we have classical branching algorithm that satisfies some properties, then I can automate it to design such time ratio trade-off algorithm, okay? Because up until now, everything was completely by ad hoc. You pick a problem, you try to do like problem by problem, find some structure and do something, okay? So our contribution is that what we do is we give you a formalized language for randomized branching rules and a meta algorithm that takes that if you have these branching rules, then this is the way we can automate, and that gives us many, many more examples than what we knew in the literature, okay? So here are some examples, like some feedback vertex said, all cycles, LP, matroid, this, that, everything can get, okay? Okay, so now, so what is our conceptual contribution is that now we are able to develop maths for, developing maths was that we had to go beyond whatever the framework of these people, but coming up with like the complex random walks, which are, some of them are quite counterintuitive, that even those can be used to design good algorithms, and I will tell you what I mean by counterintuitive, okay? And measures, people always use these measures which were like K, solution size, but now we can analyze measures which are substantially different than just solution size, okay? So all of these will look very, what is that called? Not very concrete, but I will make each of these lines concrete in the next few lectures. Okay, so now I'm going to take up my same example of vertex cover, and I'm going to give you approximation, but via random walks. So what will a random walk for me will mean? You are standing on a real line or integer line, standing at some place. With some probability you can go left, with some probability you can go right, and with some probability you can just stay put, okay? And that's it. And what does random walk tries to analyze? That if I'm at some state and I want to reach to some final state in certain number of states, what is the probability that I can reach from some start state to some final state in these many steps? And that is all that the whole area of random walks try to understand, try to analyze. So what we are trying to do now is to take all these branching algorithms and try to map them to understanding some these kind of questions. So that is the goal. Our goal is to take most of these branching algorithms and tie them up of understanding some movement from some current state to some final state in some number of steps, and that's it. Okay. Okay, so let's do one such example, and it's funny. So this is the algorithm we had, right? We picked an edge. So now I randomize this process. Okay, I do not go into both parts of my algorithm. I randomly pick which of these endpoints I must pick into my solution. I delete from the graph and I recursively solve. What is the running time of this algorithm? It's polynomial because I'm just doing k times of this. So what should be its success rate? Success ratio. If it would have been polynomial success, then it would have been like RP or these kind of algorithms. But here, because it is a polynomial time algorithm for an NP-hard problem, this is also called one-sided probabilistic polynomial time, OPPs. Okay. So what is a success? So success is you fix a vertex cover S of size k, and at each round you are choosing an edge which has at least one endpoint in S. It could have both, and so probability that you will hit that endpoint is with half, because I'm just doing a coin toss. If it comes head, I pick U. If it comes tail, I pick V. That's it. So probability of success is at least half to the power V. And that's it. So this is my algorithm, which we did before. Now I'm just doing this in a randomized way. Now what does it provide us? So now I can think of this algorithm as a random walk view. Okay, what is this? I start at K. So what I'm going to tell, up until now, how many vertices of S still need to be discovered, right? So that's my state. Every time if I do correctly, then I move from K to K minus 1 because I have discovered one vertices of S, so I have moved. So basically, if you want to understand the probability of reaching 0 in a bounded number of steps, and that's it. So now let's ask this. If I ask K steps, what is the probability? 3K by 2 steps, what is the probability? 2K steps, what is the probability? Okay? So now what is the probability here? Notice that if you make a mistake, it's a vertex cover. So whatever is remaining still remains to vertex cover. So you stay put, you never go left or right, because vertex cover, you don't go left. Vertex cover does not increase if you made a mistake. It can only decrease or you can stay put. So this random walk stay puts with probability at most half, and it goes forward with probability at least half. Why? Because both endpoint could be in the solution. So in that case, you would have moved with probability 1, right? So that is why it is at least half and it is at most half. Okay? Okay. So this is all that it is. So this is my random walk. And now, and I want to understand, to reach 0 in exactly K step, the walk must decrease in every step. And this is what we got half to the power K. So we have got our classical vertex cover algorithm in this random walk way. Okay? Let's run this for 2K steps now. Now I'm running this algorithm for 2K steps. It means all you care about that at least K times you should move left, and other K times you can just stay put. So what is a probability of starting from here, spend some time drinking tea, maybe you felt hungry, you like sleep, right? So this is like, I call it like, this we study the tortoise and hare. So like in this process, hare always wins, tortoise can still go slow, okay? So what is this? So let X be the number of steps that move the walk towards 0 among the first 2K steps. So you can think of this that you are doing 2K coin tosses. How many times you will, what is the probability you will get K heads among this 2K? Because every time head happens, you go left, right? So this is nothing but binomial. This is binomial n comma p, where n is 2K, number of coin tosses, and p is half. It just happens to be half. So that's your factor 2 approximation algorithm running in polynomial time. Okay? So if I did 3K by 2 steps, it's the same thing. Now, but number of coin tosses that I'm doing is 3K by 2. So if you do this maths, you get this number. Okay? So the probability of success is like this So if you want to boost the success probability to constant, you do just normal independent amplification 1 by this. So it is 1.0887 to the power k, right? So which is much, much better than what we got from that matching idea. Okay? But the caveat is that was a deterministic algorithm, this is a randomized algorithm, and we all don't know how to de-randomize this random walks based algorithm yet. Okay? So the random walk view already improves the running time. Okay? So this is already very encouraging that if we are able to move these branching algorithms to some first randomized good algorithms, understand their behavior as walk on some plane or this and that, we can take advantage of that to design good algorithms. Okay, so that's a key step. Okay, so that was so what I mean by monotone walk. So I call a walk monotone, yet if every step, either you stay put or you go towards your target. So vertex cover walk was so far monotone. Okay. And we also saw this algorithm, remember, where what we tried to do, we did not branch on an edge, we branched on a vertex. In one side we put this vertex, in the other case you picked up two vertices of this, right? But now notice, still this walk is monotone, because by adding vertices to your vertex cover, you are never going to make vertex cover bigger, but there is a jump, right? It's possible that if you are branching on a vertex cover of size, like neighbor of size d, and if you correctly decide it, you can jump to I minus d, right? So that's all that is happening. So with if I do the same with probability half and half, I'm not going to get. So let's decide what probability we should jump. So I go to the next step with probability p. I do this jump step with probability 1 minus p. Okay, starting at k, and I'm asking the same set of questions, right? In this jumped random walk, what is the probability that I can go from starting state to final state in some number of steps, and that's it.
You have to be careful, right? Like earlier, the number of steps told you the end, like 3k by 2 by 2.
Correct.
If you pick the degree, like the cost.
Right. So we'll get into troubles. We'll soothe, and that is where all the magic starts. Okay. So, okay, wait. Okay, right. So this walk is still monotone in the definition we came, but it is no longer unit step. Okay. So let's first analyze this. Let's just get the classical branching algorithm, which was 1.618. How do you set this probability, right? So you can set phi equal to 1 plus root phi by 2. It's not that I came up with this number magically. You just put this p, 1 minus p, you try to boost, like try to see what is the best, and you will get this number, right? And what is 1 by phi? So 1 minus p is nothing but 1 by phi square, okay? Now since every jump decreases state by at least 2, this choice will be enough to prove the success probability is at least phi minus k. And now let me give you proof why the success probability is phi minus k. Okay. So how many A steps you take? Suppose you go 1 A steps and you take B many jump steps. So what you know, A plus 2B is at most k, because every time you take a jump state, the parameter drops by 2. Okay. So what is the probability of following this path? So 1 by phi to the power A, 1 by phi square to the power b, which is 1 by phi a plus 2 power b, which is 1 power phi power k, and that's it. Right? So one run succeeds with probability phi to the power minus k. Okay? So far, so good. Okay? Anything here? So if you notice, we got this 1.618 to the power k when we were doing this branching. You actually can recover the same thing. It is basically, if you think of this, you are just sampling the leaf of this search tree, and that's it. So it's just basically a way to sample a leaf of this search tree, and that's it. And that is why you get this. So if you had very complex branching algorithm, you can set up these probabilities in a way that you will recover the same number. Okay? Okay, so this is all that I said. Now let's go back to what Siddharth was saying. But what are the set of difficulties that this random walk faces? In the exact algorithm, successful path always needs to move this side. But if I allow you to stay, right? If I allow you to stay, but what is the meaning of stay, right? So notice, now you should have picked up V, that's a right move, but you decided to pick all of this n of V. Now imagine that this degree was like k by 2 and you were hoping to get 1.1 approximation. You deleted k by 2 vertices from the graph already and your optimum did not decrease. So even if you, after this move, if you are running correctly, you are still going to give me 3k by 2 approximation. 1.1 is not possible. So this move is not correct. Okay? So previous mistakes were unit cost. But now single bad jump can kill your algorithm. Okay? So we need much more refined and controlled process than this. Okay? So let me design a different branching algorithm which achieves 1.618 and we will implement that. Right. And that's what I'm going to do now. Okay? So I'm going to modify my branching algorithm, which, okay? So rather than degree, I fix two vertices and I say in the one branch I'm going to pick this, in the other branch I'm going to pick these two vertices into my solution. And why this is correct? Like, look at S any vertex covered. If V is in S, then the first branch is compatible. In the second branch, V is not in solution, then all the neighbors go into the solution. So in particular, these two vertices go into the solution. This is perfectly fine. If you analyze this algorithm, this is also going to give to 1.618 to the power k. But what happens now is, let's look at the choices now we make. So suppose this is what optimum choices are and this is what our choices are. So if optimum also picks V, V also pick V, then op decreases by 1, error is 0. But optimum picks V and B picked XY, op did not drop, but error has increased by +2. And similarly you can do here. But if we would have branched on that degree, my error term would have been that much and then we would not have been able to control. So now with this slightly modified algorithm, we are able to capture that a wrong choice only contribute at most 2 to the additive error. Okay, any question? Okay, now coming to him, I cannot just count number of times I make a mistake because different mistakes cost different, right? So if I was planning to pick V and I picked XY, my cost was 2. I was planning to pick XY, I picked V, my cost is 1, right? So now, before just knowing number of bad moves was good enough for me to analyze an algorithm, but now I not only need to know number of bad moves, but how this bad move affects my error calculation, I also need to keep track of those two. Okay? So now you see the difficulty. So you start to analyze more and more complex algorithm and you start to get more and more complex things that you need to keep track during your algorithm. Okay? Okay. So suppose I wanted to ask for 3 by 2 approximation, then what I'm asking, you output a vertex cover of size at most 3 by 2k, given that g comma kj is. That is what I'm interested in. That if this random walk is there, right? I don't know, now I don't even know to think about number of steps because number of steps doesn't correspond to the size of the solution. I can run small number of steps and still have much more error. I can run for long number of times. So I am not able to keep track of just formulate even these questions properly in this, oh, I want to go from starting point to this in these many steps. I'm not able to formulate these questions also properly. Right? Okay. So I know for sure that this is better than 5 to the power minus k. Why? Because everything that goes always left, left, left is counted here, but there are many more paths that are there. So how to account? So I definitely know intuitively that success probability is at least this much, but how much it is? Okay. So Now to do this, state has now two coordinates. K tracks the remaining parameter and B tracks the remaining additive error budget. Okay. Okay. So now our walk is no longer one-dimensional because now it is a walk over Z square, and I am not able to analyze these two-dimensional random walks because I do not have clear picture of what I mean by number of steps, what I mean the number of paths, right? So rather than doing this, we study equivalent probabilistic recurrence that describe the behavior of this walk. Okay. So now we will have PBK, which denotes the worst case success probability when K is the remaining parameter, B is the remaining additive error budget. Okay. So what you write this is what you will write. Okay. Now notice, so let me explain to you this recurrence. If V is in my solution, right, and you got head, right, then what happens? Your budget for the error has not changed. Your optimum has changed with probability 1/5. But I could have also made a mistake, right? But if I had made a mistake, I would have picked up both of its neighbor into my solution. So amount of error I allow you in your algorithm has decreased by 2. So the budget of error has decreased by 2, but your opt has not decreased. Okay? Or I could be in the other case where V is not in opt, then I should have picking both of its neighbor, but I decide to pick V into my solution. My budget of error has decreased, but my opt has not decreased with this probability. And in the other, I am not putting to the error. So B remains the same, and this decreases to K minus 2. Right? So this is how set up this recurrence. Okay. Any question on this recurrence? So I have to take minimum of these two because I really do not know what is the reality of the algorithm. We tried, but it doesn't give us number. It is much more useful to prove convergence and this kind of thing. But we needed how fast it converges, and we need quantitative bound for that. And that became slightly more difficult. Okay. So analyzing the behavior of such recurrence was already far from straightforward, and this is what this paper in Kulik and Shashnani did to some extent. Okay. And now, so there are some two counterintuitive. So second parameter may increase rather than decrease. Okay. So what I mean, up until now, we have always seen that we always go left or we stand. But there are lots of algorithms where if we do, I can actually increase my solution. Or not the solution, but the measure by which we are trying to analyze the algorithm. It can increase. And I will give you a concrete example. And that is very counterintuitive, that why will such algorithms will go and even give you good running time. Okay? So that's a counterintuitive. Now, as you notice that for vertex cover, it was easy that if I go a vertex and if the choice for approximation is bad, then we were found of EG way, just pick two of them. But for many problems, you cannot find this. So it's like if you go there, it's like a kill state. So you can imagine that you're going from India to Pakistan, like not in a proper way, and there are lots of, what is that called? Mines are kept, and you still have, but there's still a lot of paths. Right? This is what my kill state does, right? That if you reach there, you're dead. You cannot recover from there, right? So we wanted to have, because for many problems, we did not find any simple way to make this approximation easier. But we said if you go there, like you are dead. Even then there are enough paths around that gives you good probability of success, and you can get very good running time for this algorithm. So we try to include a kill state. It's like if you go there, you can imagine that there's an integer line and there are some points where the black you cannot, so you have to jump over it. But still there are enough paths. Okay? Okay, so let me go towards the general model now. So, okay. So how we encode a branching rule? So now, to check the behavior of these algorithms, we have two matrices, what is called additive error incurred while lifting a solution back, and T is how does this drop change it. So now we keep track of these two things by these two matrices. And I'll give you an example what the entries of these two matrices will be. Okay. So for example, look at this branching algorithm where you picked V and where you picked U1 and U2. Okay. Now what are these row corresponds to? Row corresponds to V being in opt, right? So look at the, if V is in opt and you decided correctly, then the error is 0. But if you decided wrongly, then the error is 2. Similarly, in the other branch, if you decided that both should be in the solution, but you decide to pick V, error is 1 and this. And this shows change in measure. Okay. So all we are trying to tell is that what I mean by this. So my algorithm is that I don't care about what your algorithms are, what your branching algorithm is. You give me B and T matrices, I know how to optimize this. Okay. So that is where all the things. So what will I ask from the user? I don't know what algorithm you're designing, for which problem you're designing, I absolutely don't care. You give me your B and T matrices, and then I know to design an algorithm which will optimize corresponding to this. Okay? So that is how we try to encode the generality of all these problems into these matrices. Okay? Any question? You think of this way, right? What is my algorithm doing? So rows are how rows think of, so we had this matrix, right? Which rows were what optimum does and the columns were what does algorithm does. So suppose that first row is I also decide to pick V into the solution and algorithm also, opt also decides to V into solution, then the error is 0. But here I decide to put the correct choice should have been V, but your algorithm picks both the endpoints, then your error is 2. Okay.
So when you say designing algorithm, what probability do you choose those?
What? No, you give me. You will have to give me. You will have to give me B and T. Okay. I will come up with my probabilities which will optimize everything. Like I will come up with a distribution given B and T which will optimize these things. Okay. So you will just give me B and T. You will not give me the distribution. What? Yeah, you can branch like 1 and 3. Like we could do 1 and 3 because we know how to do 1 and 2. Then this like 1 and 3 doesn't matter. So you're right. So we could do those things. Okay. Right. So it just tells you that if you had 10 branching rules, then you will have that many rows and columns, right? Rows because columns. Rows are basically what are the real states of possible these algorithms are, and columns what are the choices this algorithms makes. Okay, and for each rule you will have different matrices. So each rule only tells us if this rule, this and B and T matrix. If different branching rule, there will be different B. So you give me all this B and T matrices, and then I will optimize it based on that. Okay, so what I mean by monotone case now in this definition. If all the entry of my measure matrix is at least 0, then I will call this walk monotone. So now let me give you one example of non-monotone walk. Okay. So this is something which people have studied quite a lot in parameterized complexity. It's still a vertex cover problem, but how do we analyze its running time is slightly different. So let me first define the measure by which we want to have a running time. So what is a running time? So lambda g is the cost of, if you write the classical LP, linear programming for vertex cover, its cost. Now we know that any integer linear programming has value at least linear programming, LP. So I'm saying my measure is opt minus the lambda g. This is why it is also called above guarantee, because the value of LP provides a natural lower bound on the size of the solution. Okay. So you are still finding a vertex cover, but you are not allowed to measure the running time as a function of k, but as a function of this parameter, right? And that is what FPT is all about. So you have a same problem. You can come up with a different measures, different way to analyze, and different analysis could give you different algorithm. And why it was interesting for all of us, because we know it's a FPT parameterized by solution size. Can we show it's FPT parameterized something even smaller, right? So if the way you show hardness, so you're not happy with NP hard on general graph, then you try to find it's an NP hard on planar graph of maximum degree 5. So in the same spirit, we try to do here. If it is FPT, what is the limit by which we can show FPT? If it is hard, what is the largest parameter for which we can show it's hard? Okay, so this is what it is. Now, I'll give you a situation. Okay, so here the standard branching rules, processing rules. LP has all unique half optimum solution, and the graph has minimum degree at least 3. So you can do all this pre-processing and get here. And after that, algorithm is exactly the same that what I told you. You find a vertex, pick up its degree 2. In one branch, you delete. In other branch, you do U1, U2, and that's it. And that's an algorithm which gives you an algorithm with respect to this parameter. So you can analyze the same algorithm with this new measure, but all you care about is that you do pre-processing to get to these places. And this is very standard it has known in approximation world for decades that it has all half unique solution. Okay. Now, let's look at a wrong case. Suppose V is in optimum, but we decide to take U1, U2. Now, opt doesn't change it, but your lambda can only decrease by 1. Because everybody had half, you deleted 2 vertices, so lambda will just drop by half. But let's compute mu of G2. 2 times opt of G2 minus lambda of G2. If you do this math, you will get mu G plus 2. So now what happened? I started with a graph which was less complex. I have gone to a graph which is more complex. Okay. So we thought for a long time that these kind of walks cannot be analyzed. But if you see Soning's, he goes left, right, wherever he goes, and he's able to analyze. So if we have a boundary that I don't care where you go, you take a round turn and come back. You will still reach home, right? It's just that more far you go, more you will have to pay. But less far you go, you can still come back. You don't have to just stay put. You can go left, right. Ultimately, if you go here, as many times this, if we are able to calculate this, that's your approximation factor. And that's it. Okay? So if you write down the matrix for this, this becomes now negative because my measure for the graph has changed. Like it has increased, it has not decreased. So these are like non-monotone matrices. Okay? So a wrong move may increase the measure and the walk is no longer monotone. This we didn't know how to analyze for a long, long time. And this maths makes life way more harder because a lot of theorems in convex optimization that we use for monotone is no more applicable. So you have to put some upper bound and this and that. It works, but it was a long tour. It was not, we couldn't use direct off the shore lemmas from the book. So we had to prove our own lemmas for these things. So that's the basic difficulty. I mean, computationally we knew that it works by coding. So we knew that it works, but we didn't have maths for 1.5 years to tell people that this works. So that is where all the magic, like numerically we knew that this works because you code, you put this and you can check. But nobody is going, this is a heuristic. We had to do maths. Okay. So if you write down these states, now it can look like all kind of places. All kind of places these paths can go, but that's perfectly happy because I can write my recurrences. I can still write my recurrences. Now notice, what are these tells us? It was, oh, I am correct. If I'm correct, so this is like gamma 1. This is what, I do not know this probability. This is what, you give me the matrix, I will write this recurrence, gamma 1. This is my distribution, which my algorithm will optimize. So here if you notice, it just tells that, well, my measure here has decreased by 1. But look at here, it has increased by plus 2. But my error has decreased by 2. Similarly here. So, and you have some boundary condition. So This is the most general form of, one general form of recurrency that we were able to solve. And also, let me tell you, we do not know how to solve these things when b is any arbitrary number. If b is some function of alpha times measure, only then we are able to analyze it, which is good enough for our purposes, but if someone needs to do something different, he or she will have to do something very different. Okay, so in last 5 minutes, let me. Yes. Yeah, it allows us to do so. So there's one problem for which we had to do this, otherwise we could not show anything. But for some problem we couldn't do, and that is why we need to put kill. Like if you increase so much, like there's absolutely no way you can come back. So those are kill states. Because we couldn't bound, once you go to this stage, we couldn't bound any approximation factor in any reasonable way. Okay? Okay, so what is our general framework? So what we define is oracle subset problems. So there are some pre-processing rules, those should be exact. We believe that this can be made lossy, but we do not know yet. Branching rules of constant arity means like you branch in 3, 4, 10 ways, not in infinite ways. Measure mu that tracks progress, and you can have an oracle access when needed. And why did we need oracle access? Because now that we are working with LP and this and that, sometimes we need to know whether it is feasible, what is its solution, these kind of things. So that is what I mean by oracle access when needed. Okay? So this is what I mean by oracle subset problems. Equipped with exact pre-processing rules, they should not be lossy for now. Branching rules of constant arity, and measure mu that tracks progress. Okay? And what the framework needs, you have to give me the problem and the measure, the pre-processing and the branching rules, and the local signature matrices B and T for each branching. That's all that we need from you. And almost all the classical branching algorithms that we are aware of can be encoded in this uniform language. And what we show is that if you have oracle subset problem which admits C power mu deterministic algorithm and has a proper set of branching rules, like this kind of branching rules that I told you, like B, T matrices, I can write all this, then for every target approximation factor, turns these branching rules into randomized FPT approximation algorithm, and branching probability are chosen like automatically. You don't have to give me, this is a job of us, and they are optimized to give you best running time by the framework. Okay, and so you get all these problems, and this is what was known in polynomial time approximation and what we are able to get in this table. Okay, so let me conclude in next 1 or 2 slides. So what we did, we revisited vertex cover as running example for FPT and gave you FPT approximation, interpreted branching algorithms through the lens of random walks, monotone to non-monotone, developed a general framework turning suitable branching rules into this time approximation ratios. And what remains open? I don't know whether it can be applied to other problems like directed feedback vertex head, planar vertex cover, I don't know. Can be extended to even more richer works, but more importantly, which at least I have, it has like at least bothered me a lot, can we get deterministic version of these algorithms? We have absolutely no single deterministic algorithm for either of these problems yet. So that remains in my head one of the biggest open question. And thank you. Any question?
Okay, so since we are slightly out of time, maybe we can take the questions offline. Thank
Okay.
you, Saket, for the talk and presentation.
Thank you. Thank you.
So everyone, it's time for the coffee break. We're going into it 10 minutes late. Let's come back 5 minutes late. So at 11:30
Thank you, Shweta. Good morning, everyone. So it's my pleasure to introduce Pascal Weil as our next speaker. Just a quick, brief bio. Pascal studied in France and the US. He joined CNRS in 1987 and has worked in CNRS labs since in Paris, Bordeaux, Chennai, and now again in Paris. He worked on automata theory, and more specifically on the connections between automata, logic, and algebra, as you can see in the title of the talk. He has recently been interested in automata for models of distributed computation, also in the title of the talk, and in algorithmic problems which arise in the theory of infinite groups. Pascal, as many of you may know, is a regular visitor to India and especially to Chennai. Since 2007, he has been the deputy director of RELAX, an Indo-French lab joint between CNRS, CMI, and IMSC, and largely they relax. It's my pleasure to introduce Pascal, especially since he was also recently our first speaker of the year at the Chennai Combinatorics Colloquium. So it's my second time this year introducing him. And over to you, Pascal.
Thank you very much. I don't think I need this. Yep. Thank you very much for the introduction. Thank you for the invitation. I'm very honored to participate in this inauguration, this first meeting of this new center. I think it's a great idea to have such centers anywhere, but notably here in India, in Chennai. So, yeah, it's my pleasure. Thank you very much, Shweta, for the invitation, and everyone else for the organization. As Nishad mentioned, I have many affiliations. The French affiliations usually are difficult to read, and when you have two, it's even more difficult. So this LIPN is a Paris North Informatics Lab. So you just shuffle the letters and get it right. And it's a lab under CNRS and Paris North University. But I'm also, as Nishad mentioned, and together with Madhav and Mukund here, running a CNRS, CMI, Math Science joint lab, Indo-French, called RELAX. And RELAX is not at all what you think it is. It means Research Lab in Computer Science. The CS becomes an X, so it's very serious. And also it includes mathematics these days, so it's even more ambitious than just RELAX. Good. Thank you again. So let me. Oh yes, there's a clock here. Very good. Let me get started. Automata, logic, algebra, and models of distributed systems. As Nishad mentioned, these have been things that I've been working on over the, unfortunately, too many years. And so let me start from the start. So I'm going to talk about automata, logic, and algebra, how they relate to one another in the framework of languages of finite words, so something extremely familiar to most people who've taken a theory of computation course, and then, so classical results, and then I'll move to distributed settings, and there's many things that can be said in that direction, but I will be concentrating on results obtained fairly recently together with Bharat Atsul and two of his students, Shantanu Kulkarni and Saptarshi Sharkar, at IIT Bombay, and Paul Gastin and myself. Good. So, finite state automata, everybody knew at least what they are. Here's an example. So these are little pictures. Now, sometimes they say it's a 5-tuple, but it's not at all. It's a little picture. It's a graph with decorations. And here's another example. So what they do is you say, well, okay, what are the words here? The alphabet is 0, 1. What are the words that take you from, say, from state 1 to state 2? Oh, I think I have this thing. Yes, woo, yeah. State 1 to state 2. It's okay. So you see that this accepts. This first example, starting in 1 and ending in 2, accepts exactly the words that have at least one in them. And the second example, if you take state 1 to be initial and terminal, what does it do? Well, it excludes going to 3. and you go to 3 when you have 2 consecutive ones. Okay, so words that do not have 2 consecutive ones. So if you were into enumeration systems, you'd say, oh, these are the representations of numbers in the Fibonacci basis. Okay, so regular languages. Good. Now you can also describe words, characterize words, describe languages, using formulas, logical formulas. So you use predicates A, one for each, for each letter A there's a special predicate, I wrote it in boldface, and binary predicates less than, and the variables are interpreted as positions in the word. So if you have a formula like this, what does it say? It says there is a position I, such that for every position j, position I carries letter A, and it is not the case that I is less than j. So, unless I'm mistaken, this means that I must be the last position. Okay, so it characterizes exactly that language. Capital A for me is I'm French, I'm not American, so alphabet starts with an A. It's called A, not sigma. I don't know why it's called sigma elsewhere, but I'll stick to A. Language A star A, all the words that end with A, is characterized by this small formula. And there's a theorem, very old theorem, Buchy 1960, that says that the language is regular if and only if it is defined by a monadic second order formula. It's MSO definable. What does monadic second order mean? We don't need to get into the details, but it means that you write formulas like this with these predicates that I mentioned. You're allowed first order quantification, as I used here in the example, but you're also allowed to quantify over sets of variables. So you can say there exists a set of variable capital X, such that blah, 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 and then you can say, well, this individual variable is in X or is not in X. Good. So that's a logical characterization. It's completely equivalent. It's intellectually very nice. It's not necessarily super practical in terms of either readability, because these formulas are difficult to read, or algorithmically. So you're not going to write your specifications in MSO, probably not. And there's an algebraic characterization, which is something quite natural, I think. You have your automaton, has a state set, Q, that's a finite set, and each word W defines a map from Q to Q. I'm assuming that my automaton is complete, so you read your word W from any given state, you reach some other state. That's a map from Q to Q. And maps from Q to Q can be composed, so they form a monoid, which I wrote Q to the power Q, all maps from Q to Q. And so now, from my automaton, I now have a map that associates with each word a map from Q to Q, and it's compositional, it's a morphism. Okay? And what is the language as accepted by my automaton? It's exactly those words whose transition from Q to Q takes the initial state to some final state. So it's the inverse image of P, where P is the set of maps, Q to Q, that take the initial state to a final state. And you make that an abstract definition. You take any morphism from A star into a finite monoid, into any monoid you want, if you want. And you say that L is accepted by that morphism psi if there exists a subset P of the monoid such that your language L is inverse image of P. Okay, and with what I give you, you have all the elements to figure out that a language is regular if and only if it's accepted by a morphism into a finite monoid. Good. So these are the sort of triangle of interactions. Automata, which is sort of combinatorial or maybe sort of algorithmic, I don't know, algebra, and logic that all match perfectly in the case of finite words. And so when you start your career, as I did, into this magical world where everything matches, then you're very unhappy when you step out of finite words and discover that things don't match more generally. And why is it interesting? Actually, you have this matching between these three different things, and So you can refine, you can ask now, you have more tools to talk about your languages. If you have only automata, what are you going to do? You're going to say, oh, I don't know, I mean, it has 7 states, or it has an even number of states. I mean, there's not much you can say about the automaton. Regular expressions, you can, which I didn't mention, but which is also a classical companion to all these, you can say some things, like there is no second order quantification, for instance. So it's first, no, sorry, there is no star used in the expression, so it's what's called star free. But much more than that, it's not so convenient. But algebra gives you a lot of things, and logic also. So for instance, you could ask, well, okay, so I said, Buchy says use MSO to describe all regular languages, why not stick with FO, first order? Is that sufficient? Maybe it is. Okay, and another question, no, so, okay, not another question yet. The answer, no, it is not sufficient. But how do you prove this? How do you prove that there is no first order? How do you prove that the non-existence of something? You need a little bit of structure behind, otherwise it's not going to work. And a companion question is, well, I give you some regular language. Is it first order definable? Some are. My answer no says some aren't. How do you know? How do you find out? And there's a theorem, two theorems actually, but combined, this is the statement from the 60s or late 60s. And let's say L is, a language L is first order definable if and only if it is star free. That's what I mentioned earlier about regular expressions. Something that's nice to write, but doesn't tell you how to decide. And if and only if it is accepted by an aperiodic monoid. What is an aperiodic monoid? It's one in which, for some n, an n being you can take to be the cardinality of the monoid, so it's something you can check algorithmically, satisfies x to the n plus 1 equals to the x to the n. Okay, so this last property is decidable, and that makes the other two decidable, which was really not obvious, and as far as I know, there is no other proof of the decidability of first order definability or star freeness than this one that goes through the monoid characterization. Of course, you can massage a monoid characterization into something about automata, because you go, I'm not going to get into the details here, but you go to the syntactic monoid of a minimal automaton of your language that you can do algorithmically. And the syntactic monoid it's enough to see that the transition monoid of that guy is aperiodic. And so you can retranslate algebraic properties into the minimal automaton, but fundamentally it's because you have something algebraic behind. And there's many more refinements that you can take. Some of these words may be familiar to you, like piecewise testable languages, locally testable languages. I'm not going to get into the details. Sigma 1, which would be some refinement of first order, or FO2 definability. FO2 means you take first order formulas, but you allow yourself the usage only of 2 variable names, which you can reuse through scopes of quantification, but you allow yourself only 2. If you allow 3, you can do anything that FO can do. But 2 you cannot. And what do you get? Well, something smaller. And there's a super interesting class. But we're not going to get there today. But the fact is that all these classes, membership in all these classes is definable, and is definable through the algebraic characterization. So this is where we are, I think. Yes, one more thing. That's almost the end of my advertisement page on algebra. And another result, which will play a role later in the talk, is this. So let me define first what's the cascade product of 2 automata. So you have 2 automata, A and B, and you run an input word W into the first, A, and you output the computation of A on input W. So what do I mean by that? You output you output a copy of your word W, but now you've decorated every letter with the state of A that you were in reading it. Okay, so that's what I call the computation of A. It says, on input W, letter after letter, I've been in this state and that state and that state of A. And now you take that word, which I wrote chi A of W, to be an input for a second automaton B. Okay, so it's like what do you call that? A series composition of automata, a cascade. It would be better if it was vertical for the cascade. And right, so that's an operational automata, produces a new automaton, more complicated. This can be translated in algebraic terms. It's called a Ritz product of monoids, but it doesn't matter. The thing is that there are some basic, simple automata that you can use, and Krohn and Rhodes in 1962 proved that every regular language is accepted by a cascade product, not of just two, but a lengthy cascade product, of group automata and reset automata. What's a group automaton? A group automaton is one in which every letter is a permutation of all of the state set. So, yeah, injective or deterministic and codeterministic. And a reset is something like this. In a reset automaton, there are three kinds of letters. Letters like C that do nothing. Letters that like A that take, wherever you are, they take you to state 1, and letters B, wherever you are, they take you to state 2. That's a reset automaton. Okay, and Krohn and Rhodes said, incidentally, there was their PhD thesis, and it was at MIT, and it was not very long, I think less than 100 pages, and it was their joint PhD thesis. I don't know that it has happened before or after a single piece of work be two PhD theses. Anyway, at the time it was considered quite a breakthrough, and right, so they say anything you can do with an automaton, you can actually do by this cascade composition of very simple automata. Good. So now, let's go to distributed models. As I hinted before, a lot of the things I mentioned collapse or are not yet elucidated. Like what's the proper algebraic framework, for instance, for distributed models. Anyway, there's lots of different distributed models. So what I mean here is that we have a distributed system, so there's a set of individual processes, okay, and each of them is their own little finite state machine. Each of them has their own alphabet of actions and finite state behavior, okay, and they communicate. And there's many ways in which this could be defined. I will concentrate on one single way, which is called Mazurkiewicz traces. I'll try to explain how that works. So, in fact, the way it works is that some letters are shared between different processes. So if those letters happen, then they happen on the different processes that they belong to at the same time. So they synchronize, these actions synchronize these different processes. Okay? So formally, my alphabet A is equipped with a location map that says, okay, so my letter A, every little letter A, has a set of locations, a set of processes. Okay? And the combination of this location map and the set A is what I call the distributed alphabet. And you understand that if two letters, two actions, do not require the same resource, do not act on the same resources, or have disjoint locations, then they're called independent. There's no way that they know that that the other one is happening or not. So they can commute in some sense. They're not ordered neither causally nor temporally. And the trace monoid is the quotient of the free monoid by the relation that says, okay, so independent letters commute. Okay, so it means that there's a natural way of taking a word on A and leading to its trace, which is its equivalence class for this thing. And conversely, but I'll get back to what traces really look like. And conversely, if you take a trace, you can take its inverse image. It's the set of all the linearizations of that trace. So here's, I think, the right way, or a right way of looking at traces. So in this example, we have 4 processes. So the set P of processes 1, 2, 3, 4. Okay, and you can see each letter. So the letters that we have, A1, A2, A3, A4, B, C, D, E, you can see on the picture what their location map is, right? A1, A2, A1 is located only on process 1. B is located on process 3 and 4. E is located on process 1 and 4. Okay? And right. And so now you have this word. Maybe the word is A1, A1, B, C, D, A3, E, A2, B, C, A4. I'm sort of going left to right on my picture. Why not? That's a word. But now I can commute some of the things, some of the letters, if they are independent. For instance, this B has no connection with C or with A1, so it could have been pushed there, but not further, because it will bump into the D that is also on process 3. On process, 3. And the E that is here could, or this A2 if you want, could move here and no further, but the B could not move to the left of the E. Okay? So when you take a word, if you think about it, and maybe it's like also playing like Tetris, it's like a horizontal Tetris. You put I don't know who remembers what Tetris games looks like, but you know, you put your letters as they come in your word and push them as far left as you can, and you'll get this picture, and then you can also shift them around. Okay, so a trace for me is a poset like this, where every processor 1, 2, 3, 4 corresponds to a linear order, but the whole thing is not a linear order. Okay. Very good. And right, so you can even ask things, you know, like, okay, so when I'm here, this process E9, this event E9, this is a B there, I'm on process 3 and 4. What do I know that happens on process 2? Well, I am not aware of this A2. What else is on process 2? This E5, this D, event 5. Am I aware of it? Well, yes, because as being here on process 3, I'm aware that there was an A3 before me, which is aware that there was a D before it. Okay? So I have no information about the A2 or the C up there, but I do know certain things. Okay? So there's this causality, this poset that I'm describing. Okay. Now, a trace language is said to be regular if the set of its linearizations, all the words that lead to these traces, is regular. Is there a, so now that definition, the word regular is out there, is there an automaton model? Yes, there is. Zelonka introduced asynchronous automata that implement this distributed structure on the distributed alphabet. So what do these automata look like? Very difficult to draw, so I did not attempt. But as I mentioned at the beginning, each process has its own finite state control. So for each process I, there is a set of states, Qi, and the global states are the tuples of states for all the processes. Okay, and when I look, so just bit of vocabulary here. When I look at a single letter here, and here I failed and I put a sigma instead of a capital A. So some contamination is there. When you look at a single letter A, let me call QA the tuples of states of the processes that intervene in letter A, or that A is located at. Okay, so not all states are in lock of A, but this restricted tuples, not global states, but just restricted. This is what I call an A state. Okay, and now in a Zielonka, in an asynchronous automaton, each letter A acts. It acts on the global states, on the tuple of all states, but its action depends only on the A states it sees, and it will transform only those. So the action of A, the transition delta A, will turn Q sub A, these tuples of states in location that belong to A, into another tuple, okay? And it will leave all the other components of the global states for processes I that do not belong to log A, it will leave them unchanged. Okay? So this really tries to take into consideration this notion of this distributed computation. What A sees as an action is only the location of A, these processes that are in its lock A, and it is not aware, so it does not depend on, and has no action on the other processes. Okay, and then you choose a global initial state, global accepting states, and Zielonka proved in 1987 that a trace language is regular if and only if it is accepted by such an automaton. And it's a very difficult, very technical theorem that has led to a lot of literature in the ensuing years, with people trying to understand what was behind this this construction, how to understand the interaction between the distributed structure and the automaton, and in particular Madhavan and Mihin Sohoni had a very interesting work that also was followed by a lot of literature on so-called gossip automaton. Yes?
Is there a central notion of a synchronous automaton?
So the synchronous would dilute or forget in fact, about the distributed structure. It would say, okay, so I am forcing my B here to be before the C, or the contrary, or the opposite. So it would forget the asynchronicity means nothing more than the fact that I don't choose a representation. I choose the poset representation, not the linearization. So I don't choose whether B is before C or not. And so if you take this definition and you say, okay, so I have a trace language which is regular. So behind it there is this the language of words of linearizations, which is regular. There's an automaton for this. This automaton has some particular properties that you can fix, that you can check. If A and B are independent, two letters are independent, that means that they commute. So in your automaton, at least in the minimal automaton, if you can go from this state to that state by A and then B to another state, you can do, maybe by a different route, but from the same place to the same place, using BA. So this is called a diamond property, diamond automaton. That would be maybe the synchronous version of those. But it could be that AB is equal to BA, or label this pass from the same place to the same place for other reasons than independence. Just because in that particular language, those letters have the same context, the same syntactic context. And so you lose something by going synchronous. The asynchronous is the way to account for the distributed structure of the distributed structure, and hopefully to account for the properties of the system we are modeling. Does this answer the question?
I asked because of the distributed algorithms. We take synchronous and asynchronous. Of course, asynchronous is completely events based, right? And synchronous gives you a time step, right? Kind of
right.
Thing. And that allows us to say make a lot simpler algorithms, or certain things you can do in synchronous far more easily than you can do in asynchronous. That in that way.
Right. So. In some sense, it's the same situation. You know, it depends what you want to do with your language. If you want to say is it regular or not, you don't need this Zilonka distributed asynchronous automata. The automata that I described on this language of linearizations is enough. But if you want to, if you want to go in the direction of finer questions, is it first order definable? Is it this? Is it that? Maybe it's going to help. Maybe you're not going to be blocked because you are forgetting about the distributed system. You've fixed, you've rigidified your a priori nonlinear order. And if you're going to implement it, like you have a specification from some logic, and you know the distributed structure of your system, it is what it is. The processes are what they are, and you want an implementation on that distributed system, you cannot ignore that structure, at least in an abstract way. So this is really, the question of what you need to use to solve a particular algorithmic, for instance, or implementation problem, that depends on the problem, and we're sort of like one step back from that question, trying to remain true to the distributed architecture. Is there a logical characterization? So yes, but it's a little disappointing. So I think you also have monadic second order logic characterization, and with the sort of same, the analogous result proved by Wolfgang Thomas in the late 80s. And there is a maybe more interesting, exciting at the time, 1992 result that says, and first order definable is also equivalent to star free. So that's good. That's good. But so then you would say, okay, so now tell me something more about, I don't know, sigma 1 or b sigma 2 or some other refinements of the first order hierarchy, for instance. Or tell me about algebra. Is there an interesting algebraic structure to represent, to account for these trace languages? So in some sense, yes, going synchronous. You have your regular language of linearizations, and it has a monoid. It has a syntactic monoid, and you can certainly characterize the fact. This is in the definition of a regular language being a trace language being regular by the fact that it's the syntactic monoid of all the linearizations is finite, because this is almost a definition, but it doesn't. It works for first order. It tells you, okay, so there is a decidable algebra-based characterization of first order. But when you go to smaller or different subclasses, nothing very interesting has happened, or extremely complicated. There were some results by Kuflight now that were very complicated and sort of super topical. I mean, there was like an ad hoc sort of solution. So the algebra part is still, in my view, missing. And also, there is no simple and meaningful way to go from an MSO formula to an asynchronous automaton. That means to an implementation. And so there comes into the picture some other logic, not MSO, but propositional dynamic logic. That's something that started in the late 70s by Fisher and Ladner's introducing this framework to reason about programs. And then there was an interpretation of the words, which turned out to be equivalent to regularity, to MSO. And then with my co-authors, we introduced, maybe Paul Gastner had introduced it before, local propositional dynamic logic. I'll explain why local, but meant for traces. So, if you've seen propositional dynamic logic before, then you know that there are several sorts of formulas, and there are so-called event formulas and path formulas. So here are the what is it called, the syntax, the semantic, whatever, that thing that says how you build those formulas. So the event formulas, as their name indicate, are going to be evaluated at specific events, so points, positions in my trace. And either they say, well, this is letter A, or this is Boolean combination, or I can do a path formula from my position, and at the end of that path formula, some pre-existing formula phi will hold. And then the path formulas they will be evaluated at a pair of events. Let's say there's a path from this event to that event, and in my trace. And the path can be just staying put and testing whether a certain phi event formula is true. Or it can be, let me go backwards. Let me first assume that I am an I event, I'm on process I, and let me go backwards some amount of time on that process I, so that's why it's called local. And then check whether phi holds. Or let me go forward, or let me take disjunction, concatenation, and star of such properties. So there's some kind of regular language of paths that's going on here. Now, how do you interpret that on a trace? I could put a very long and very boring and unreadable slide, but I borrowed a slide from Paul, which has lots of colors. I don't know how to do this myself. And so here is a trace. Okay, all the dots are events, or extended dots, events that are on several different locations, different processes. And the little phi's, phi 1, 2, 3, 4, 5, 6, are properties that may or may not hold at a given event. Okay, and I'm looking at this formula, this event formula, phi, and you can see that phi there's these angle brackets from here to there, and then phi 6. So, and then in between, in here, I have a path formula. Okay, the path. So, how do I interpret this? I am saying that this phi holds here, of this black dot, black event, if there is a path, if I can follow a path that satisfies, that's described here, to a place where phi 6 holds. Okay? And what does my path say? It says, first you go along process 3 to the right, making sure that phi 1 holds all the time. Okay? So that assumes that I am already on process 3. This is the case in my black dot. I go forward, making sure that phi 1 holds all the time, and at some point, I test for phi 2. Okay, so maybe phi 1 holds here and here and here, I don't care. At some point I decide to stop, so it's non-deterministic in its definition here, and I test for phi 2. And phi 2 happens to be on process 2 and 3. And now I go further to the right, but on process 2, I'm allowed to do that because I've reached this guy, making sure that phi 3 always holds, and at some point I stop and test phi 4. And I'm here. And then because phi 4 is both this event rather is both a 1 and 2 event, I can certainly do this, go backwards on process 1, making sure phi 5 holds. And then I reach a place where phi 6 holds, this phi 6 here, so I'm happy. Okay. So this is how you, I think with that example you can like figure out any, the semantic of any event formula. And good. So, right. So this is local PDL. And then there's a restriction if I don't use the forward thing. It's called local past PDL for obvious reasons. Okay. So why is it interesting for traces? It's because it really builds in the notion that you are looking at process I events at some given point. Your movements along the trace are totally event. They're local to a particular event, to a particular process. Okay, and a theorem that we proved took us a lot of time. There was several different papers. It's rather quite technical. Is that this local pass PDL is expressively complete for regular trace languages, which means precisely that the language is regular, trace language is regular, if and only if it can be defined by a local pass PDL formula. Okay, so this is good, but a little gratuitous at this point. So what we're trying to do then is like use these formulas to actually synthesize, so out of the specification given in local pass PDL logic, synthesize a synchronous automaton in a way that's structured. So the way we did this was again using this notion of cascade product, but this time of asynchronous automaton. So it's exactly the same idea. You have an asynchronous automaton A, you feed it a trace T, you output the computation of T by A, which means that you've decorated your trace A with the state. Now the states are rather complicated, right? The global state, they're tuples, but it doesn't matter. You've decorated your trace T by the states you're in, and then you fed that as input to another automaton. Okay, and you started with a distributed, your trace is over a distributed alphabet A, or a tilde with the location. So now the output here is labeled by pairs of a letter and a state, and you need to say what is the distribution, but you just take the distribution on the first component. Okay, and again you're going to use basic bricks, and the basic bricks are the same as forwards, permutation automata and two-stage reset automata, but I want to see them as asynchronous automata over my given distribution, which I don't choose. So I'm going to take localized versions, which means they happen only on one particular process, on process I. The two states are on process I, and on every other process there's a single state, and when every letter is the identity, so nothing happens of any meaning or significance on the other states, on the other processes. So localized group automata, localized two-state. And with the same authors, or a subset of the same authors, we proved this statement, so that any regular trace language can be realized by a cascade of asynchronous automata. Then they're missing a bit of it. In fact, of these particular localized group automata and localized two-state reset.
So is the converse true? If anything can be realized as a
yes, because if you compose cascade automata, you get another automata, and so something that's regular. That is the easier part of the theorem. Okay, so right. How much time do I have? Difficult question. 15. Oof, too much. So let me give you an idea of how this works and how it connects to my logical apparatus and why it's interesting. And the last part, I don't know, you're going to be the judge of whether it's interesting. But so the statement I gave is to say every regular trace language can be accepted by a cascade of basic localized simple automata. But really the proof is out of a locally passed PDL formula, I will manufacture my cascade product. So I'm going to use the natural structure of a formula, the recursive structure of a formula, to construct, to prove my theorem, but also to have my cascade product appear in front of me. So the key point in this proof is to compute for each event formula an asynchronous automaton, which, preferably one that is a cascade product of basic localized automata, an asynchronous automaton which on input a trace T will output the same trace decorated by the truth value of phi. You know, at this, see my trace that I push in is a bunch of events, and at each event I want to see which letter is there on the trace and whether phi holds or not in that at that event. So you want to do this by structural induction, so you start by the simplest formulas. If phi is just a letter, well, that's very easy. The letter is on a given process, and you can manage that. Boolean combinations are not a problem as usual. And I'm not going to do all the cases. It gets terribly technical and somewhat difficult for some of them. But I'll give you a simple enough case here where your formula phi is of the form: go back on process I for a bit and verify whether that psi holds. And we assume that by induction we have already an asynchronous automaton that computes the truth values for psi. And is in the required form, meaning a cascade product of the small localized automata. And now let B be this guy. So I'm going to do a cascade of my A psi, which comes from previous induction steps, followed by this guy. This guy, first, before I explain the different decorations, it's a reset automata. It's a two-stage reset. Okay, a particular case where there's all letters either keep you in one place, or they take you to state 2. And what are my inputs? A trace, yes, but a trace on which distributed alphabet? On the alphabet that says, on the alphabet that has a letter and a truth value, true or false. Okay? And what does this say? It says, as long as I read any letter with false, I output false. At some point, in fact, the first time, whatever, but it's distributed, so there's no first time. But when I read a truth value, so when I read any letter with a truth value true, I change state and I still output false. And then I output true whatever I read. Okay? So if I combine my two things, I'm pushing my trace T through A psi, and it comes out a trace that's decorated by true and false, the same trace but with trues and false. And here I'm saying that when I'm pushing it, then on it's localized at process I will output false as long as I see false for psi. And when psi becomes true, I'll still output false once, and then I'll output true. So that means that I've been going now I'm seeing that I'm going maybe next plus and not previous, but you would do the right left reverse. Okay, so it's like saying, okay, so I'm going forward with false, 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 and then as soon as I see true, I change state, so I'm going at least one step to the right, and then I'm staying there true. So that corresponds to the semantics of this, actually not prev I, but next I plus. Okay, and so the rest of the proof is of that nature, only it gets quite complicated for this case, with the case where you are saying, oh, and by event I can actually follow a path that itself has a complicated structure. And that part actually uses the classical chronoids, so the words, finite monoid chronoids. And okay, that's the proof, not the proof, but an idea about the proof of this result, that every local pass-PDL formula yields a cascade product of simple localized asynchronous automata. So what we've been doing as a conclusion is talking about trace languages, which maybe not everyone was familiar with here, but that's a very standard model for distributed computation. And we've been revisiting Zielonka's equivalence between regularity and asynchronous automata. And this revisiting has been done through the lens of this particular logic, which has been proved to be expressively complete. The proof that it was expressively complete did not use Zielonka automata, it used the definition of regularity. And then this expressively complete logic I've used to prove a Chronoids type theorem, so cascade decomposition for trace languages, for regular trace languages, in terms of cascade products of simple localized asynchronous automata. So it's actually interesting that this distributed system can be seen as a cascade of localized, single process localized simple automata, but of course it's not always the same local, so the whole distributed structure still holds. And this provides a new, I think, more structured proof of Zielonka's theorem, because one byproduct is that indeed every regular trace language is accepted by some Zielonka automaton, but we even give more information, particularly one that's a cascade product, etc. And that's it.
Pardon my total ignorance on these things. Are there any connections to temporal logic also on these kind of things?
Yes. Yes. So, Madhavan will correct me if I say stupid things, but temporal logic, so in words it's like linear temporal logic, but now it's not so linear anymore. Can be expressed in terms of this propositional dynamic logic. And it has been studied quite a bit in the context of traces. So you have to modify a little bit the basics of temporal logic, but it's a rather natural thing. But temporal logic captures only first order definability. So it doesn't capture all of regularity. And so that's an issue. Depends what you're trying to model. If it's first order, then LTL or temporal logic is good enough. And if the question extends to, but what about the cascade decomposition? for first order definable. If we were in words, we'd say, oh, but you know, Cronrode tells us that if your language is first order definable, I mean Cronrode plus Schützenberger and the rest, if your language is first order definable, then you don't need to use this group automata at all. It's just a cascade product of two-stage resets. It's very tempting to think that the same thing holds for traces, but it doesn't. It doesn't. I mean, there's like a little bit of counting mod something that needs to be done, and but exactly what the final, from the book statement will be is not quite obtained yet. Working on it. So it was a very good question, in fact.
Any other questions? Okay, if not, let's thank Pascal again.
Let's felicitate the speaker.
I don't know. Felicitate. Thank you. Thank you.
All right, let's break for lunch. We'll be back here sharp at 2.
Hello, welcome to the first talk in the afternoon, which is by Parthe Pandit, who's a Thakur Family Chair, Assistant Professor with C-Minds at IIT Bombay. A brief intro about his career so far. He was a Simons postdoc fellow at UCSD and he got his PhD and MS degrees from UCLA, and prior to that he got his undergraduate degree from IIT Bombay, and he works on theoretical ML with the intersections in signal processing and statistics. He was a recipient of the Schmidt Sciences AI 2050 Early Career Fellowships and Best ISIT Student Paper Award in 2019. So the speaker is definitely not fighting his sleep. Hopefully you can fight your sleep and pay attention, the English attention.
Thanks. Thanks for the kind introduction and for the warning to the listeners. First of all, it's a really exciting occasion, I think, a theory fest. And so I would like to congratulate IIT Madras for starting ArtCS. I had some really nice visits to the Simons Institute, and I'm hoping to I actually got several papers out of those visits to the Simons Institute, where I was just talking with someone on the board and someone else was passing by and they saw our problem and thought that they could solve it, and they did solve it, and we wrote a paper about it. Hopefully something like that can happen here as well. And yeah, so today I'm going to talk about some precise asymptotics of some high-dimensional statistical inverse problems. This is a tutorial style talk. I don't have any new results of my own that I'm presenting today. This is more of an overview of what's been done so far in a slightly different language that I find more convenient to understand these new techniques and frameworks that have been built in the last couple of decades. Okay, so here's the outline for my talk today. I'm going to talk about the linear inverse problem specifically. I'll start by presenting two optimization algorithms for solving this linear inverse problems, and they are loosely derived from some kind of a divide and conquer philosophy. I'll then show you a specific learning rate rule for those particular algorithms that enable us to analyze what happens in the algorithm in the system more generally in a statistical manner. So I'll make it precise what exactly I mean by statistical analysis of the optimization problem. And the analysis is going to be asymptotic average case analysis, and there again we'll see some kind of divide and conquer type of idea that shows up. So let's get started. We're going to talk about the statistical linear inverse problems. What's the problem? You're given some inputs and outputs. The inputs are these vectors AI, what we call features in machine learning, and the outputs are yi, what are called targets, or and what we're given is a statistical model for how this data may be generated. So yi is generated from some exponential family distribution that has this natural parameter AI transpose x, right? So x is this unknown parameter that holds across all the data points. Yeah. So I'm going to assume that x lies in n dimensions, and the number of samples that are given to me is m. Okay, so the popular approach to estimating this unknown vector x in this generalized linear model is some kind of a regularized version of maximum likelihood estimation. Turns out that in high dimensions there may be some problems with maximum likelihood estimation, and so in practice people usually do some kind of regularization. What is that? So you solve an optimization problem, the search is over Rn. The first term is some kind of a data fitting term. It measures how well you're fitting the data that has been provided to you, AI, yi. And the second term is some kind of a structure enforcing term. It penalizes certain structures that you don't want in the solution that you propose. Okay, and then what's the kind of analysis that we are interested in? So suppose psi is some kind of a metric that measures some distortion between x hat I which is the ith coordinate of your estimator x hat, and x star I, which is the ith coordinate of some ground truth that may have generated your data, right? And we want to understand some average metric across the coordinates, right? So one standard thing we typically like to use is the mean squared error. This is in the 2 norm, but you could have other norms as well that you may choose to understand the behavior of this distortion depending on what the problem domain that you're working with is. Yeah? Okay. So we went over this already. The supervised learning problem and learning linear models in a supervised learning problem is essentially the same. The only difference there is that there you are interested in making predictions. So there the metric of interest is going to be some prediction error and not parameter estimation error. In machine learning, the most popular way of solving these kind of problems is through empirical risk minimization or what is called structural risk minimization, when you add a penalty that sort of a regularization penalty. And in signal processing and statistics, the problem of sparse regression is also a sort of special case and a very well studied case of this problem. So you're given or you're not given this sparse vector x star that was generating the data, y is equal to a x star plus some noise. Yeah? A is your measurement that you know, y is the measurements that you obtained. So a is the measurement operator and y are the measurements. Yeah? And your solution is the solution to this optimization problem, again a least squares term plus some L1 penalty that encourages sparse solutions being proposed by the optimizer. Right? So this is the lasso problem that has been really well studied in statistics. And yeah, the challenge really in high dimensional statistics is we understand the behavior of these systems when m is much bigger than n. So m is the number of observations, n is the problem dimension that you are working with. But when that is not the case, understanding the behavior of the system is of interest more generally in this large class of problems. So let's look at a couple of divide and conquer style algorithms for solving these optimization problems. I'm going to rephrase the algorithms that are actually presented in their original papers in a manner that allows me to then use the learning rate rule that I'm going to talk about later. Yeah. So the optimization problem is essentially the following. You have this loss function here. I'm going to assume that all the elements of this loss function are the loss function is the same and the regularization function is also the same across all the coordinates. Yeah. And z is equal to ax. That's the constraint that ties the two terms in my objective function. Yeah. So this is one really interesting development in optimization and fast algorithms that has happened in the last 15 years or so, is the development of these proximal methods. So they solve the optimization problem by solving a certain scalar nonlinear optimization problem and using that to solve the vector optimization problem. So the proximal operator of a function rho is defined as the minimization in R of lambda rho plus some quadratic penalty. Yeah, and the quadratic penalty is centered at u, which is the argument of this prox operator. Yeah. So this is a 1D optimization. It can be solved very efficiently, and there is a lot of work that has gone in developing libraries to solve these problems for specific functions rho. So this is a very nice library called proxop, or the proximity operator. This is my bookmarks don't show, but it's one of the first bookmarks on my browser page as well. I use it quite often. It's a very nice library. I like it. Okay. So you can use these libraries to solve the minimization problem. We'll see how we do that. So here is a particular first order optimization algorithm. It's called primal dual hybrid gradient. It was proposed by Chambol-Pock in 2011. So what they first do is they rewrite the original optimization problem as a saddle point problem. The only thing that's been done here is that the convex conjugate of L has been introduced. So L of Z has been written in terms of its convex conjugate. Yeah. And if we define the proximal operators for the conjugate L star and the proximal operator for rho, which is your penalty, you can write this particular alternate minimization approach to solve the problem. So what is this doing? You take two estimates, x1 and z0, and then you hold one of them fixed and you minimize the other, and then you hold the first one fixed and minimize the other one. So here you are minimizing over z, here you are minimizing over x, and you keep doing this alternatingly. Yeah. So there are two step size parameters, eta and gamma, that are introduced here. And the theory in the paper by Chambol and Pock shows that as the number of iterations of this algorithm grow, as t goes to infinity, the x and t together, x and z go together to the saddle point of this optimization problem, if the learning rates satisfy a certain bound. Yeah, yeah, in that manner purposely, because I'll be choosing specific values of gamma and eta later. So there is some sort of precision parameters, not learning rate parameters. Yeah. Okay. Here is a second order algorithm the reason I call it a second order algorithm is because it requires access to the singular value decomposition of the matrix A. So you write down the SVD as U, S, V transpose. U and V are both square matrices. U is a square matrix in M dimensions. V is a square matrix in N dimensions. And you rewrite the optimization problem in these transformed variables. So U and V are invertible matrices. So V transpose V is identity, U transpose U is identity. Yeah, they are unitaries. So you can write the optimization problem in this sort of transformed manner. Now, what are the sub problems that you can solve efficiently? So you can reduce this problem to this particular optimization problem. So you have minimization of some function of a rotated version of some vector w in m plus n dimensions. So w is just the concatenation of x and z, subject to some linear constraints, and those linear constraints are easy to, so this constraint here is an element wise operating constraint because it's a diagonal matrix. Right? So you can sort of project onto that constraint easily in some sense. Right? The subproblem structure is nice here because the proximal operator of a function composed with a unitary matrix has a closed form expression. So you can use this fact to design your fast algorithm. And that's exactly what this Piesman-Rashford splitting version of ADMM does. It initializes two dual variables, and it alternatively solves a proximal operator, and then it does a rotation, which is a transformation, then it does another proximal operator, and then it does the reverse transformation, which is Q transpose. Yeah. I call it pure because there is no damping involved. The original PRSM ADMM algorithm involves an additional damping step that is necessary to make it converge. Okay. And by converge again I mean that as t goes to infinity, the number of steps go to infinity, so W converges to the augmented Lagrangian of this minimization problem, which is equivalent to saying x and z converge to the augmented Lagrangian critical points. Yeah. This is all well and good. This is very classical optimization based analysis. We are going to do something slightly different today. Okay. So here is a quick contrast with the other optimization analysis that is very widely used. So the standard optimization theory typically focuses on worst case problem instances. Will the algorithm converge in the worst case problem instance that you are given? The AMP theory that we are going to see today is more of an average case analysis, and we'll make it precise what average case actually means. Optimization theory again typically works with fixed n and m. The problem dimensions are fixed, but the number of iterations are going to infinity. Yeah? What we are going to do here is we are going to fix t, the number of steps for which the algorithm is being run, but we are going to take n and m to infinity in some sense. Okay. And turns out that as you take n and m to infinity, you get some exact answers. You don't get bounds, you get exact limits. Limits exist and you can find out what those limits are. The problem with this type of analysis is that many times there are large universal constants which may not exactly tell you how well you are doing. What you see in experiments is different from what your theory actually tells you. So it gives you a very nice general understanding of the problem space and what would happen in the worst case scenario, but it doesn't tell you what would happen in a typical scenario that you would see, right? And so that's the AMP style theory is going to be very precise. It will give you precise phase transitions about when the problem is going to fail in this average case sense. Okay, let's quickly contrast with other type of statistical analysis as well. So the classical statistical analysis on this graph, the x-axis is the number of observations, the y-axis is the problem dimension n in which the search is happening. Yeah. So in classical statistics, you hold the problem dimension fixed and you take the number of observations to infinity. Right? In this regime, many nice results hold for optimization based estimators. Right? Maximum likelihood estimation is consistent under mild regularity conditions. You also have some kind of asymptotic normality properties for maximum likelihood estimation. Yeah. In contrast, information theory type analysis will deal with what are the hardest problem instances you can never solve. Yeah, even in the average case. Yeah, there's a large amount of work that has gone in the last couple of decades in coming up with non-asymptotic analysis, which is what happens for a finite n and a finite m. Can you tell me exactly what is going to be the error if I run the algorithm? And this is a very powerful analysis, but again, it has large constants which sometimes are large enough that they don't give us precise insight into what's happening in the experiments that we run. And today we are going to look at this one regime in which we are going to work, which is that n and m are both going to infinity, but they're going to infinity at a proportional rate. So the ratio of n and m has a limit alpha, and that alpha is some constant. It's some number between 0 and infinity. It's not going to 0 or going to infinity as n and m go to infinity. Yeah. So there are some pros. The kind of theory that you get from this analysis is very actionable. Okay, I'll show you a trailer of what exactly actionable means. There are no large constants that are hidden behind big O notation. So whatever you see in practice is very well explained by the theory. The cons are that, well, the proportional regime may be restrictive and there are some assumptions on the data that you need to make. Under which this theory is going to give you precise analysis, but you may be willing to make those assumptions just because the analysis is so crisp. Okay, so here is the sort of the nature of the results that you can get using this theory. So this is the group lasso estimator or the multitask lasso estimator, which is solving this matrix valued optimization problem. So the search is over matrices of shape n by c. The first term is the Frobenius norm square. The second term is the sum of the two norms of the rows of x. Yeah. So the first term couples the rows of x, the second term couples the columns of x, so you can't solve this problem independently for the rows and columns, you have to solve it together. And suppose your data is actually coming from some kind of a ground truth solution x star, such that the ground truth solution has sparse rows, so very few rows in this matrix are actually non-zero. Okay. Then and the gamma function, the specific form of the function is not too important here, but what's interesting is that we can get exact answers to what is going to be the limiting performance of your estimator. Yeah. So the lines that are being drawn here are using this function here. Yeah. What is the x-axis? Sorry, I didn't mention what the x-axis was. The x-axis is the different values of the regularization parameter lambda. Yeah. So here clearly you can see a particular phase transition that all problems behave in a certain manner when lambda is large enough, and then depending on the sparsity there will be a bifurcation of the behavior of the system. No, second moments have to exist. Yeah. Okay, so here is an immediate application of this in a sense that it can be used in practice directly. A large amount of time is spent by engineers in doing hyperparameter tuning in practice. What this theory now gives me is an exact curve of what is going to be the best value of lambda for a given sparsity of the ground truth. Yeah. You may not know what the ground truth sparsity is, but if you have a sense of what that is, you can refine the search. So the y-axis here is in log scale. You can refine your search. You can also do something like back engineer what could be the sparsity based on what is the optimal value of lambda that you see in practice. Yeah? So these kind of levers you now have access to in some sense. Okay. So let's now sort of build some tooling to enable us to do this kind of analysis when we are working with these n and m limits going to infinity. So we are going to do analysis using again some kind of divide and conquer. We are going to break the problem down into two simpler subproblems for which we can give exact analysis, and then we will build on top of those exact analysis to get these closed form expressions for the limits that we want. Yeah, so the first problem is that of denoising when you are adding Gaussian noise. Okay. So suppose you have a scalar random variable x that has a density function fx that is proportional to e to the minus rho x. Yeah. What you observe is r, which is x plus some Gaussian noise with variance sigma. Okay. For this problem, the maximum a posteriori estimator, which is the mode of the posterior distribution p of x given z, is exactly what I have written here. It is the proximal operator of rho evaluated at r. Yeah, and the noise shows up somewhere there. Yeah. So this is one object that we'll use. We can analyze the asymptotics of scalar denoising quite well. We'll show exactly what happens. The other simpler subproblem that we can use is what is called ridge regression. Okay, so what is ridge regression? You solve this the quadratic optimization, but the penalty now is instead of L1 norm, we have the L2 norm squared. The advantage of this penalty is that there is a closed form expression for what is going to be the solution. Okay, so you can take the gradient, set it to 0, you get this closed form expression. And the nice thing is that again we can analyze what are going to be asymptotic properties of the ridge regression estimator. Okay, and then we will combine these two analyses together to get what happens in more general nonlinear cases. Okay, so here is what the analysis for Gaussian denoising looks like. So suppose you are now looking at denoising a vector which has Gaussian noise added to it. So if your prior was the Laplacian prior, which corresponds to having rho of x is equal to the absolute value, the proximal operator you can find in closed form. It is what is called a soft thresholding operator, and it has certain thresholds that are given by the constants that exist in this. Right, and turns out that if we assume that the empirical distribution of this vector x star converges to a scalar random variable x star, we'll maybe mention precisely what we mean by this assumption. We can exactly tell what is going to be the mean squared error of reconstruction. The limiting error of reconstruction is a two-dimensional integral over variables x and t. T has the Gaussian density and x has the law of whatever is x star. So dfx is a length element of x from the CDF of x. Yeah. And we are going to call this the function epsilon. We don't want to keep writing long integrals every now and then. Yeah. So g here is the proximal operator. Right. So there should have been a comma and gamma here, which I have missed. Yeah. So there's a gamma here in the notation, and that's gamma is the gamma that shows up there. It's related to the threshold. Yeah. Okay. So there's some spectral analysis that you can do for the ridge regression estimator. You can do some spectral analysis for the ridge regression estimator. This is a nice homework question to give to first year grad students or something like that. So you can write in closed form what is going to be the solution of your estimator, which allows you to actually open up what is going to be the mean squared error and write it in terms of the singular values of the matrix A and some other sort of transformed versions of the vector x star and the noise that is being added. Okay. And again, if you were to make this assumption that the empirical distribution of these three vectors converge to some three scalar random variables, you can again write down in closed form what is going to be the limiting mean squared error of this estimator. It's going to involve expectations of scalar random variables, and I'm just going to write this as an expression. I mean, there's not much I can say here at this point. I can just calculate these expectations in closed form because they are scalar random variables. Yeah, I can do this on a computer very cheaply. Yeah, this is a typo. It should have been x stars. Yeah. Okay, and turns out that these expressions show up again and again in all the analysis that we will do as well. So we call them the bias function and the variance function. And this is sort of the signal power and this is the noise power. So this is how it breaks down. Okay. Okay, so for matrices A which are IID Gaussian, so if A is this matrix of size m by n, whose ijth element is drawn IID from a Gaussian distribution, and the variance is 1 over m, which is just done so that the normalization is not trivial. Then the distribution of the singular values behaves in a very predictable manner as the size of this matrix grows. Okay. So what I am showing you here is the histogram of the singular values squared of this matrix A, yeah, for n equal to 2048 and m equal to 4096. Yeah. And the limiting distribution only depends on whatever is the ratio of n and m. Yeah, this is what is called a Marchenko-Pastur distribution. It's a sort of celebrated result in random matrix theory, which shows up heavily in the kind of framework that we are going to work with. So we'll define this function t that shows up again and again. It's derived through something called the Stieltjes transform of the distribution of the singular values squared, and the bias function is some algebraic manipulation of the t function, and the variance function is also another algebraic manipulation of the same t function. For the Marchenko-Pastur distribution, somebody has calculated exactly what is going to be this t function. So we know exactly for the Gaussian matrices what is going to be the behavior of the resulting error for the ridge regression estimator. Yeah, we know exact closed form expressions for how this is going to behave for different values of my regularization parameter lambda. Okay, so for the scalar denoising, scalar Gaussian denoising, we wrote it down as an expectation with respect to two variables. For the ridge regression, we wrote it down as an expectation with three variables: the signal, the noise, and something that was coming from the singular values of the matrix that we are using. So let's now use some kind of divide and conquer based analysis that puts these two pieces together and gives us closed form expressions for more general estimators. Okay, so here is a particular algorithm. It's called the generalized approximate message passing algorithm. It chooses specific values for these learning rates that showed up in the primal dual hybrid gradient algorithm. So this is a special case of the primal dual hybrid gradient that we talked about earlier, with a special learning rate that is chosen for the two updates. So gamma and eta have some special learning rates that have been chosen. Okay, it has the same fixed points as the primal dual hybrid gradient algorithm. Yeah, because we're only changing the learning rate and the learning rate rule, nothing else. So if we can say anything about limiting properties of solutions to this particular set of iterations, that will imply things about the behavior of the PDHG algorithm more generally. Yeah, and more generally also about the saddle point that these solutions are converging to. So we can characterize the problem more holistically. Why are these step sizes chosen in such a manner? Well, because some kind of decorrelation happens, and it allows us to get a tractable handle on what are the quantities these things are converging to as the problem size goes to infinity. So this is called generalized AMP because it generalizes the AMP algorithm, which was defined only for the square loss. So remember, H was the proximal operator for the conjugate of the loss function. The case of square loss was covered by Donohoe, Malecki and Montanari in a very nice paper from 2009. Okay, so let's formally state what this kind of convergence is going to look like. In order to state that convergence, I need to first define a new mode of convergence that you may not have seen before. So we are going to work with a class of test functions which are called pseudo-Lipschitz functions of order k greater than equal to 1. Okay. So what are they? Essentially, they're kind of relaxations of the Lipschitz function. The difference in the output is bounded by the difference in the input times something that is allowed to depend on what are the inputs. Okay. So for k equal to 1, this is just the class of Lipschitz function with Lipschitz constant 3. Yeah. But you are allowing k to be bigger than 1. So it's a generalization. So we are going to say that a sequence of random vectors, okay. So xn is my sequence of random vectors. Xn is one random vector in Rn. And we say that it converges to this random variable x in this PLK sense if the following property holds. If for every pseudo-Lipschitz function, the average of this function over the elements of this coordinate, over the coordinates of this vector xn converge almost surely to the expectation of that same function with respect to x, which is what we are converging to. Okay. Why do we say almost surely here? Because x was a random vector, this empirical average is also a random variable, and so when we talk about convergences of random variables to constants, we have to qualify it with what is the mode in which this convergence is happening. We are going to talk about almost sure convergence here. Yeah. If you've seen Wasserstein metrics, this is equivalent to some kind of Wasserstein convergence. If you define the empirical CDF that you get from the coordinates of this vector xn, this is now a random CDF because the vector was a random vector, right? Then the Wasserstein distance between this empirical CDF and the limiting CDF is also a random variable, and that random variable converges to 0 almost surely. Yeah, so these are two equivalent ways of stating this notion of convergence. Okay. So here is the formal statement that we can provide for the analysis of this generalized approximate message passing algorithm. So here are some assumptions on the data that we are going to work with. So AMN is a matrix of size Mn. We already mentioned what are the entries, how are they distributed. We are going to assume that the ground truth converges in this PLK sense to X star. Yeah. Yes. So if it exists for if the kth moment exists, then it exists for all of them. So we just have to check for the kth moment, and we are implicitly saying here that the kth moment exists when we say this. Yeah. Yeah. So if the ground truth converges to some X star, and the initialization also converges to some known random variable Q1. Then we can say something about the joint distribution of the iterates of this algorithm. Okay, so I run the algorithm for t steps, and I can say something about some iterates that show up in the algorithm. Okay, this is a formal statement. It has been proven rigorously. A corollary of this is what is actually useful for us. The corollary is the following: the mean squared error is exactly the error term that we saw earlier. Okay, what's different here is that gamma and tau are some sort of two constants that also we need to track. So these are scalars that we need to keep track of. Yeah. So what are these scalars? There is a clean recipe of how to come to these scalars after t iterations of the algorithm. The paper actually gives very precisely how to calculate what these scalars are going to be. Without going into too many details. They all essentially involve expectations of scalar random variables, integrals of at most 3 dimensions at any point. Yeah. You can get a very nice simplification for what happens in the case of the square loss, and I'll show you an experiment that validates the descriptions that were given by the theory. Okay, so the experiment that I'm going to show you is for the lasso problem, where the SNR is equal to 1, so 0 dB SNR. Sparsity is 1%, n, which is the input dimension, is 1024. Okay, for that particular scenario, what I'm showing you are the scalars that were showing up in the algorithm, the errors that were being presented by the iterates of the algorithm for different values of SNR. So the dots again are what you see by running an experiment on a finite dimensional problem. The solid lines are what you see are obtained by the scalar iteration that I wrote down. I know exactly in closed form what is going to be the value in the limit when n and m both go to infinity. You see some error bars in some of these terms. That's because the finite dimensional problem is still a random problem, and that is why there is going to be some variance to these quantities. And as you would expect, as the size of the problem increases, this variance shrinks. So this was for the problem with dimension 1000. The problem with dimension 4000 has much smaller error bars, and you can't even see the error bars in most of the places. Yeah. So this is a theory that tells you exactly what is going to be the behavior of the performance of the optimization formulation. Okay. So using this kind of theory, some very nice results have been derived for different problems in high dimensional statistics. I'm just going to share a couple of these results. So one such result was by Bayati and Montanari in 2011. They were able to show that there are some sort of implicit functions that tell us what is going to be the mean squared error, which is this quantity in red here, and how it depends on the regularization parameter lambda through some implicit function. Okay, so they didn't give me explicitly what was going to be the behavior of MSC as a function of lambda, but they gave it to me as an implicit function which involved 3 variables. That's good enough. Yeah. Okay. Here is another experiment which essentially tells me that even if I were to run the primal dual hybrid gradient algorithm or this generalized AMP algorithm, they both find the same solution, and so their performance is asymptotically the same. What's interesting though is that the learning rate rule that GAMP uses is far below the threshold that the convergence analysis for PDHG requires, and yet somehow the algorithm also manages to converge with that particular step size rule. Yeah, it's kind of taking the entire spectrum into account and not the worst case directions that the worst case analysis was taking into account. So Gaussian matrices may be too restrictive an assumption to make, and we were able to do this kind of generalized analysis for arbitrary singular value distributions beyond Gaussian matrices in the case of ridge regression. So can we do this for other problems as well? And turns out the answer is yes. There is a sort of variant of this machinery called the vector approximate message passing algorithm. This uses the second order algorithm that we talked about, the PRS ADMM algorithm, and it essentially uses these subproblems with their tractable analysis. Okay. Very quickly, here is a description of what the algorithm looks like. I'm just stating what it's going to look like for the square loss case, but essentially for every other loss function you can reduce it down to exactly this form. But the algorithm is very symmetric in how it operates. There is a certain correction step that happens, and then you multiply by a unitary matrix. You apply a nonlinear operation that applies element wise. You do another correction, and then you apply the reverse of the unitary matrix. Okay, So it's very symmetric in how the algorithm operates. This makes the analysis very elegant in some sense. So again, the fixed points are critical points of the augmented Lagrangian, and here again we can give a formal analysis for what is going to be the performance of the algorithm as the problem size goes to infinity. So as n goes to infinity, if t is fixed, the number of iterations for which the algorithm is run, then we can precisely state what is going to be the limiting distribution for the iterates of the algorithm. And here again is sort of the closed form expressions for what are the errors that are incurred by the algorithm. And here you can see the two sub-problems that we had broken it down into earlier show up. So there are two estimates of the solution, x and x hat, and their errors are being tracked through this scalar iteration. One involves this scalar integration with respect to the law of x star. The second involves the expressions that we got for the bias and variance for the ridge regression estimator. You can show formally, specifically, that as you run the algorithm long enough, these two quantities match and they both go to what is the error of the estimator, that is the solution to the optimization problem. Okay, so a quick overview of what's the proof, what's actually allowing us to use so many Gaussians under the hood. Why are these things converging to Gaussians? A very quick, this is a nice question again to ask in an intro to statistics class in grad school. So if Z is an isotropic Gaussian, and let D0 be the event, that you have some linear measurements on Z, then the conditional distribution of Z given this D0 event is also a Gaussian with a mean that is given by T pseudo inverse B, and another independent Gaussian which determines what is going to be the covariance matrix for this distribution. Yeah. The interesting thing is, for Gaussians you can say that this is an independent copy of Z. Yeah. So a similar property also holds for matrices. So if A is a matrix whose entries are IID Gaussian, and you have some linear constraints on this matrix, so some constraints from the left, some constraints from the right, so these are two constraints, then if A is distributed IID Gaussian, then A conditioned on D1 intersection D2 is also a Gaussian matrix with a mean that has an expression and a covariance that comes from another independent copy of a Gaussian. Okay. Turns out that this property can be extended beyond the space of Gaussian matrices. We can apply this to what are called Haar distributed matrices. Haar distribution is the uniform distribution on unitary matrices of any size, right? So, if we have the event is A is equal to VB, A and B are deterministic in this particular slide, then conditioned on this linear constraint event, the distribution of V is, again, you can break it down as a deterministic part and a random part. And the interesting thing is that the random part is always going to remain independent of the deterministic part. Yeah. Okay, so the proof essentially is, so till the tth iteration, the algorithm has seen certain times the matrix, the random matrix V has been multiplied certain times from the left and certain times from the right. This gives some linear constraints on what is the randomness that remains in this random matrix, right? So this gives a conditional distribution for the random matrix after t iterations of this algorithm, and that allows us to show that certain iterates of the algorithm can be expressed as some deterministic term plus a term that behaves like an independent Gaussian. Yeah. So here is sort of the pictorial description of what's happening. So on top is the behavior of the algorithm. On the bottom is the equivalent system of scalar random variables and how you can derive this system. So every time the algorithm hits a unitary matrix, you are going to get some kind of Gaussianizing behavior on the output. Right? What that means is everything that you want to track in the algorithm is essentially a Gaussian or some nonlinear function of a Gaussian. And how do you keep track of Gaussians? You only need to keep track of their means and covariances, and that's what the state evolution machinery does. It just keeps track of what are the covariances that are involved in the algorithm. Okay, so here are some examples of what kind of results have come up in the last few years using this kind of machinery. So here is one result. This is a very nice result from a paper that came in NeurIPS in 2020. So they talked about the phase diagram of the true positives and the false discoveries that you get when you use the lasso formulation to find support recovery type of problems. And as you change the level of sparsity or the level of hardness of the problem, you see different behaviors and you see some kind of phase transitions show up in what is achievable and what is not achievable. Yeah. So these kind of phase transitions you can exactly characterize using this framework to do your analysis. Yeah, and this machinery has been applied quite widely in studying the behavior of many problems in high dimensional statistics now. Yeah. So TPP is the true positive proportion and FDP is false discovery proportion. Yeah, and yeah, so yeah. Okay, here is another very nice paper that came out in 2022 in Annals of Statistics on the surprises in high dimensional ridgeless least squares interpolation. So this is a phenomenon that is recent to machine learning as well. It's called the double descent phenomenon. So as you increase the ratio of n over m, you see that the system's performance first degrades, you do some kind of overfitting, and then somehow strangely the error in your system reduces again. And they use this machinery to get some very crisp analyses. So here again in these plots, the dots are what you get from experiments and the lines are what you get from these closed form expressions from the analysis. And turns out that this property of double descent is very much dependent on what is the level of regularization that you use in practice. As you tune the level of regularization, you get these different curves with different colors. Yeah, so at some point the double descent just goes away if you optimally tune your regularization lambda. Okay. They didn't quite use exactly the same machinery. It was more based on ideas from random matrix theory, but it's only slightly different from the machinery that was developed. In fact, Andre Montanari was the one who wrote the first paper on these AMP type analyses. Okay, yeah, so this is my last slide. I'll just quickly summarize what we talked about. We were able to do some kind of average case asymptotic analysis for optimization problems using closed form expressions. And this allows us to actually pose and answer some very important and interesting questions in statistics, machine learning, signal processing, and so on. And this enables characterizing sort of phase transitions in these systems, which is very important in today's day of sort of doing theory research, where a lot of phenomena are coming to us from sort of the empirical world. The nice thing is that this entire framework is sort of full of rigorous proofs. There's no hand-wavy arguments here. And there are sort of some other equivalent frameworks that are also being developed simultaneously, and we don't fully understand the connections between these frameworks, so there are some open gaps there as well. This framework has been used quite widely in the last 5 years to understand many complex behaviors that arise in systems involving deep neural networks. So So things like test time inference and scaling laws analysis have also been done using this kind of a machinery. Yeah, with that I'll stop. Thanks.
Questions? Okay, since there are no questions, I'll ask one.
Okay.
Yeah, so one thing is like you are trying to write down a precise characterization of an asymptotic mean square error. Is there a way to use that to design better algorithms? Like,
Yes, yeah, you can use this information to design better algorithms.
but there'll be unknown quantities and all that, right?
Yeah, so these won't be sort of algorithms that would work in the worst case scenario.
Not worst case, but even on an average, like you have a data set and you had the matrix and maybe something about the ground truth that you don't know.
Right, so you can use this information to design better algorithms, yes, yeah.
I mean, that part is like, is it unexplored? Because, okay, I get an expression.
I don't think it's been explored. Well, there is some limited work on, so there is this class of algorithms which are called unfolding based methods for solving inverse problems. So they essentially roll out this gradient descent iteration which involves a large number of matrix multiplications, and then they say, well, we'll throw out whatever the original matrices were, we'll just learn these matrices by throwing some data at them. Right, so this is, so you can do more efficient unfolding in some sense. You can reduce the depth of whatever unfolding you're doing using some problem structure that you may know extra.
Or to put it differently, like, is there some way I can use that expression to come up with an algorithm which gives me lower asymptotic mean square error? Okay, this is...
Oh, this is actually to do with the saddle point, right? Like it's, if any algorithm reaches that saddle point,
that's enough.
You are going to get that same error in some sense.
Okay, so that's...
So
that's
what does better algorithm then mean is
yeah, I need to think about it, but like you have a mean square error for every like x hat.
Yeah.
Okay, my better is always in non-asymptotic. Asymptotic, I don't know. But like
yeah.
For every non-asymptotic case, if I have a like a mean square error bound, I can use it to see if I can come up with a better algorithm with a lower bound. But in the asymptotic regime, I don't have a clear direction.
Yeah. That's an interesting question. I'll think more about this.
It's still brainstorming. Yeah. So yeah, thanks.
Yeah.
Thank you. Maybe potentially unrelated, but so in these, do you expect, does this framework also give you, let's say, rates of convergence, right, under some assumptions, good assumptions on the data, right? So the context behind this is at some point there was an algorithm which I was looking at which got, in theory we could only show like in the worst case setting some polynomial rates, but in all empirical examples we looked at it converged linearly.
Yeah.
Right. So I wonder if something like this can...
Yeah, something like this does hold actually here. So in this algorithm you can show will converge exponentially fast if it converges.
Okay.
Because there's no guarantee of convergence. So this is kind of more of a proof technique. So you would still use something like PDHG or ADMM to actually solve the problem. But once you've solved the problem, you still want a handle on, well, could I have done better by tuning lambda or something like that, right? Those kind of questions are just hard to answer without doing them by yourself. This kind of gives you a handle on these kind of quantities. How would the behavior of the solution that PDHG finds, can you give me a handle on that in terms of the other hyperparameters in the problem? But yeah, if the algorithm converges, it converges much faster than any other algorithm I have seen. That it converges is, there's no guarantee for that. Like, yeah.
Thanks.
In that case, there are no other further questions. Let's thank the speaker again. And you want to give it? Yeah. Okay. As a token of appreciation, I think you get a memento. Just this.
Just the mobile. That also looks gift wrapped, na? So next is Divesh, I think, right? I will introduce. Yeah, hi. It's my pleasure to introduce our next speaker, Divesh Agarwal, who is not only a well-known researcher but also a good friend. Divesh is an associate professor at the Department of Computer Science and a principal investigator at the Center for Quantum Technologies at the National University of Singapore. He earned his PhD at ETH Zurich. His research spans lattice-based cryptography, pseudo-randomness, computational complexity, and coding theory. His key contributions include the fastest known algorithms for many different lattice problems and advancing the understanding of their computational hardness. His work also includes state of the art constructions in non malleable codes and extractors, which play a crucial role in many cryptographic protocols. In recognition of his research, he was awarded the NRF Investigatorship in 2024. So we're very happy to have him here. And also for those in Chennai, he's going to be around next week. So you can also, talk to him anytime next week. Over to you.
Sorry. ऊपर करूँ? Okay. It's good. Yeah. All right. So thanks a lot, Shweta, for inviting me and for the great introduction. And this is an amazing initiative, and hopefully we'll see a lot of success over the next few years. Okay, so today I'll be talking about this work. It's kind of a survey talk, basically, where I'm talking about lattice problems and kind of looking at them from a slightly different perspective than what people usually think of computational problems. Like when we talk about computational problems, we typically think of polynomial, like basically we restrict ourselves to polynomial time. Either we talk about polynomial time reductions or polynomial time algorithms, or we'd say that, like when we say that a certain problem is hard, we typically mean that there's no polynomial time algorithm, right? For example, when we say that P is not equal to NP, implies that there's no polynomial time algorithm for a certain problem. When we say that a problem is cryptographically hard, we assume that there's no polynomial time algorithm to solve this problem. But what people typically care about in practice when we are thinking of, let's say, crypto systems is we really want to understand how hard it is. Like just being not solvable by a polynomial time algorithm is not necessarily enough. Okay, so here's a brief overview of my talk. I'll begin by introducing lattice problems and kind of talking about what is known if we restrict ourselves to the standard setting, polynomial time. Like that's kind of what I'll begin with. And then I'll talk about kind of what we can say when we go beyond polynomial time, like talk about exponential time algorithms. I mean, here when I'm saying algorithms, I mean deterministic or randomized algorithms, but also non-deterministic algorithms, and then reductions. And then even if we take that viewpoint, I'll mention there's some concern with these reductions, and then I'll present an alternate viewpoint. So this is essentially, the whole talk is more or less about changing the viewpoint and just re-looking at the state of the art and kind of seeing what we can say. Most of the content is going to be quite simple. I mean, you can interrupt me and ask questions during the talk. Like, you don't have to wait till the end. Being interactive is generally more fun. Okay, so start with introducing lattice problems. So what is a lattice? A lattice, very simply put, is a discrete subgroup of n-dimensional real space like R to the n. So for example, if you want to draw it in 2 dimensions, this is how it will look like. It's like a grid-like structure where for example, the simplest lattice is the lattice of integers in n-dimensional integer vectors, right? In general, more generally, the lattice is specified by a set of basis vectors b1 to bn. So for example, here is a picture of a 2-dimensional lattice with basis b1 and b2, right? And you can see that all integer combinations of these basis vectors are basically lattice vectors. So like 2b1, 2b1 plus b2, 2b1 plus 3b2, like all integer combinations, right? More generally, the lattice is an integer times b1 plus an integer times b2 plus an integer times b3 and so on. So you look at all such vectors, infinitely many, but countably infinite. So these are what defines this lattice, right? Okay, so what is the lattice problems that we consider? The most important, the most fundamental lattice problem that we want to think about is what is called the shortest vector problem. So what is this problem? Here you are given a lattice, you'll be specifying the lattice via the basis. So you are given n basis vectors and you want to find a shortest non-zero vector in the lattice. For example, in this picture, this vector v is the shortest non-zero vector. So of course 0 is the shortest vector, right? But we are not interested in 0, we want to find the shortest non-zero vector. And I'll denote by lambda 1 the length of this vector. So this lambda 1 will show up many times, so just remember that this is the shortest vector. This is the length of the shortest vector. And when I say gamma SVP, what I mean is the problem where we want to not necessarily find the shortest lattice vector, but find a vector which is a gamma approximation of the shortest lattice vector, which means it is fine to find a vector that is at most gamma times lambda 1 length. So we are okay to relax it by a factor gamma, right? So for example, if you think of this circle, or in general in n-dimensional, an n-dimensional ball of radius gamma times lambda 1, we are okay with finding any vector inside this ball, right? There are in n-dimensional space there can be exponentially many vectors. We are happy with finding any one of them, right? Okay, so SVP is a hard problem. It is NP hard. Let me just give you like as much intuition as I can possibly give on this 2-dimensional planar surface. Like basically for a 2-dimensional lattice, a basis basically can look like the nice basis that we had earlier, but it can also look like the basis like this, right? B1 and B2. And imagine that you are just given B1 and B2 and not really given the lattice vectors. When you look at that, it's much harder to spot where the short vectors are, like in this lattice. In particular, finding the shortest vector. And this picture becomes way more complicated when you think of n dimensions. And actually for 2 dimensions there are smart algorithms that can find the shortest vector in polynomial time, but for n dimensions, basically it's an NP hard problem. You cannot really find an efficient algorithm. Another very important problem for lattices is what is called the closest vector problem. Here you are again given a lattice specified by the basis, and you are given a target vector. This target vector can be anywhere in the n-dimensional space, not necessarily a lattice vector, and the goal is to find the closest lattice vector to this target. Yes? Yes. Factoring a large number is not NP hard. For it is not NP hard, it is believed to be computationally hard in the sense that people at least believe that there is no efficient classical factoring algorithm, but it's not NP hard. In particular, you can prove that it is in what is called NP intersection co-NP if you define it as an appropriate decision problem, and so we don't expect this to be NP hard, right? Basically this under standard complexity theoretic assumptions, actually factoring is not NP hard. But in what context do you want to ask? we don't believe we know it. There is a quantum algorithm. I mean, whether we will have large-scale quantum computers that will actually implement it is like you can say that we believe that this will happen, but there is an algorithm. Okay, one can give different answers to this question, but I think the right answer is we just don't know any quantum algorithm for this problem. And since it has such a geometric structure, and typically we have seen quantum advantage for problems which have a nice algebraic structure, which is not there in this problem, right? Basically, so typically for geometric problems we have not been able to exploit any, get any quantum advantage. So that's why I mean there's no proof that you cannot have a quantum algorithm for SVP. Yeah, actually there have been many attempts in the recent times, like many failed attempts, but there have been people have been trying to kind of come up with a quantum algorithm. Yeah, so okay, so no, so not for the NP hard version, but as you see, like basically this SVP, we can define it with gamma approximation, and it's also interesting actually for the it's cryptographically relevant when gamma is polynomial in n, and for that variant we can have like potentially quantum algorithms. I mean this is not ruled out. For NP hard problems, sure, we don't expect quantum algorithms. Yeah, especially if you want to talk about public key cryptography or even one-way functions, we don't know how to place. Yeah, okay, so closest vector problem. So here the goal is you want to find the nearest vector to this target vector, right? I mean, so you're given a basis, given a target vector, and you want to find the nearest lattice vector. So and when I say distance L comma t, this denotes the distance of the target vector to the nearest lattice vector. Sorry? Yeah, I mean, okay, I should have specified the norm, but since I'll not bother too much about it, like think of Euclidean norm, right? I mean, I'll not be, but you can define it for any norm in general. For mostly when we talk about this in cryptography, we typically think of the Euclidean norm. So let's just restrict ourselves to that. Okay, and then there's a variant of this problem which is called the bounded distance decoding problem. This is just CVP but with an additional promise that the target vector is close to the lattice. So the distance of the target vector to the lattice is small. So typically it's like distance is lambda 1 of L with shortest vector divided by a factor gamma, and gamma is, you think of it as bigger than 2. So why you want it to be bigger than 2? So that like there is unique decoding. So so when you look at the nearest lattice vector, you cannot have more than 1, right? So it's, and this name really comes from basically the error correction code literature. There's an analog of this in error correction codes, and that's where the name comes from basically. And for lattices it doesn't seem like bounded distance decoding seems like the natural name, but just because the similar variant was already existing in the codes literature, and that's why kind of it got this name. Yeah, so this is a problem that actually we will care a lot about. So okay, and then the problem that we care, like this is probably the most important problem in cryptography, at least in the last 20 years. This is without if you look at any crypto Eurogroup proceedings, I think maybe half the papers, I'm not exaggerating, okay, 1/3 1/3 would have LWE somewhere. Okay, fine, we can check, but good fraction. Yeah, okay, so learning with errors, what is this problem? It's essentially the bounded distance, it's a randomized variant of the bounded distance decoding problem that I just mentioned. So what is the problem? You have a secret S. So secret S is the vector that you need to find out. So this is, and what you are given is these noisy samples. So you're given a vector A and inner product of AS plus some error, right? and you're given a bunch of these samples. So let's think of these as like m samples. M is something like polynomial in n, multiple samples, and the goal is to find S, right? Notice that if you did not have error, then this is a trivial problem. You can just solve it using Gaussian elimination, right? Straightforward. But with these errors, it becomes much harder. This, like in particular, we don't know how to kind of recover S. This is a hard problem. So, as I said, this is essentially the average case version of BDD. How to view this? Let's think of a lattice where you are lattice which is generated by these column vectors of A, right? So the column vectors of A are the basis vectors, but additionally you basically append these with this P000, 0P00, like P times basically the fundamental basis vectors, right? And when you do this, then essentially what you are asking is this target T, think of it as AS plus E modulo P, and this is close to the lattice generated by these vectors, the column vectors of A and these in this P. Basically, so this target is close to this lattice, and the goal is really to find the nearest vector. Finding the nearest vector would immediately give you S, which is the secret that you are interested in. Make sense? So this is very closely related to the bounded distance decoding. It's essentially an average case variant where basically the vectors, the matrix A is chosen at random and errors are chosen at random, right? As opposed to BDD, which was the worst case problem, with the basis is arbitrary and the shift is arbitrary also. What's the reason? So because we want to look at modulo P, right? So this automatically, when you look at the lattice generated, so essentially what is a lattice, right? We take all vectors here and all of these vectors and look at all integer combinations. And taking integer combinations with these is effectively doing the modulo P operation, right? Good. Okay, so why do we care about lattice problems? So why are they interesting? Why do we have 1/3 or 1/4 or whatever fraction of the crypto proceedings? Because this is probably the most popular answer, at least at the moment. I mean, this was not the reason that people started looking at lattice problems. People started looking at lattice problems primarily because of the worst case to average case reductions. But yes, but I think they got popularity after IIT's result and then Regev's result basically made it really, really popular. But since this is the most popular answer, let's kind of go with that. And like, so this is people really care about post-quantum cryptography. In particular, NSA in 2015 made this statement where basically they said like our ultimate goal is to provide cost-effective security against a potential quantum computer, and so they said like let's get a new suite of algorithms up to basically protect us from this upcoming quantum-resistant algorithm transition. Like essentially, people believe that large-scale quantum computers might come up sometime in the future, and basically you want to protect like yourself sufficiently in advance. And so this NIST, the National Institute of Standards and Technology in the US, initiated a standardization process in 2019 for identifying a post-quantum crypto system for widespread use. Right, this was initiated, and a bunch of submissions were received. This was basically the initial list of submissions. As you can see, most of the submissions, like a large fraction of the submissions, are actually lattice based, and then there was some code based, multivariate, hash based. Like this was, I think there were 20 signature schemes and 49 key encryption, or basically encryption schemes. But then what survived after like a scrutiny over a few years basically was mostly lattice based schemes. There was one hash based. Then they continued around with future like for digital signatures, but essentially what people are relying the most on are lattice based schemes. Right. This is generally the state of the art, and so that's one motivation to care about lattice based cryptography. The The other one is that this lattice-based cryptography allows us what is called the worst case to average case reductions. What it means that we can basically base our cryptography on worst. So when we want to use cryptography, obviously we want to generate our public key randomly, so randomness is inherent, right? When we use them, but we want to base our crypto systems. I mean, it would be great if we can base them on worst case problems, because when we say that a problem is hard, we are much more comfortable saying that a worst case problem is hard than we are that an average case problem is hard, right? I mean, so, and what was amazing about lattices, and which is not true for pretty much any other public key crypto scheme, is that there are actually reductions from. So this you can say that if you can break this particular public key crypto scheme, then that means that you can essentially solve this worst case lattice problem that people believe is hard, right? That's a well-studied worst case lattice problem. So in particular, what people got was a reduction. So this was actually from the work by Oded Regev from 2005. Got a reduction from approximating the shortest vector problem, approximating SVP, to solving the learning with errors problem. And so LWE, which we kind of believe is hard for average instances, and this is hard in the worst case, right? I mean, so what this reduction achieves is there's a polytime reduction from this approximating SVP to LWE. So here's a picture of what is known about the shortest vector problem, kind of before our work. Essentially, this is what is known in the polytime world. So in particular, what is known is that for approximating this problem up to a factor constant factor, this is NP hard. So we don't know how to, so basically unless P is equal to NP, there's no polytime algorithm for solving SVP up to a constant factor. And then there are clear barriers for approximating this, or for showing NP hardness up to a factor bigger than square root n. In particular, square root n approximate SVP is in co-NP, and square root n over log n is in co-AM. So that means we don't really believe that it's NP hard for those factors. And if you make the factor slightly larger, then you can suddenly build very useful cryptography from this. In particular, if you believe that n approximate SVP is hard, then you can build then you can build one-way functions from this. And if you believe that n to the 3 over 2 factor LW n over 3 n to the 3 over 2 factor SVP is hard, then we can show that LW is hard, and we can build public key crypto from here. And for classically, basically, if you believe that n squared SVP is hard, then we can, if it's hard classically, then again we get sorry? Like if it's hard means there's no polytime algorithm for this, then there's no polytime algorithm for LWE. Basically, that's what we are saying, right? And I mean, yeah. So they got NP hardness of SVP for L2 norm, right? I mean, yes. So, but what they got is, I mean, this is NP hard under randomized reductions, right? But for P greater than 2, they got it under deterministic reductions. Carp reduction. Yes. 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 Yes, but you can look at the lattice generated by this. You can get basically we are in m dimensions, right? So you can get m linearly independent vectors that are generated by these n plus m vectors. So you can there are standard algorithms that you can run. Start with these n plus m vectors, and you will get m linearly independent vectors that generate this lattice. Yeah. Yeah, exactly. I mean, you can define a group, so you can define it by a basis, but you can also define it by a generating set of vectors. But it will still be discrete. In particular, think of it this way: it's still a subset of the integer lattice. It cannot. All vectors are integers, right? So it cannot be denser than the integer lattice, right? Make sense? Good. Yes. Yeah, everywhere here, like it's still hard, right? I mean, we don't know how to solve this. I mean, when the factor becomes that large, then we know how to solve this problem in polytime. 2 to the power n by 2? 2 to the power n by, this is actually smaller than 2 to the n over 2. But something between that, yeah. So there is a trade-off. I mean, basically, in particular, the larger the factor, the easier the problem becomes. You can get a faster algorithm. So it's really a like smooth trade-off in this entire range, right? And I mean, this is like so pretty with this problem. I mean, you can teach a whole course on just this problem. Actually, we do that basically because it's so rich. I don't know of any other computational problem that has this range of kind of what you can say about this problem, right? But this is not the topic of this talk. But so we want to really understand what do we actually mean when we say hard, right? When we are talking about this world, we are saying no polytime algorithm. But I want to really kind of understand this slightly better, right? When we say P not equal to NP, we mean SAT has no, P not equal to NP implies SAT has no polytime algorithm because SAT is NP complete, right? I mean, but then what is well studied now, it's been almost 20 plus years since this has been studied, like what is called the exponential time hypothesis, where we make the assumption that 3SAT has no sub-exponential time algorithm. So that's a much stronger assumption than this one, which says that it has no polynomial time algorithm. Now we are saying that the best algorithm has to be exponential. It's 2 to the Cn for some constant C, right? So this is a very widely believed assumption. I mean, in particular, for so many years of research, I mean, we've not been able to find a better algorithm. So we believe that this is hard, and kind of we base a lot of conclusions on this assumption. And then there is an even stronger assumption, which says that, which is called the strong exponential time hypothesis, which says that the constant in the exponent is essentially 1. Basically, it says that SAT has no 2 to the 0.99 n algorithm, n time algorithm, and I can replace SAT here by KSAT for a large enough k, and still the same assumption holds. So if you talk about what people believe, I think ETH is believed probably a little bit more than SETH. SETH, there are people who might contest it a little bit, like say that this might or might not be true. But I think no one really contests that ETH probably. Good. So let's look at this picture again. The worst case to average case reduction. Now the best algorithms for n to the k SVP, based on all our understanding of this problem, are still exponential in n. So the best algorithms run in time exponential in n, no matter what the constant k is. Like obviously, the larger the constant k, the smaller will be the constant c. So there is a trade-off there, but these are still exponential in n. So this is the best state-of-the-art algorithm for this problem. Runs in time something like 2 to the n over 2k. So as you can see, if k becomes larger, this constant becomes smaller, right? And there is also like SETH hardness of SVP known for this, but this is for near exact SVP, right? Now, if we ask about what we can say about these reductions when instead of poly time, we allow, let's say, 2 to the epsilon n time. And here think of epsilon as a really tiny constant, let's say 0.01. So that means that when we start with the 2 to the Cn hardness assumption, let's say that we assume that whatever is the best algorithm that we have for SVP, that's kind of, we cannot really improve that, we've tried hard enough, and we believe that this is really correct. And then what can we conclude about LWE? So if we allow 2 to the epsilon n time for this reduction, then that would mean that LWE is hard up to a factor 2 to the C minus epsilon n. Just the same similar way as we conclude, like as we do for NP hardness reductions, we can do the same here, and we basically get that under this assumption that n to the k SVP cannot be solved in better than 2 to the C n time, we get that LWE cannot be solved in better than 2 to the C minus epsilon n time. So this brings us to the main statement that I want to make here, which is like talking about these problems where we allow ourselves more than polynomial time. So remember that this was our polytime world, and now when we allow 2 to the epsilon n time, the picture shifts. This is what we can show. So there is a co-AM protocol when the factor gamma is a constant. Instead of square root n over log n, we get a constant factor. But I am allowing this much time. So there is a co-AM protocol where the verifier runs in time 2 to the epsilon n, and we can get a co-AM protocol for SVP with approximation factor a constant, right? And similarly, we can what we can get in the 2 to the epsilon n world, which we are not able to get in this world, is also a co-MA protocol. If you don't care about the distinction between AM and MA, you can just forget about that, but like essentially we can improve that to co-MA instead of co-AM. And then for co-NP, we can get we can basically solve SVP square root log n, basically basically the complementary problem, the negation of SVP with factor square root log n in co-NP. I should not say co-NP here because we're not talking polynomial time. The verifier is really epsilon n, but just to be consistent, I'm kind of calling it to co-NP. So if strictly speaking, that's not really co-NP. And then what is very interesting is that if we allow this much time, we can actually start with a harder problem in some sense, right? We can start with SVP with square root n factor, and from that we can get the hardness of SIS, which means we can get one-way functions assuming square root n SVP is hard. And similarly for LWE also we can get a square root n factor improvement. We can start with n approximate SVP, and we can get that LWE is hard if we allow ourselves 2 to the epsilon n time. So in particular, across all these reductions, we are improving by a factor which is something like square root n, roughly square root n, if we are allowing ourselves 2 to the epsilon n time. Yes, correct. Yes, I mean, I'm just thinking of the reduction in this much time, so that the conclusion that we get. So in particular, let's just take a look at the reduction for LWE. Earlier we had a polytype reduction from n to the 1.5 SVP to LWE. What it meant is, let's say that we believe that n to the 1.5 approximate SVP is 2 to the 0.067 n hard. This is just plugging in the best algorithm and assuming that that's really the best possible, and that would give that LWE is 2 to the 0.067 n hard, right? Because basically, but now since we have a harder problem here, we can make a stronger assumption for this harder problem, and our reduction is taking this much time, so we'll shave off that factor, but we still get a better conclusion basically. So just by changing the perspective slightly, we can essentially revisit the reductions and kind of get something better. Of course, I mean some of these reductions actually when you allow that much time, it's not so straightforward. It doesn't carry through immediately. You have to kind of work a little bit. For this talk, I will focus on the reductions where the reductions or the results which are kind of the simplest, which are easy to understand. So I'll just show some of these results. So in particular, one result that I will show is this co-AM protocol. So let me just say what essentially we are interested in. What is for example co-NP. What we are interested in is that the prover Arthur sorry this is no picture yeah. So this is a prover. This should be Merlin. yeah. So the witness Merlin Merlin sends the witness, and then Arthur wants to output. I mean, I think everything is fine except I should have said here Merlin. That's but other than that, yeah. So what we want to show is that the completeness, which is that if the distance of the target is large, right? The distance of a target from the lattice is large, then we want to say that there exists a witness W such that the verifier on seeing W and the input would output far, right? I mean, that's the completeness property. And soundness is basically if the distance is small, then we want to say that no matter what witness what witness Merlin produces, the verifier will always output close, right? That's what we want to say in the NP setting. Oops. Oh, this is like converted to PDF, is it? Oops. Oh, why did that happen? It was showing fine on my screen.
Do you want to connect your computer? I might have the...
Okay. Yeah, I think so.
I mean, we can just, because you may not be happy. But the rest of it is actually...
Oh, rest of it is fine, is it? Is it just that? Okay, then I can live with that. I think it's fine. No, it's okay. This is okay. It's okay. I think we can skip that slide. It's fine. If it's just that, then it's okay. Okay. Oh no, this is again also coming like that. Sorry. Okay, okay those two. Okay, then let me skip to the next one.
I'm also wondering if this is just an image. If I just do this, it's better, right?
I think.
Okay, now that's true. So I think it's readable now at least.
Yeah.
And there were only two.
Okay. Okay, so in the co-AM setting, which is the setting that I'll be talking about, basically Arthur sends a random message in the first round, and then Merlin produces a witness, and then Arthur is supposed to basically run the verifier on the input and the witness. This is a standard setting, right? And then basically say whether it accepts or rejects, right? And for the completeness, what we want to say is that there exists a witness such that the verifier basically says that this target is far, or outputs basically far. And for soundness, what we want is that no matter what the witness is, the verifier will output close with high probability, right? And here it's not here since there is randomness in the first message, so you don't output far or close with probability 1. You basically have a certain error. So think of it as, when I say with high probability, you can think of it as 2/3 or 1/3, or you can think of a larger probability. Doesn't really matter. Okay, so I want to talk about a co-AM protocol actually for SVP instead of CVP. So I was just mentioning CVP, but I'll actually present for SVP because it's just simpler, right? So here you are given as input the lattice basis, and let's say T star I denote as the shortest vector in the lattice, and consider the ball that is centered at 0 of radius square root n, and the ball that is centered at the shortest vector but also with the same radius, right? And when this shortest vector is far from the origin, like basically all the lattice vectors are pairwise far from each other, essentially, which is the same as saying that the shortest non-zero vector is large, then you can see that these balls are very nicely disjoint, right? I mean, they're kind of far apart and disjoint. We're looking at balls of radius root n, and the target, sorry, not the target, this is the shortest vector is at a far away distance, 10 times square root n, right? Whereas when the distance between the origin and the shortest non-zero vector is much smaller than square root n, think of it as epsilon times square root n, then these balls have a good overlap, right? The balls overlap quite a bit. So in particular, the volume of the overlap over the volume of one of the balls is kind of significant. Actually, in n dimensions, it's not very high, but this ratio is still like 2 to the minus epsilon squared n, something like that. So it's visible, at least in the exponential world, the overlap. So what it means for the protocol, my prover is always Earth. Okay, so what we do is we sample S to be a random vector of length at most square root n, right? And also we sample V, which is a lattice vector, right? So I mean, think of any sampling algorithm that would sample the lattice vector. There are known sampling algorithms. And then what Arthur sends to Merlin is S plus V. Not so much, no. So think of this like basically GPV or any algorithm that would sample some vector, right? And then what Arthur sends is S plus V, right? Now, if you see, when the shortest vector is large, then what Merlin has to do is Merlin has to guess what S is and what V is, right? And notice that if the shortest vector is large, so 0 and the shortest vector is far away from each other. In particular, if you look at these balls around all lattice vectors, they will all be far away from each other. So then Merlin can easily figure out what V is and then figure out what S is also, right? Because Merlin sees S plus V, and Merlin just finds the nearest vector, which Merlin can easily do because these balls are really far apart, right? I mean, these balls are square root n radius, so essentially bigger than like S lies within the vector S. So this V plus S is essentially lying in a ball around V, around the vector V. So Merlin can easily figure out what S and V are. So in particular, Merlin will always give the correct answer, right? This is easy, straightforward. But when they are close enough, no matter what Merlin tries, Merlin will always be confused between, let's say, the vector V and its shift by the closest vector, because this S, the length of S, is much larger than the distance of V from the nearest vector. So there is a huge overlap between the ball around V and the ball shifted by the closest vector, similar to like the overlap between 0 and T star, right? I mean, this is similar to this ball. So there is no way that Merlin will be able to figure out. In particular, the probability that Merlin will hit the correct S happens with like probability 2 to the minus epsilon squared n. So Merlin is wrong with probability at least this much. So which means that if we allow ourselves enough time, then we will figure out the difference between the yes case and the no case. So, and this same idea can be used to also see the reduction from 1 over epsilon SVP to bounded distance decoding, and hence to LWE, because there are standard reductions from bounded distance decoding to LWE in particular. This was one of the main results shown by the paper that introduced LWE, the paper by Oded Regev. So I will not talk about the reduction from bounded distance decoding to LWE, but let me say how you can use the same idea to get from 1 over epsilon SVP to BDD. So what you have is the input is the lattice vector L and T star is the shortest vector, and you are looking at these balls. Again, the same argument, right? If T star is far apart from 0, if the shortest vector is long, then these balls of radius square root n around 0 and T star are disjoint and in particular very far away from each other. But if it is if T star is short, then these balls have a huge overlap. And so what we can do is we can replace Merlin by a BDD oracle, and we will still do exactly the same job. In particular, remember that what we needed to do was that in the far case, we wanted to figure out what V is, which was essentially solving the closest vector problem, and under the promise that the closest vector is quite close to the lattice vector, which is true here because the shortest vector is large. So if the shortest vector is large, then clearly the length of S is much smaller than the length of the shortest vector. So the BDD oracle promise is fulfilled, hence it always gives the correct answer, right? And if the shortest vector has a small length, if it is at most square root epsilon times square root n, then this BDD oracle, the promise is not fulfilled. It might not behave correctly, but no matter how it behaves, we again have the same thing, right? BDD oracle will just not be able to figure out the correct answer, so it will be wrong with probability at least 2 to the minus epsilon squared. And exactly the same argument. In the no case we are talking about something weaker than Merlin, so of course the same guarantee still holds. Good. So that essentially, those were the two results that I wanted to show in the picture. These are kind of very simple ideas that I wanted to present. The other ideas are slightly more involved, so I didn't think that this was appropriate for this talk. But now I want to get to a third aspect of this talk, or the third part of my talk, which is essentially I want to point out a concern. Even when we talk about these reductions and we allow ourselves exponential time and whatever, there's still a concern with this reduction, and I want to talk about an alternate viewpoint that kind of partially at least alleviates this concern. So let me say what I mean. If you take a very close look at how these reductions look like, in these reductions from worst case lattice problems to the average case lattice problem LWE, so what happens is you start with a polynomial approximation of SVP, and you get to some kind of, so BDD again with the similar polynomial factor alpha, and then you reduce that to LWE. But if you look at the reduction, it reduces to LWE in the same dimension n, but the modulus that you get when you look at this reduction, that is actually exponential in n. And then there are other results. In particular, there is this result by Brakerski, Langlois, Pikert, Regev, and Stele from 2013 that basically shows that you can start with LWE with dimension n and modulus exponential in n to LWE with dimension n squared and modulus polynomial in n. If you compare this and this, you notice that the amount of information that is there, if you think of the entropy of the secret, that basically stays roughly the same. So, but we really care about kind of P being polynomial in n, because we eventually want to kind of use this in cryptography, and we want to kind of reduce this to the decision problem, for which we really need P to be polynomial in n. But that means that we start with dimension n, we end with dimension n squared. So even if we talk about kind of these reductions, and so on, we say that we have a worst case to average case reduction. What does it mean in a fine-grained sense. What does it mean? Like, okay, so notice that the best algorithm for LWE run in time something like 2 to the n. So you have a 2 to the n times log p divided by log n if you really care about the exact factor. So this is the result by Blum, Kalai and Wasserman from 2000, and it's still the state of the art. This is the best algorithm for solving LWE, which is roughly exponential in n. But if we look at the best possible conjecture that we can make about these problems, we can say that these problems are exponentially hard. They run the best possible algorithm runs in time like 2 to the constant times n. What does it mean about LWE? We would conclude that LWE in dimension n squared cannot be solved in better than time 2 to the n, which in particular means that if you just change n squared to n, you would essentially get LWE cannot be solved in less than 2 to the square root n time. So even if we make the strongest possible assumption here, what we get for LWE is not super strong, right? I mean, this is 2 to the square root n. So which is the gap between what you are able to conclude from these worst case to average case reductions and what you want to conclude, which is that the algorithm that you have is really the best possible, is huge. This is not very, this does not seem very satisfactory, right? I mean, this gap in particular, and if you look at kind of if we follow this thread that people discussed in this NIST, there is a mailing list around NIST. I mean, this is a complaint that like people who don't like lattices keep coming up with. This is a complaint that is very popular. I mean, not necessarily in these words, but something around these lines keeps coming up. Okay, so we would ideally want to close this gap. I mean, like this gap between what is the best algorithm and what is the best bound that we can prove. We want to close this gap. So for this, I want to kind of change the perspective a little bit. Okay, so what does that mean? So let's look at what do we mean when we say that a crypto system is, let's say, 256-bit secure. This is a standard notion that we kind of want to think about. We can think of it as like the fastest algorithm for whatever dimension n takes roughly like runs in time 2 to the 256. We can kind of think of it that way. But we can also think of it this way, that no reasonably efficient algorithm, let's say something that runs in 2 to the 50 time or something, can basically break the crypto system with probability greater than 2 to the minus 200. This is also a reasonable statement. I mean, if we assume that our adversary has only a limited amount of time, let's say, then probably we are happy with this kind of statement. And this is, I guess, what is more closer to what we usually want, right? I mean, it can be debated, but let's say we go with this B, right? I mean, which is no reasonably efficient algorithm can break the crypto system with probability greater than 2 to the minus 200. So we can, if we take that viewpoint, then we can introduce this alternative measure of computational hardness. This is actually, a reasonably studied notion in computational complexity. I wouldn't say it's really popular, but at least there is some work around that. So which is looking at the maximum possible success probability for a probabilistic polynomial time algorithm that solves a problem. Instead of looking at the best running time, I'm saying I'll restrict myself to polynomial time and then ask what is the best success probability. For example, for SAT, this would be 1 over 2 to the n, right? You can just guess the solution. For Hamiltonian cycle, this would be 1 over n factorial. I don't know of anything better, for example, for Hamiltonian cycle. Even though you can solve it in 2 to the n time, if you kind of look at this, then the best success probability, then this changes the view of like the computational hardness of a problem to something that's different from what we were talking about earlier. Okay, so what does it mean for LWE? LWE, the success probability is basically you want to kind of you want to guess the secret or guess the error, like whatever the two, the success probability would be something like p to the minus o of n, right? And ideally we would want to get a lower bound that would look something similar in this setting, where I'm now allowing myself polynomial time and I'm asking what is the best success probability that I can get. So the question that we want to ask is, can we do much better? And I want to say that under a reasonable assumption about the worst case lattice problem, we cannot really do much better. So what is the best success probability that we can obtain for worst case lattice problems? For worst case lattice problems, based on my understanding of lattices from so many years, and this is something consistent with something I asked several people in the community. I mean, there's no proof for this, but the only algorithm that I can think of for solving SVP, if I'm given only polynomial time and I want to kind of maximize the success probability, is basically running this very famous Lenstra-Lowas algorithm and then guessing the coefficients. So what Lenstra-Lowas algorithm allows us is to essentially say that it changes the original basis into a nicer basis, where you can say that now the coefficient vector for the shortest vector is bounded. It's like all the coefficient vectors are bounded by something like 2 to the n, which essentially means that if you want to guess all of these coefficients, the success probability is going to be something like 2 to the minus n squared. You can do slightly better, so it's 2 to the minus n squared times log n divided by log n. So this is slightly smaller than 2 to the minus n squared. So I'm now saying that let's make this assumption that we cannot really solve SVP if I am only allowed polynomial time. I cannot solve it with success probability better than this. If you don't like this assumption, great, like basically break it. This is amazing. This would be amazing, right? I mean, so I mean, if you are like not happy with this assumption, that's actually a good news, right? I mean, then like let's try to find an algorithm that does better. That would teach us something about these lattice problems, which we don't know. So I'll call this a natural conjecture, and happy with the debate that like if we allow only polynomial time, then no algorithm can, let's say, solve BDD on an arbitrary n rank lattice where alpha is something like 1 over poly n. This is in time poly n with success probability better than 2 to the minus n squared log n divided by log n, right? So this is assumption that's coming straight away from the best algorithm that I can think of for this. And what we can show that if we make that assumption and we kind of revisit the reductions, the worst case to average case reductions, we look at it from this lens, like now we are allowing ourselves poly time, we are happy with losing like exponential factors in the success probability, suddenly like that's not a problem. We can actually get near tight reduction. So in particular, that conjecture would imply that maximum success probability for efficiently solving LWE looks something very close to what one would expect, which is p to the minus omega n over log squared n. Yeah, so there is so we can do a trade-off also. Like so you can get some nice conclusions still there. Probably weaker than whatever I have here, but yes, but you can get a trade-off. So I'm nearly also end of time. I mean, like so I'll end with a few open questions. I mean, I'll not really get into how to get that, but I'm really reusing ideas that are already there in the literature. So open questions find new very interesting implications of these conjectures that one can say are very strong, but getting interesting conclusions from these would I think force us to basically understand these conjectures better, right? So in particular, the first conjecture I am stating is lattice problems even with poly n approximation factor are exponentially hard. I mean, this is just based on our understanding of these problems for so many years. Actually, this is a problem that people have tried really hard. I mean, this is a problem that would really affect cryptography, so people have really invested a lot of time on. So I think this is a more believable conjecture in some sense. I mean, because more time has been invested in trying to break it. So of course one should try to improve these algorithms, but also if we are not able to improve these, let's make this conjecture and let's kind of get interesting conclusions from this. Like what can we conclude from there? So I mean, people have built this whole theory of fine-grained complexity starting with the 3-SAT. And this here is a much more relaxed problem in the sense like you are allowing a large approximation factor. So you can maybe reduce. Okay, so when I'm talking about implications, I'm not really necessarily talking about cryptography implications. I'm talking about computational complexity implications also. I mean, sure, sure. I was not necessarily suggesting cryptography. And then the other conjecture is like if I allow myself only poly time, then SVP cannot be solved with success probability better than 2 to the minus n squared, like ignoring those small factors. Can we get interesting conclusions from this? Can we understand this better? So, I mean, for example, a related question that I was kind of saying, I did not have it on the slides, is for example, Hamiltonian cycle. This is one example. The best polytime algorithm, if I want to talk about polytime algorithm and the best success probability, the only thing I can think of is like guess the cycle, which is like 1 over n factorial probability, right? Guess the sequence. But if you talk about the computational complexity of Hamiltonian cycle, you have a 2 to the n time algorithm. This is simple 2 to the n time algorithm. So in some sense, it feels like Hamiltonian cycle is in some sense maybe harder than SAT, like or Hamiltonian cycle with the n being with the parameter n being the number of vertices seems harder than SAT where we replace the parameter by the number of variables, right? Because there both are like the running time. The best running time is 2 to the n. The best success probability is 1 over 2 to the n. So can we kind of understand this difference a little better and kind of say what we can conclude? For example, can we get nice conclusions from the statement that Hamiltonian cycle we cannot really get a success probability better than 1 over n factorial if we allow ourselves polytime? So I mean, yeah, so I wanted to kind of put these questions out in the open and see if anyone has. Lattice dimension smaller than the security parameter, and then correct. I see. Okay. I mean, I have to think about because. No, so do I have to think. I'm just saying that there's a regime where something I see. Could possibly be said. Okay. Because in the standard setting, this will not help. I see. Yeah, sure. I mean, really open-ended, like basically what I want. Yes. So, sorry, I don't understand the question. As in SVP and SAT are both NP-hard. Yes. So they would have a polytime reduction with each other. Correct. But even then, okay, maybe not SVP, maybe it's Hamiltonian cycle. Yes. But you mentioned that Hamiltonian cycle problem, the best success probability that we are able to think of is like 1 over n factorial. Right. Whereas for SAT, it's just 1 over 2. So the problem there is that when you do these reductions, right, the reductions in the NP world, the reductions can have a blow up in the parameters. So in particular, when you reduce from Hamiltonian cycle to SAT, Hamiltonian cycle on n vertex graph would reduce to maybe n squared variable s sat instance. And then the conclusion anyway changes, right? N factorial, like n becomes n squared. So
does this mean we can have a, let's say, class of problems which can have similar success probabilities?
that's kind of what I'm trying to suggest. Yeah, I would like to say more than that. I mean, basically. So if there is something interesting that can be said, I will be happy to hear. Yes. Okay. Okay. I see. Yeah, this seems very similar.
Yeah,
I would
that
say.
sounds
Yes, I see. I mean, I'm definitely not claiming that this is the only time that this kind of statement has been made.
No, no, he's just pointing
Sure.
another direction.
Yes.
But also like they do something like Shweta was saying that they have to do some kind of complexity leverage. I don't remember whether it was exactly the dog square terms, but they have to do some kind of two security parameters.
Right.
Some kind of leverage.
So for example, this result that I was talking about, the reduction, right? One thing that we had to care about when we did this reduction is that I mean, I did not want to get into the details, but really when you do the standard reduction for worst case lattice problem to LWE, you make polynomially many calls to the oracle. But polynomially many calls is very costly here. So what we did was basically did this whole thing with a single call to the, and we are okay with losing like exponential factor in the success probability, that's totally fine. But like making more calls is not. So in that sense we had to change the reductions. Yeah.
So in the interest of time, let's take further questions to the coffee break. Let's thank the speaker. So as a small token of our appreciation.
Thank you very much, Shweta. Thank you very much.
All right, everyone. Last coffee break.
Good afternoon, everybody. And our next speaker, Siddharth Barman. He is currently Associate Professor at IISc. And he is also Mindtree Chair in the Department of Computer Science and Automation there. Before joining IISc, he was postdoc at Caltech, PhD in Computer Science from University of Wisconsin-Madison. Siddharth is recipient of ACM India Early Career Research Award 2023, Young Engineering Award by Indian National Academy of Engineering, INAE. He is also an associate of ISSC, Indian Academy of Sciences. His research lies at the interface of computer science and microeconomics, especially algorithmic game theory and fair division. Siddharth, please.
Great, thank you. Thanks for the introduction. Let me thank the ArtCS teams, in particular Shweta, for the invitation. Very delighted to be here at the inauguration of the center that promises to be both a catalyst and a glue for the growing theory community in the country. So extremely happy, and again, thank you for all of you. It's a Saturday evening, and I'm very happy to see such a almost a full class. So I'll talk about two complementary research themes, and the big purpose of my talk is to share some of the passion, some like the excitement I have for these two research themes, and I will give you a big picture idea of why I do think a lot of the TCS community, a lot of the students, and like a lot of the faculty here would find interesting application questions and techniques in these two spaces, in these two threads. But I'll do so by means of two results. I'll highlight the sort of big ideas I have, the big connections, by means of two very specific examples. The first will be about partitioning graphs, like a clean results of how do I divide vertices of a graph in a balanced manner, in an equitable manner. And the second result will be, so the first result will be from fair division. The second result will be from welfare economics, collective welfare, and what that will highlight is that how a principled approach, a very theoretically sound approach, can impact a very important real world problem. So the problem there, which I'll focus on, is called nearest neighbor search, approximate nearest neighbor search, and it is a workhorse. It's a primitive that's used heavily in data science applications. So it's used, for example, in ad display recommendation system. So Bing, for example, uses it for displaying ads. Spotify uses it for recommendations and so on. So I did a back of the envelope calculation, and I realized that even among the applications I know, it's executed around 100,000 times per second. So now I leave it to you to understand how many times would this primitive run by the time I finish this talk. So it's that scale at which this is done. And what I want to convey to you is that how very nice theoretical ideas impact such an important, improve such an important application. So these are the two results. I will sort of use them to highlight connections. I'll show how these sort of fair division acts like this beautiful banyan tree outside the hall, outside this building, and connects to many other branches in TCS. Before I go to such like the big picture idea, let me just give you trailers, teasers for these two results, so we have something to anchor ourselves with. So what is the first result? Equitably dense subgraphs. Here's the result. So this is joint work with Paratosh. It's quite a clean statement. So what I want to convey to you, and I'll do this in a fair bit of detail, is the following existential guarantee. What it says is that give me any graph G, simple and directed graph, and give me any count K, any integer K. There always exists, I can always in fact find one in efficiently, a partition of the vertex set. So I can look at the vertices, partition them into K parts, such that the edge density of every part is very close. And when I mean very close, I really mean very close. They're additively close to each other within a number 4. So two things, I'm not saying that the ratios are close, I'm actually saying that the density numerically is plus minus 4 of each other, and this is again a universal existential guarantee. For any K, for any graph, I want to convince you that such a partition exists, and edge density is just to recall, is the average number of edges within each subgraph. So here's a picture. So give me any graph, give me any count k. In this example, let's say this is k. What I can do is I can partition the vertex set so that if I look at V1, look at the number of edges within V1 divided by the number of vertices, look at V2 again, number of vertices divided by 2, yada yada yada. All these densities, so half the average degrees within the subgraphs, they're additively close to each other. They're plus minus 4 of each other. So, and just to pique your interest, this result has nothing to do with graph theory. It's actually not even combinatorial, and in fact it generalizes to much more beyond graph densities. It's just a placeholder for me to sort of convey a bit more abstract result. But we'll sort of use this as our example. That's polytime. Yeah. Polytime. Always exists, polytime. Yeah. N cubed algorithm actually. Yeah. Without even sort of much simple dynamic program. Okay, so that's result 1. That's a fair division result because you can think of it as fair division result where I'm partitioning the vertices of a graph among k agents, k entities, and every agent's valuation for what it receives is the edge density. And what I'm saying is I can always partition the vertex set equitably. Every one of these k agents is getting a set that it values within plus minus 4 of each other. Result 1. Result 2 again, as I said, is about neighbor search, nearest neighbor search. It comes from collective welfare. The idea is that how can you use this notion from welfare economics, this welfare function called Nash welfare, to improve diversity in these search results. And as I've already sold on you that this is a primitive, this is a building block that's used heavily in even modern things like RAGs, if you know what that means. It's things that are used to sort of prime large models. Used in recommendation systems, for example, Spotify's NOI is an ANN based system, so on and so forth. So a very sort of a real world impactful application. I'm sort of very happy that Microsoft in fact is testing this out. So it is likely that some of it or ideas from here will actually get deployed. So like a rare feat to have this sort of a end-to-end synergy from like good theory to like real deployment. So that's the second result I want to sort of discuss briefly. These are the two results, and again this sort of makes little sense right now. What I want to say is like does it improve? So it improves. So this is not a synthetic data set. This is an experiment we actually performed on Amazon data set, and when you start using the Nash welfare function, you see that you start getting better results. So if one searches for the word shirts and you're using this Nash idea, you get like a nice diverse set of colors. And if you're searching for blue shirts, you actually only get blue shirts and not like a diversity when it's not required. So this sort of dynamic idea that it lets you find diverse results when required and when not is something that gets executed by it. This picture will make much more sense once I spell out the details, but that's sort of the trailer I have. Okay, so as promised, let me step back now. I will use these examples to substantiate many of the observations I'm making here, but the next few slides are intended sort of for a broad TCS audience. Why should someone like this find fair division interesting? I mean, and my point would be to sort of connect it to many fields and sort of hopefully excite you to look at some of the problems, some of the open conjectures in the space. So the field as such has like really classic history. There's a 7th century Greek epic poem, Theogony, where there is a fair division algorithm, where there's a fair division protocol. In fact, there's a biblical reference to that. It's called the story of Abraham and Lot. You have a piece of land, you have to fairly divide it among two individuals, Abraham and Lot. And here's the algorithm. It's the so-called cut and choose protocol. Abraham looks at the land, divides it into two parts that he is indifferent between. So the large piece of land, here's a cut mark. Abraham is happy either with the left part or the right part, and then Lot comes in, picks among the two that he likes more. So it's an envy-free protocol, and this is a story from the Bible. There you go. That's sort of the genesis, if you will, of fair division. The mathematical study started in the 1940s, so even that has a rich history. The classic literature deals with problems like cake division. So cake represents divisible resources, things like land, water. And there's a lot of work in terms of market equilibria. And a very distinguishing feature of this work, which I think TCS should get inspired by, is axiomatic studies. So we will see this again by means of the example I promised. But what math econs did, which sort of something to get sort of take note of, is the fact that a lot of their objectives are axiomatically supported. So they do not just pick a maximization objective, or let's say a minimization one. They actually start with axiom. They say, I want a function that should satisfy these properties. This could be like fairness properties, economic efficiency properties, and so on. And based on these axioms, then they sort of identify the right objective to work with. And what we'll talk about, Nash welfare, is one such objective. So this study of axioms, again, quite classic, but it's something that we should learn from. Of course, elements of mechanism design, so truthful, strategic participants in fair division, like bread and butter of a lot of economics. The modern themes are, like, again, interestingly, are combinatorial. So this is like a big, like a lot of activity around this in recent days, certainly by computer scientists, and the focus a lot on, in contrast to classic results, is on combinatorial things. So for example, instead of dividing things that can be fractionally assigned, like water, land, a lot of new results focus on discrete division, like allocation of houses, kidney matching, or course allocation, and so on, or partitioning vertices, things that you cannot fractionally divide. A lot of work in discrete, of course, algorithms, complexity, so on and so forth. So a lot of new themes, a lot of classical themes, so it's a rich space. And this is something that I really sort of promised you earlier, like connections, like why should a general audience enjoy or take interest in this? And it has many. I already gave you a graph partitioning results, that will be sort of the focus of a large part of this talk, but even coloring problems, like the classic Hohenal-Semeredi theorem, which says that not only can I color a graph with, let's say, maximum degree plus 1 colors, in fact, I can color any graph with maximum degree delta, such that with delta plus 1 colors, such that every color class is balanced. They have the same number of vertices, so on. So this, you can think of it as a fair division, as a constrained fair division. You have chores, you connect chores that conflict, you partition them among delta plus 1 agents, so that every agent gets the same number of chores without any conflict. That's Hohenal-Semeredi. Looked from my perspective, that's a fair division result. So we have ongoing work with Vignesh, with like look at, let's say, weighted versions or other notions thereof. So coloring, graph partitioning, certainly a lot of connections to fair division. Even matroids, constrained fair division, you can think of it as like assigning independent sets of matroids to agents, captures things like house allocation and such. And there are recently nice results, like one that studies the so-called one equitability result in matroids, or even classic conjectures in matroid theory, like White's conjecture, have direct implications and connections with result, like certain fairness guarantees. Extremal combinatorics, again, extensively studied, but has found connections and implications within fair division. There's this nice result that shows that this Erdos matching conjecture actually connects with what is called quantile shares, a notion of fairness. And also there's this very prominent fairness criteria called EFX, which connects to rainbow cycle. I'm not giving you a lot of details. My purpose is to sort of like just have a slide with some names. Someone can take a picture and sort of look at it if you want to. Discrepancy theory, again, you can, now that I've said it out loud, you can just think of it as a fair division problem. Like vector balancing is a balancing problem. You're partitioning vectors such that like sum of vectors in one part, component wise, is close to the sum of vectors in other part. And so it is a fair division problem. And to quote Kabir, Jit Dekhun Tit Lal, so the last one is more my like biased perspective. It's not really how many people would say it, but like to me, even Caddis and Singer or Weaver's conjecture is a fair division problem. You are given a matrix, you want to partition the vectors such that the spectral norms are close to each other. You might call it cat and singer, celebrate it, but for me, it is a fair division where the valuations happen to be the spectral norm. So again, I'm wearing red color glasses, so the world does look red. And this is again a partial list. It kind of goes on. Again, most standard TCS, many applications, many connections. What I do want to say is that while it does connect very well, in terms of hammers, it actually is distinct. So for example, the consensus result actually is proved using topology. It's using a result from topology, the Boucher-Coulomb theorem, whereas discrepancy uses a lot of combinatorics like the Spencer's pigeonhole idea or SDPs or these Comlosh style convex optimization techniques. So it does bring in a new set of hammers, and it's worth considering. We will in fact look at an application of Sperner's lemma, but there are many, like fixed point theorems, this KKM theorem, so on and so forth. These are results from topology, and they do have applications in fair division, both the divisible classic settings and now in these new combinatorial discrete settings. So lots of new hammers worth trying off. Another technique that I do want to really highlight is like something that gets flipped, is that there are results in fair division that use markets for algorithm design. So let me say this again. So unlike the well-established algorithmic game theory paradigm where you develop algorithms in the service of economics, so you develop algorithms to find equilibria, there are now results which say that, oh, you can take a market, results from market equilibria, use that as a technique to design approximation algorithms. So there's this constant factor approximation known for Nash welfare. It actually does follow this template. So it uses the concept of Fisher market to develop an algorithm. So sort of a reverse brain drain, if you will. And of course, standard theoretical computer science, probabilistic methods, approximation algorithms, you name it, it does appear a lot in this literature. So lots of interesting techniques, lots of interesting connections, and what really sort of excites me about it, is it's a very fertile ground. There are open problems, like there are deers on this campus. It's everywhere. There's something called the EFX conjecture. To the students, look it up. It's a very pithy statement. You can explain it to your younger cousin who's giving boards, and do lose some sleep over it. It's that beautiful problem. It's a very succinct, very nice problem. You don't like someone in your hostel, tell him to prove it, and that'll be a remedy. There are many other sort of interesting questions, and talk about gaps, right? So there's this cake division problem, division of like a fractional resource, a resource that can be fractionally assigned, and there's a huge gap. The best known lower bound is something like n square, and the only known algorithm for it runs in that time. Yes, it's a tower of 6 n's. So if n is 4, you have 4 agents, that's going to take more than the lifetime of the universe to run. Nonetheless, it's a finite time algorithm, and the lower bound and the upper bound are by no means close to each other. So large gap, good open problems. I could have given a 1-hour talk on just the open problems on it. They're nice surveys. Again, I do invite you, the students, to take a look and sort of go through it. So with that, that's the big picture landscape. The many things I mentioned are sort of quick with my time, but what I do want to do is focus on these two results and sort of convey some of these observations a bit more precisely. So let's start with the fair division results, and then after that, however much time I have, I'll focus on the collective welfare part. So equitably dense subgraphs, this was the statement I told you, any graph, any count k, I can always find a partition. So give me a social network, however large, 1 million people in the social network, give me any group count k, I can always find k groups such that the average number of friends within each group is plus minus 4 of each other. Additive bound, and again, polytime, I can find it. There's an efficient algorithm as well. Do notice, just to make a few remarks, I'm not looking at an optimization problem. I'm not telling you that the densities are going to be large or small. All I'm saying is that the k parts will have densities close to each other. So it's really a balancing problem and not an optimization one. Yes. It does. It's just looking at one part and whatever the density there is. Yeah. No, good question. It's open question. So what I can tell you, and you'll actually, I'll repeat it since you have asked, if you give me a Hamiltonian graph, then I can guarantee that each VI is connected, but not in general. Yeah. Okay. So that's the edge density. Again, Saturday evening, let me give you examples. So here's a graph. It has 13 plus 3 vertices, a complete graph on 13 vertices, a complete graph on 3 vertices. Number of edges is 13 choose 2, that's 78, plus 1 plus 3, 82 edges. And let's say I pick k as 2. So I want to partition it 2 parts so that the edge density of the paths are close to each other. This is not a good attempt. So if I take these 3 vertices as V1, all these orange vertices as V2, the edge densities, if you do the calculation, are more than 4 away. But I could be slightly smart, take these 10 vertices, so 7 plus 3 as V1, take these 6 vertices as V2, and the edge densities are again exactly the same. So here it happens to be connected, but in general, like the question that she has asked was, can you guarantee that each V1 and Vk are connected? In fact, balancedness is also an additionally nice thing which we don't have an answer to. So that's the result in more generality. Let me just drop the mic and not create suspense. As I said, the result has nothing to do with graph theory. It's not even combinatorial, strictly speaking. It comes from cake division. Like, nice to hear cakes on a Saturday evening. Here it is. And yes, it's not. There's a recent work by Hussaini, Vishwaprakash, Sethia, and Yadav that improves it to 1, and 1 is sharp. The proof has nothing to do with graph theory. The result, of course, yeah. Yeah, I mean, even on a Saturday, I shouldn't have made this mistake. Yeah, the proof is not graph theoretic. It's for the equitability, they get it to 1. This thing, instead of 4, it's 1, and 1 is right. Okay, cake division of a divisible resource, classic stuff for this literature. So what is a cake? It's represented, it models this interval 0, 1, right? So it's a divisible heterogeneous resource. Divisible in the sense that if I have n agents, I can give every agent an interval within 0, 1. So like a piece of the cake, an interval 0, 1. And heterogeneous because the agents will have different values over different parts, different intervals of the cake. So here's a quick illustration. 0, 1, that's my cake. Take any interval, take any agent A among the n1s. I have a value function associated with the agent. So it has some value, let's say non-negative value Va for this interval I. And similarly, if you give this agent a different interval j, it will have a different value again, Va of j. So Va is a function that maps intervals, baby intervals within 0, 1 to non-negative numbers. That's the valuation I'm going to look at. I have n agents, I have one value for all of them. So what I want to do, what is the cake division problem, is that I have n agents, they have these valuation functions that map intervals of 0, 1, 2 non-negative numbers, and I want to find n intervals in the cake. That is, want to look at 0, 1, make n minus 1 cuts, and hence I get n intervals, then assign them, permute them among the agents, such that it's fair with respect to these heterogeneous valuations. And a standard notion here is that of NV freeness. So what I said again, let me repeat. What I want to do is look at this cake and I make some n minus 1 cuts. So I get, let's say, an interval IA. I give it to agent A. I get another interval, the second one from the left. I give it to agent B and so on. So partitioning the cake means making these n minus 1 cuts, and the resulting intervals are assigned, permutate among the n agents. And the requirement, the classic quintessential notion of fairness in this field is called NV freeness, and what it says is that you divide the cake and then assign the intervals such that no agent envies anyone else, i.e. every agent A looks at the interval it has received, so looks at the value it's gaining from the interval assigned to it, and that value has to be at least A's value for any other interval IB. So do note, both sides of this inequality are evaluated with respect to i's valuation, the valuation that maps intervals of 0, 1, 2 non-negative numbers. It says that I is happy, satisfied with the interval assigned to it, and at least as much as any other interval. So the right hand side is IB left, and this inequality should hold for all pairs of agents A and B. So every agent is NB free, looks at a piece of the cake and says I don't want it.
So these n intervals are given to you?
No.
So how is this condition function specified?
Let's, for the time being, be mathematicians and just say it's a function. Yeah, it's usually done through what is called the Robertson Webb query model, but I'm only going to tell you like a existential guarantee. So there is a function VA, that's a well-defined function. I'm not looking at a computational problem as of now. Yeah, just an existential guarantee. Does that? Okay, great. So just to repeat, the intervals are not given to me. The point is to make these cuts, find the intervals and assign them such that this NB freeness holds for every pair. Okay, very well studied. Like these are books from even the 80s. They're like 4 more. I just ran out of space on the slide. So, I mean, a lot of literature around it, a lot of good math, very interesting applications like border dispute resolution and so on. So, rich literature, rich in terms of application, so well-studied theme. And again, interest of time, a lot like raise suspense. Here's the punchline. Beautiful result by Sue. And what it says is that this might look very surprising to you, but such a division always exists under very mild conditions on the valuations. In fact, you give me a valuation function that's non-negative, continuous, and it satisfies what is called the Hungry condition. I'll spell out this condition in a minute. Very mild 3 conditions, and such an NV-free division is guaranteed to exist. Do notice, all I'm assuming is non-negativity, continuity of the VAs as a function of intervals, and this Hungry condition, which I'll spell out in the next slide. But in particular, VAs do not have to be monotone. They do not even have to be additive. So I'm not saying that value of 2 intervals that are right next to each other is the sum of the values of the individual intervals. Any valuation that satisfies this, such a division always exists. Give me such valuations, there always exist n-1 cuts and the reallocation of the intervals such that every agent is NB free. And the proof is literally by that picture. It's called Sperner's lemma. I'm very short on time, but yeah, there are beautiful YouTube videos on it. Again, next time if you're watching a reel, stop yourself and watch this proof. Yeah, you'll thank me. But this theorem statement is here, but very nice, super elegant proof, and that can be explained really in a very nice video. So the Sperner's lemma with some labeling ideas really give me Sue's like universal existential guarantee that give me a cake, give me any number of agents n, give me these values, valuation functions, the continuous, Hungry, and non-negative, such a thing is guaranteed to exist. Okay, what is the Hungry condition? Let me sort of not delay it further. All it says is that if you give me any partition of the cake, it will value some interval over the empty one. So let's say that you value the empty interval at 0, you make n-1 cuts, you have n intervals now. Some intervals can in fact be empty. You can make 2 cuts at the same point, but there will be a non-empty piece that the agent values at least has a positive value for it. So the agent is hungry. There's some part of the cake she'll like than any other piece. So that's the technical condition, and you actually, it really pops out of Sperner's lemma. If you see the proof, you'll see why it makes natural sense. But that's the Hungry condition. Let me repeat myself. I do not require monotonicity of the VAs. I certainly don't want additivity or any other structure from the VAs. Any continuous function that satisfies this condition, the Hungry condition, Sue's lemma is applicable. Yeah. Yes. They are all valued at 0. That's the term valuation, like implicit. Yeah, it's a condition. Let's say. Yeah. and they are indistinguishable. Yeah. Yeah. Yes. Yeah. That's Sue. I started with a graph and I've ended at the cake. Good journey. But if you think that's sort of too simple, let me sort of temper our ego a little. There's a nice result by Stromquist, and this addresses the question that was asked, like how is this given? So even if it's given in a very natural query model, forget polytime, there's no finite time algorithm for it. So I can give you, like, for example, rational valuations at rational at all rational, and you'll never be able to find it, like sort of an adversarial Stromquist thing. So this result holds if I'm forcing this condition that I'm making n minus 1 cuts. There's a more relaxed model where you make many cuts and then give unions of intervals to agents. And this very complicated algorithm, Aziz and McKenzie, works in that relaxed thing, but that's the running time. Improve it, and I'll like you more. Unconditionally. It's not a hardness result. There's no finite time algorithm for it. It's actually like an irrationality. It's like I can make sure it's at a point where you keep answering and I keep moving so that you, for infinite, like you keep having smaller and smaller but positive NV. I mean, if you think convergence, closeness and open set arguments was an unnecessary course in your undergrad, read these proofs and you realize like why closeness really matters. This is actually, no finiteness rests on the fact that if you can I can infinitely make you walk smaller and smaller steps in an open set. So again, very interesting stuff. You regained appreciation and respect for topological concepts. These are algorithmic things, but the existential result stands. And this is where I want to get to. That's my end goal, the graph partitioning. And I am actually going to give you pretty much the entire proof. I'm going to start from there and establish this graph theoretic result, and in fact address a few of the questions that were raised like during the conversation. Okay, so how do I do this? Here's the idea. Light bulb is here. I have this graph, I have this integer k. What I'll do is I'll look at my cake, 0, 1, and let's say I have capital N vertices. That's the number of vertices I have in the graph. What I'll do is partition my cake into these baby intervals, each of length 1 over capital N. So I have exactly capital N contiguous intervals, and I'm going to associate every vertex of the graph with one of these intervals. Doesn't matter in what way. So let's say the vertices are indexed 1 through capital N. Just associate the first baby interval with vertex 1, the second baby interval from, oops, shouldn't have done that. It went out of the full screen mode.
That's okay, I got it.
Thank you. So, yeah, the first interval with the first vertex, the second baby interval with the second vertex, and so on. So I have capital N of these small baby intervals, each of equal length, and I just associate all the capital N vertex one with each. So what do I have? I have the density function defined for me. What I'll do is I'll use that to define a valuation over the cake. So I have this rho function that I'm inheriting from the input graph. From that, now I'll define a function over this cake, in fact over intervals of this cake. So let's do that. So take any interval. Let's say it starts at this baby interval between s minus 1 by capital N and s by capital N. So that's the baby interval associated with the sth vertex, and it ends at the interval associated with the tth vertex. So it's completely covering, integrally covering the baby intervals of vertices s plus 1, s plus 2 to t minus 1, and it's partially covering the intervals for s and t. I'll just do a linear interpolation of the density function. That is, the value I have, I'll define this function for any interval as the following. So it looks complicated, but just follow me along. All I'm saying is that the vertices whose intervals are completely contained, I'll take them integrally, And the ones that are fractionally contained, I'll take them, let's say, with probability proportional to however much the overlap is. So if this R is this random set where vertices s plus 1 to t minus 1 are always there, vertices s and t are included with some probability proportional to however much the interval is being covered. Whatever the expected value of the density function is, that's my f. This is called a multilinear extension of a set function. There's some technical reasons for this particular choice, but for the purposes of the talk, all you can think of is that I started with a density function defined over subsets of the graph. So in particular, it is defined for contiguously indexed vertex subsets. I can use that to define fi. Just linearly interpolated. The interpolation ensures that this gentleman right here, f is continuous. Yeah, I mean, what I just said kind of holds true. It's just an extension. So in particular, if I look at an interval that starts at an integer multiple of 1 over capital N and ends at an integer multiple of 1 over capital N, the f value for that interval will be exactly equal to the rho value of the vertices that are completely covered. So if x was in fact s minus 1 by n and y was t by n, f, the function of the interval, would be exactly rho, the edge density of vertices s, s plus 1, s plus 2 and so on. So Shreyas had asked a function about continuity. So what I'm saying, what you could have done was taken a Hamiltonian path and indexed him in such a way, but I'll get to it in 1 second. But that's the function I have defined over a cake. So I started with a set function rho, the edge density function. I've landed at a function f that's defined for every interval of this cake this way. Okay, continuous function, it's non-negative because rho is non-negative. Can I apply SU? No, it's still not hungry, right? So you could have looked at a partition where the edge densities are all 0, so it's not a hungry condition. I hate to admit it, but this took actually a few days to figure out. Here's the fix. You just pick an arbitrary small epsilon and add the length function to it. So you have this function f, and now you add a function length of I, which is positive for every interval of like every positive length interval, very small epsilon. Just add it and you have this new function v, and this is the valuation function I have. So I started with a cake, I had this count number k, I started with a graph with a count k, I've now constructed a cake, and what I can do is consider k agents, all of whom have the identical valuation v. They have the same value function. So it's a special case of SU in fact, where all the agents end up having the same value function. And this sort of distinction really helps me get a polytime and beat the impossibility result I mentioned earlier. So I'm going to invoke SU. In fact, I'm going to invoke it with k agents, all of whom have the same valuation function v. Okay. Yes. 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 It will be 0. Yes. Yeah. Okay. X and Y are in the same thing. Then whatever the length, let's say they cover 1 over 2n. So you'll include this. So right now I'm only defining v. What you are talking about is like a rounding error. Right. So if both of them are in the same baby interval, you will still include it with some non-zero probability. For right now, it's just a definition of v. It doesn't have to be like sort of consistent across like contiguous intervals. Okay. It's a very subtle point. I am going to punt on it, right? Like the fact, what you are saying is actually going to matter. This is the advantage of giving talks versus writing papers. I can skip details I don't care for. But just to answer this question, like if they are very close, what you can assume is that n is like k is less than n by 2. If it's n by 2, you can just take pairs of vertices and get the edge density 1 or 0. And If it's n by 2, you can argue that all of them will have sufficient length. So the end I star, which is about to show up, you'll never be in this case. You can sort of do some pre-processing for that. So, okay, I have this valuation. I apply SU with k agents that have the exact same valuation function defined on the cakes. And what SU guarantees me is this existence of this magical partition I1 through Ik star. Since the valuations are identical, the allocation doesn't matter. I can give any interval to any of these k identically valued agents. And what do I get? I get that the values of all these intervals under this function V are the same. Let me just summarize. I had my density function rho. I got extended it to find a function on intervals of the graph, intervals of the cake. I changed it a little bit to get the hungry condition, and under this V, I have this NV free allocation guaranteed to exist, which satisfies, I am scared of doing this, but satisfies this thing, that every agent is NV free and they have the same valuation. So value of all the intervals under V is exactly the same. So every agent is indifferent, the k agents are indifferent among the k intervals. Great. I'm home actually, not literally, but at least in the proof. So what this V means is that, so this equality, I can just spell out what V is. It's F plus epsilon length, so I have this equality. Note that length, the cake itself is 0, 1. The length cannot be more than 1. So there's an epsilon additive term. Great, but what do I get? I get that even with respect to the extension I had defined for the density, up to epsilon, I am very close. Okay, great. F is the proxy for the rho function defined over the cake, and all I have to now do is, as Professor Jayakumar was pointing out, round. I have intervals which really, if it's starting and ending at an integer multiple of 1 over capital N, it actually does exactly corresponds to a vertex subset, but you could have some like that line in between, but not a big issue at all. So if it starts here and ends here, what you do, here's a simple thing, you just shift it to the left. So if I star was for agent I, you give Vi, define Vi star, you just start at S and end at T minus 1. Just literally round it, shift it to the left, and you will get from these k intervals, you will get k subsets, V1 star, V2 star, Vk star. Notice that not only am I giving you V1 star, V2 star, Vk star, I am telling you that they actually are indexed exactly in the right order. V1 star will have vertices 1, 2, 3 up to some number. V2 star will start at the next vertex and again stop somewhere, and yada yada yada. So if this was a Hamiltonian path, just to answer your question, this would be connected parts of the path. Okay, that's V star, and the final thing that's left, again, this is property that I got because I was careful in defining my extension, that this function and this function, this apply to intervals and this apply to the rounded subsets, are only going to be 2 away. So just plug it in. I mean, you have the top thing, you can drive epsilon to 0, and this is what you get. This 2 is why you get a factor 4. You can improve it, as I mentioned, recent work by a bunch of co-authors, in AMAS, I think. Okay, that's the result. That's the proof. Cakes lead to graph partition. Yes. You can carry out with any epsilon. Yeah. Not any epsilon small enough, sufficiently small. You can argue that the density function, right, will take some sort of rational value. So pick an epsilon that's small enough that if the inequality holds with epsilon, it has to hold without epsilon. Sufficiently polynomially small epsilon works. Yeah. Does that answer your question? Yes, it does. But small enough, like 1 over poly in capital N will suffice. Yes. I will give you a stupendously generous result in 2. I've actually fooled you into thinking it's a graph theoretic result. I never used the fact that it was a density function. I could have done with any discrete set function. I've actually given you the proof for the general result. I just use the graph as a sort of toy in some sense. Like, so 2 slides and I'll answer your question. But you've actually seen the general proof. So notice just to repeat the question, I've never used the property that the row I started with was the density function. The only thing was that rho and f are additively close. That's like a Lipschitz property of the set function. So I'll give you a general statement and we can sort of discuss this one more time. So there's a polytime algorithm, and just to speak on that, it has nothing to do with density function. Here's another invocation. Instead of rho, you start with the cut function of a graph. And the result now says, give me any graph. Let's say it has maximum degree capital delta. I can always partition it among any k vertex subsets, such that the cut functions are almost 4 delta each other. The 5 comes because I do want non-emptiness property, a technicality that I'll skip today. But what it's saying is that, okay, look at this graph, these red vertices, they have like 1, 2, 3, 4, 5 edges going out. Look at the blue ones, they have 4 edges coming out. So you have these parts, and if you look at the number of edges that are going out, they are very close. They're just 5 times the maximum degree. Here's the general result. In fact, I have proved this to you. I just sort of didn't tell you I'm proving this. Give me any set function, f. So it's a set function. So it's defined over subsets of a ground set capital V. The only property I want is that it's non-negative. Again, only property I want that is it's non-negative. It can be non-monotone, doesn't have to be submodular, subadditive, nothing. Any set function under God's green earth, as long as it's non-negative, for any k, I can find, not find, but again, oracle question, there exists a k partition of the ground set, so that the function values are additively within 4 of each other with the scale factor, the Lipschitz constant of f. So Lipschitz of f is just that how much does the function fluctuate if I add or remove one element. If that is small, which happened to be 1 for the density function, happened to be maximum degree for the cut function, this is it. So yeah, as I said, like very general things, and I hope to find other applications of this. Okay, I'm done. I have like roughly 10 minutes left. I will like quickly go over the other thing. If you have questions, I'm happy to answer. I'll switch gears and talk about a bit more applied work on this welfare functions. Excellent. So Nash welfare, Nash social welfare for neighbor search. So this result has 2 parts, and my only point is to tell you the pillars. Once they are there, the arch, you can sort of make it for yourself. But at the same time, here's the big picture that I really want to convey through this part. And this is more like why is this sort of direction interesting? Why is this program interesting? And the idea I want to convey, modulo all the technical details and the specificities of the result, is that it is very interesting to now look at algorithms as economic policies. There's a lot of talk about using AI ML tools for socially sensitive decision making. Things like algorithms are deciding on whether loan applications get resolved, admission policies, things like filtering CVs. So there are lots of algorithms that are really impacting people at large. They are impacting the same way as economic policies do, the same way as like tax policies or tariff policies impact a large population. Algorithms are in the same realm now. Also, like economic policies, these are not very engineered constructs anymore, especially with very large AI models. They are learned from data. They have lots of black box components, so they're not extremely engineered, like hard-coded steps. So even then, like this sort of synergy or the sort of similarity between economic policies and algorithms show up. So the big idea I have, the thesis that I'm sort of posing in front of you, is that the same way as, let's say, World Bank looks at an economic policy, looks at how decisions will impact populations at large, we should look at such algorithms, especially when they're making socially sensitive or responsible decisions as economic policies. And this is not just sort of a meta statement. The example I'll tell you is a very concrete instantiation thereof. I'm going to look at a primitive, this nearest neighbor search, and kind of actually use a very specific construct from welfare economics to sort of quantify that. And in all of these applications, and the one that I'm about to show is one exemplar, but the point is that the algorithms decisions, and when I say algorithms, I also mean like AI models or machine learning tools, they do induce utilities or rewards. And be imaginative. When I say rewards and utilities, it's not necessarily monetary, though it can be. Like if an algorithm is deciding on a loan application, the reward is monetary. But algorithms can also decide like course allocation, which then can impact your CGPA, or like they can filter CVs, in which case the reward is the opportunity you get to say interview at a place, so on and so forth. So these are like very general terms, and what economists have done, what welfare economics has done wonderfully well, and this goes back to this axiomatic treatment I was talking about, is that they've come up with welfare functions that do satisfy some very nice properties. Let me reiterate that point. It's sort of important to keep at a high level message. The point is that here I'm not starting out with an objective function, right? Instead I'm saying, look, I have to evaluate valuation. So I can make decision one and it will result in some values among a population, let's say of capital T people, or I could make a decision two, which will result in a different tuple of valuations. So how do I compare these two? Right, and the way to compare is that you come up with a function that composes these t numbers into a single number, and then say whichever is higher, that's a better distribution. But what I'm not doing is that saying, okay, here's a good way to compose, let's apply that. What ends up happening is that you list out properties that you want of such a function, and then in fact you can filter out and say that, oh, this is the right function. It in many cases is the unique one that satisfies these axioms. Okay, just a simple example, slightly late, but imagine that you have a policy decision, or let's say an allocation decision, and you're running it among 4 people. So you can decide on some taxation policy which results in these utilities for the 4. The first person really benefits, gets 100, the rest 3 get a utility of 0. Or you can decide policy 2, in which case this is the realized 4 values, the utilities V1 through Vt of the 4 t equal to 4 agents, so on and so forth. What valuation functions do is like they give you a function that maps these t tuples into a single number. The higher the value, the better it is. And here you can actually see what if you want to be fair or like take care of the collective, and these are better metrics. But at the same time, do note, if I were looking at the sum, which is like a very ad hoc choice, the sum of the utilities, you would have gone here. The sum here is the larger than the other two. All I want to point out is many a times, including when your CGPA is being calculated, you are using the sum. You're using the arithmetic mean. It's not always the best metric of choice, especially in sort of the socially sensitive or decision-making context. Here, the minimum person is as happy as possible, so more like an egalitarian choice. The last two maximize what is called geometric mean. And this is what I was trying to say. I mean, I'll not have time to go into what these axioms are, but the way we land up at the Nash welfare function is like by studying these axioms. So we start at these axioms and realize that there's only one function that actually satisfies all of them, that happens to be the geometric mean of the utility. So you look at values, and which is a better tuple is defined as the tuple that has the higher geometric mean. So again, this was something we discussed, like this is maximized at this vector, the right hand side here, but this achieves a balance between complete fairness, the egalitarian extreme, and the utilitarian extreme of looking at the sum. Say that again, please. Yeah, so I'll add like a smoothing constant to take care of that, yeah. So we shift it a little to, it's a technically important thing, but I'm not, purpose of the talk, I'm sort of skipping that. Okay, so that's the geometric mean. So I told you this problem has two pillars, one coming from welfare economics, Nash welfare, done. The second actually coming more from computer science, a very, very prominent problem, the nearest neighbor search. I'll finish in 5 minutes. Yeah, it's called the nearest neighbor search, but again, sort of extremely nice even from a theoretical standpoint. And the problem as such is quite simple if I had linear time to solve it. So what's the problem? I'm given this list input vectors p1 through pn, they're d-dimensional vectors, and at real time I'm given a query q, again a d-dimensional vector, and some small number k, and all I have to do is find the k nearest, the k most similar vectors among p1 through pn. So if I could scan this entire list, very easy problem. With order n time or order n times the dimension time, it's very easy. The catch here is that this actually, as I said, it's back of the envelope tells me it's roughly 80,000 times per second, and that's only the applications I know of. So even before I finish this sentence, this thing would have been executed more than 80,000 times. So you have to do it at large scale. In many applications, n is actually web scale. A billion vectors is not a rare thing, and D also is large, like the dimensionality of these vector embeddings, as they are called in many applications, tends to be like thousands or more. So you really have to come up with a data structure over the input vectors, so that if I give you a query, you can really solve it with very astonishingly low latency. So yeah, again, formally it's a clean problem to state. I just want a size k subset from the input set, so that this total similarity is maximized. You get the k most similar vectors. Approximate means that, okay, exact you can't do better than order n, but I allow you some approximation in this objective, that's a and n. And they're products, like really large scale products, like DiskANN is the one that Microsoft uses, Annoy is Spotify, Gemini has its own, I'm forgetting the name, but yeah, there are dedicated clustering based or graph based data structures for solving this problem. Okay, what is the objective that I'm now going to address? The point is that it works wonderfully well, but what ends up happening and in a lot of these applications is not only do you want k most similar vectors, you do want some diversity among the k most vectors. So for example, if you look at the product examples, Amazon has a catalog where all the products are expressed, so-called embedded as vectors. The query now is a keyword query. A user comes in, searches for the word shirts. That word shirts is again mapped to a d-dimensional vector q, and they really do vector like nearest neighbor search to find for this query q shirts k products that are closest to it. So that's how catalog search in many cases works. So when you do return shirts, you actually not only want the closest ones, but do want some diversity among it, say in terms of color or certain other attributes. So this is a problem that really is was an issue for many of the products. It's coming from the real world. And again, unlike many cases where things like diversity and responsible AI is not well defined, here it's sort of rather cleanly set up for us. You have attributes. So every vector among those capital N has some subset of attributes, and you want diversity with respect to these attributes. Okay, and this was a solution that was deployed in many cases. It's again still deployed in some real world applications. What you can do is simply put a hard constraint. Say that, look, I want to maximize this objective, the same objective as before, but no attribute should appear many times. So you pick this ad hoc number k prime and say that return the vectors that are closest, but no attribute should like dominate the set of k things you have. So any attribute should appear at most k prime times out of the k times that you have listed. So here's the issue with it. So if I search for shirts and let's say I constrained it that white or black cannot show up more than 3 times, great, I do get diversity now. I have 4. With a hard constraints, I've limited the number of black shirts, let's say, to be 3. But the catch in this was actually observed by product engineers. If you now instead search for the query word blue shirts, so you have the same set of vectors p1 through pn, q, instead of being the vector representation of the word shirts, is now the vector embedding of the word blue shirts. A hard constraint is a bad thing. When the query is blue shirts, you really do want all 9 shirts or all k shirts to be, k returned vectors to have that attribute, to have blue. So that was one concern. The other concern is, if you just think about it a minute, this actually independent set hard. It's a fairly nasty problem even to approximate, and heuristics like really were struggling at it. So here's the key insight, the magic moment, right on time. The idea is to look at these attributes as agents. So literally think of them as entities, and the choice you make, the k vectors you make, actually attribute utility to them. So here's the setup. You look at every vector that you select, every k vector. Now for every attribute L, if this vector has this attribute, so you pick a shirt, and if it happens to be red, then you increase the utility of the red color. So if you have 20 colors in your entire catalog, you have 20 agents, and for every color, what you can do is compute this utility for any subset of vertices, k vertices that you pick. So it now maps it to a welfare setting, and you can maximize the geometric mean of these utilities. Just to address this question of 0, you can add this offset of eta to make things non-zero. And again, this was where I started. If you do this, again, this is real, it's not synthetic, this is Amazon data set. We have many, many more plots, but out of respect to the center, I did not include them. I really have system looking plots. But if you use this objective, you can kind of see that when you do need diversity, it gives you diversity. When you don't need, it organically sort of manages to do well. The theory result is that unlike the constraint one, which was independent set hard, this does have a 9 approximation. They're good heuristics, something that we actually have deployed. In a few weeks, we'll make the code even on GitHub. So I will stop there. Thank you for staying back on a Saturday.
For the graph theoretical results, have you looked for graph theoretical proofs of the same?
So the improvement to 1 is like quite combinatorial. It's like a local search thing. The point which I didn't sort of allude to is that this sort of machinery does give me guarantees for NV freeness as well. So even if you had like heterogeneous valuations, you do get nice results. So for that, we haven't.
Because you mentioned this Hamiltonian path thing where you actually get these connected.
Yes.
But that implies that there is a stronger version, right? That for any ordering of the vertices, you can...
So this gives you a counting result as well.
Right.
So then not only 1, but you can use that idea to say there are, in fact, notably many.
Right.
Yeah. But, I mean, the improvement by Hosseini et al. Is combinatorial. But this technique of mapping it to a cake lets us to, like, this was one result among many. It lets us like get something like, for NV freeness as well, it lets us establish results. Yeah.
Got it, thanks. And since you mentioned cake so many times, do you also have cake for us?
Yeah. We'll go to one of the bakeries, Nisha. Yeah.
Any other question?
Yeah.
Yes. Siddharth?
Yes.
Okay. So what was special about using Nash social welfare for the neighborhood search? Any other objective function or the axiomatic properties of Nash social welfare make it a uniquely good choice?
Not really. Like, so if you force scale freeness, and this was probably something that I the only function you can pick is Nash welfare. Yeah. So it's a function that wherein my hand is forced. So if I want scale freeness and these other axioms, up to sort of these eta shifts, that's the only thing I could have picked.
And do you have any thoughts, like if we can relax any of this, does that open up the possibilities of looking at?
So you can, I mean, you don't have to have scale freeness, but then you can look at egalitarian welfare. And like, there's a generalized version called p-mean welfare, so the entire family of functions you can look at.
Okay.
Yeah.
Thank you.
All right, so in the interest, oh, you have, can you take it offline maybe? Yeah, so in the interest of time, let's thank our last speaker and let's present a token of our appreciation.
Yeah, let's also thank all the organizers for this wonderful event.
Alright, so that brings us to the close of this event. Thank you so much everybody for coming. I feel really inspired by all the fantastic talks we saw. Let's thank all our speakers. And I'd just like to say a few words. I made a few notes so that I don't forget. The first thing is that, we're just starting out this center and we're really hoping that all of us can collaborate and take things, further together. So to the researchers here, I'd like to say that stay engaged with us. There are multiple ways in which you can do it. I have a few ideas and you're very welcome to suggest more. So one thing that we thought of is, having research clusters here. So for instance, any topic that you're excited about, which shares interest with one of the RCS faculty, you can find another couple of people maybe from anywhere in the world that you'd like to work with and who want to come spend time. We can invite them, you can come, they can come, have a research cluster here, spend a week, 2 weeks, whatever you want, and use that as a catalyst to your research. So that's one idea. Then we can have workshops on more focused themes. So since we were inaugurating the center, I wanted to do like a big theory fest, like just lots of exciting theory from all around. But we can have particular topics, more focused, where we can invite experts in those topics and kind of learn all the latest and greatest techniques and open problems and so on. So once again, anyone here is welcome to reach out to us, propose such a thing. Of course, at this point, at the outset of this center, we need it to be rooted at IITM with the RCS faculty. So whatever areas we already represent, we need to grow in that. So, reach out to any of us, propose workshops, we'll be happy to support that. Third thing is, let's have more of a student exchange. So, if you find through these other initiatives or otherwise that you have topics you'd like to work on with us, then send your students. We can support that. They can come here, spend time with us. Similarly, if you'd like to host some of our students, that's something that's also, we're very happy to do it. And going forward, right, I think what's the vision really? So right now, I mean, we've started out, even though it's a big thing for us, but it's still small in some scale of things. Everything is small in the appropriate scale of things. So the vision would be to have something where we don't even need IIT Madras faculty to necessarily be involved, right? So it could grow into something like a Simons Institute where, there is opportunity even for topics completely unknown to us, for people to come here and find a space here to think about those problems. We are a distance from that, but what I'm trying to emphasize here is really that the goal here is to push beautiful science, right? Create an environment where you can really do what you love the most. And I really hope that everybody here will stay engaged with us. We will routinely update our website with different initiatives. We'll make email lists, maybe you can sign up for that. And as I already said, if you have other ideas, just reach out to me. I'm very happy to discuss. I want to say something to students here. So we have students that have come from all over the country. I was really overwhelmed by the response that students showed. In fact, it was really sad that so let me tell you what happened. The great thing which happened was that as we circulated information about this center, about the event and so on, there was a lot of excitement in students all over the country, and this is of course fantastic. And within half a day, we had more than 300 registrations. And this is both fantastic as well as heartbreaking, because we don't have the capacity either in the hostel or in the dining hall or even in the auditorium to support 300 students. So then what we did was we did a round 2 where we said that please pay a nominal fee and we will reimburse that fee, but just as a commitment, like pay this fee. So I'm sure there were some spurious applications and possibly some duplicates, but even then, I mean, the number was much more than the 112 that we finally did invite. So what we did was we said pay this fee, and then we sat looking at our computer, and when we reached the number that we thought was the maximum that we could do, we actually closed the registration. And I have to say, I really felt bad doing this, but this is just a physical constraint that we had. So what I want to say, the takeaway is that there was that much excitement, and I think particularly among math students, where maybe this is recorded, okay, so yeah, less corrupted by some certain kinds of jobs. So I think that there is a lot of excitement for theory. The absolutely outstanding talent that India has for theory, I think nobody can, nobody even needs to think about that. So there is absolutely no doubt that we have this incredible potential sitting right here, and we're distracted into all kinds of different things. Many times there aren't enough opportunities, there are many challenges, but nevertheless we have really outstanding theory happening in the country. This was evidenced most prominently in these last 2 days, right, in all these amazing talks that we saw. So if you're a student, if you've come here, I'm happy you were not cut out by our very mean process. But if you were excited, please do apply to us. We already have some really great theory work going on, and moreover, we are going to sort of scale up more and more on these kinds of activities, these kinds of events, where hopefully we'll have lots of these wonderful researchers from all around coming. And we already have a lot of emphasis on collaboration, traveling, just having fun doing research, right? So please do apply, and that's all I have to say. So thank you very much again. Let me thank, I should say, very important. Very important to thank the many wonderful people who made this possible. My team from the Cybersecurity Center, who, even unrelated to this new center, has selflessly devoted all their time as though it's like a family wedding. So, Ram there. Jayanti, who I think each and every person, she had to leave. I wanted her to be here while I thank her, but her daughter wanted her to come away somewhere, and I felt like I've harassed her enough, so she's left. But she's really been sort of she's just put in so much effort into making this happen. All of you have engaged with her. And others like Madanan, who helped us in getting our wonderful new lab ready, though you haven't seen that. Kalai Selvi, who's helped a lot with the website. Edel, who's been helping with the mementos. Nagalakshmi, who's been helping with the registration. Is she here? maybe not. So we have a really dedicated team, and actually I think that credit goes almost 90% to this team, because all of you know how it is. I mean, if it were left up to me or the rest of the faculty here, like what are the chances anything would happen, right? So there's a lot of effort that the team has put in, and I'm really very grateful to everybody. And last but not the least, in fact the most, I'm very grateful to all the speakers. I'm very grateful to the audience. It's such an enthusiastic audience. In fact, we did not manage to get the big hall for today, and this hall, the capacity is 80. And Ram told me, this capacity is too little. We need to have a bigger hall. Maybe we'll do it in CS25, like the other in our computer science building. And I was like, no, we have the dining space here, and this is more convenient. This is nicer. And I'm like, come on, we're not going to have more than 80 people. This is, theory. There's not going to be more than 80 people, but there was. And we actually had a very decent number of students sitting in the overflow. So we, as a backup, just for the sake of completeness, right, like a proper theorist, we just had like an overflow room, just for the sake of completeness, where the talks would be live streamed. And as I'm sitting and listening to talks here, I'm getting a WhatsApp message, please tell people to speak into the mic because the overflow audience cannot hear. So, it's really amazing. I mean, there's been so much enthusiasm from the audience. It's so heartening, so encouraging. Thank you so very much for being here. I very, very much hope that I will see you all very soon again. And please spread the word, please stay connected, and have a wonderful evening. Thank you so much.